This college pre-calculus course is different from other college pre-calculus courses. Like many other ones, you will be learning all the concepts from an experienced university professor. But in this course, Ed Pratowski will also show you how to implement the pre-calculus concepts using Python. This course is for anyone who wants to learn pre-calculus, but especially for those who are learning computer science.
Welcome to Precalculus with Python. So we're going to use Python code to do all your math, and we're going to look at topics like triangles, trigonometry, solving triangles, finding out all the sides and angles and area of different triangles, even starting with just little bits of information. We're going to look at a lot of the graphs of the trigonometric functions, and one of the things with these graphs is they're repeating patterns. So we can graph things like tides or, phases of the moon or something like that that has a repeating pattern to it. And we're going to look at bringing data in, and especially data that might have repeating patterns, and using trigonometry and other pre-calc tricks that you'll learn to analyze that data. And being pre-calculus, all of this, we're going to get a little bit further into math. What are some things we can do with all these points? How can we graph things? How can we graph different sorts of functions? And how can we solve maybe some problems you haven't looked at solving yet? And then lead up to things like sequences, series, limits, and that brings you up into some things you'll be able to do in calculus. So let's dive into it, and let's take a look at pre-calculus with Python.
So the first thing we're going to do is set up your Colab. You might remember this from before, but remember, click on New, More, and we're going to click on Google Colaboratory. And if you don't have that already, you can go to Connect More Apps, and it might not show up there, and you click in here. You can search for Colab, and mine's already installed, but you could click and then install it if that's the case. So, new, but we're not going to do a doc or anything, more, all these other things. Google Apps Script, by the way, is more like this runs in all of your documents and sheets and everything, and it's kind of based on JavaScript, so that's also good. But we're going to focus on the Python and Google Colaboratory. There we go. You create a new Colab. Give it a title. Now, what you're going to do is you're going to build this throughout the course, like we did in the algebra course. So you're going to give this a name. You could even call it pre-calc if you want. There you go. If you something like that. I think in the algebra course I just called it your notebook. And we're going to add to this throughout the course. So what you can do is, it just gives you this code block. If you give text, and then if you double click, if you put the hashtag, now in the code, that would be a comment. In here, that's going to give it a title for the table of contents. So, I might have like get data, because that's the first thing we're going to do. And then, I'm going to put the code here. Code here. We'll get to that later. I just want to show you that if I add other text here, next topic, but notice I'm not putting the hashtag there. So over here, I go to the table of contents, and get data is in there, and we can find this. So you see, you can minimize that. So within this topic, you can have your two cells. And that's what we're going to do. We're going to build this throughout the course. And yes, the first topic is going to be how to get data into Colab, so that then we can do math to it. So we'll look at that in the next video. So let's take a look at some different ways to bring your data into Google Colab. So And all this, we're going to have like a math focus. There's much more you can do with grabbing data from different places, but our goal here is to get numbers, get arrays of numbers, and then we can do some math to it. So I'm going to really focus on that in a few different ways. Yeah. So maybe you have a CSV, comma separated values, that type of file, which can open in a spreadsheet, like Google Sheets or Excel, but you can get the CSV directly if you have that online. I have this, a few of these examples here. This guy at Florida State, he actually has this website that has, a bunch of different examples. So I picked a few of them here. So, we're going to import all these things, pandas, import files, IO, all this. And I usually like to define whatever the URL is as its own variable. That way, you keep it organized, all these different possibilities here. And then this code doesn't have to change. So there we go. That built-in pandas function reads CSV. And all of these things, I'm going to store them all as table 1. This and the other examples, so that you get the idea that here's all the ways you can get this data in as a table. And then now once we have a table, we can do all kinds of stuff to it. One of the things we're going to do is that function table1.head, the heading and the first few rows. This is usually, let's say you're getting this data and you don't know how big this table is. You want the heading because you're going to use that for some other things. And, the first few rows, you want to get a sense of what that data is. So the last line of code here, you don't have to put print or anything. If I just say table1.head, now if I just said table 1 without that .head, it'll actually just print out the whole table here. You don't even need a print statement. That may be overwhelming. So I just want table1.head, and we're just going to see what this looks like here. So this one was, cities.csv, and we see we have latitude and longitude of different cities. Interesting, but also just to show you that, hey, you can have numbers that you can work with. Maybe you want to import this into some sort of, plotting lines or something like that on a map. There we go. So we have that. I also want to show, supposing, and we've seen the heading, so I'm going to comment that out now. But let's run it instead, table1.describe. So we see it gives certainly all of your headings or your headers. That's what you want. And then with each of these, you get that description of each column. This is going to be really important. Now, the count, if you're counting something, it's going to be integers, but somehow it always puts this as a floating point with all these decimals. So there we go. Now, we can look at the count and see, first of all, that's great. All the columns have the same number in them. So I'm not going to have missing data. I like that. But there you go. Mean, standard deviation, minimum, maximum. These are also really important, minimum and maximum, because if I want to think about graphing this or, some sort of range, I get an idea of what I'm looking at here. So these are some of the things, heading, the describe. I'm going to show this other one here. So if I comment this out, and if I have this, let's do this one. The people one, actually, maybe I'll skip this one. The people one, that's kind of neat. There's like 4 things in there. All right. Letter frequency. Let's see. We have this, and I'm going to show you this. Just, again, it's just some tables as some examples here. And from some document, it has each letter and the frequency, how often this came up, and what percentage it was. There we go. Now, we might know from other statistics that E would be the most common, and we see that, shows up 12.6% of the time, which for 1 out of the 26 letters, instead of showing up, less than 4% of the time if it was all evenly distributed. No, E shows up 12.6% of the time. So there you go. Just interesting. And we could have this described. Now notice if you have both of these, I didn't comment out the heading or the describe. See, notice no print statement. So just saying table1.head, table1.describe, it ignores this, or it was going to do this, but then when we had this, it just bumped that out of the contention. So even if you didn't comment that out, that without the print statement, just saying that last line, table1.describe, that's the thing it's going to run. And so we see, frequency, count, scientific notation, even though it didn't need it. So 2.6 times 10 to the first power is 26. There we go. Mean, median. So just some interesting things. So I just want to show you this. So this is one way that we can have, different URL and some of the key things we want just stored as a table, and then something, the heading or the describe. Now, you could also upload the CSV, and this is all the code you need. It will give you, this creates this dialog, this files dialog. So then if we're going to call it uploaded, so that, if I had this without the uploaded equals, it has a file dialog, but it might not do anything meaningful. Whatever you pick, it's going to store it. Then whatever you pick, it's going to store it as this variable. And then this is the way to get the file name. So whatever you just selected to upload, and, it's going to pick that one. Yes, you're going to iterate through exactly one thing. So that's why you can just say next. So there's your file name. And I'm saying that this is a CSV, so that way I already know that I'm going to do .read CSV file name. And once again, what am I doing? I could actually just have this without the table 1 equals. And again, it'll do that, but it's not going to really accomplish anything. I want to store it again as table 1. So now I have this, data frame table. And from that, storing it as table 1, we can do all kinds of other things. So pretty cool. Maybe I have a table on a web page. And remember, we see a lot of web pages that have tables. A couple examples I have are, Wikipedia pages. You might have a web page with a lot of tables. So this one, my importing, pandas, I'm going to read HTML, and I'm going to, just knowing I'm not just reading a table or CSV, I'm reading the website, read HTML. But this one, I'm going to store it as a variable tables. So that's going to be my list of tables. And we see, I do want to print this. So this, you can use this for exploratory situations. There are how many tables? All right, well, I just stored that as all my tables here. And I can say, now, having already looked at this, I might not even need, these last 2 lines at first. I could just, or these last 3 lines, I could just print out this one. How many tables do I have? I happen to already look at this. I'm like, oh, table number 4, that's the one that I want. So you see, now I'm just going to have this tables element number 4 from that array. And again, what am I doing? Storing it as table 1, and I'm going to print that out. Now, there we go. It happens to be different managers and the years and wins and losses. I just thought that was an interesting thing because we can have some names and dates, fine, but I also have a bunch of numbers I can use. Wins, losses, winning percentage. There we go. So, that's the one I decided to pick. Now, notice, I picked this one, Wikipedia for the Philadelphia Phillies, because the Phillies. But, I also put another one, Cricket World Cup and similar data if you want to analyze that. And now we can do some other things with this. Once I have this stored, so let's say I run this block of code, and now this table is stored as table 1. I can continue that and I don't have to go through, like once you import that, it's good for the session, which can be hours or up to like 20 or 30 minutes of inactivity. If you aren't running any code, this cell or another one, for like 20, 30 minutes, it still might stay there in, the current memory. If not, then you might have to go, you leave and come back, then you might have to go and run that other one. But this is good for anytime you're importing all this. Great. Now I have all this. I don't have to go through and do that again. Now we can say this. And what I did is just, just to show some of the things we did, I just calculated my own winning percentage just because. So just to show you, so I can have this table 1, because now that I have that, I see all my headings. So I'm going to take table 1 wins and table 1 losses. So you see, looking at this, I can pick these table headers, and this is going to be an array, np.array, because I already imported NumPy even in that previous code cell, and I'm going to create a NumPy array from there, wins and losses. And then what I did is I just made my own average equals wins divided by, wins plus losses. You could print that out. I just put that in there. But here's what else I did. I created another table column. So now I have table 1 average. This didn't exist before. That equals this. So I create this average, which is, if these are NumPy arrays, look at this. I can make this other array of all the averages. And then I can create a new column. Now, that's there. So I could print this and I could have manager winning percentage. And then now that I created that, I can just add this other. There we go. I don't really need the extra space. Average. I can create this other column. So now I'm going to print table 1. Now, first of all, notice it did print it. And, really this Python creating the averages, it really just, this table was correct in the winning percentages. The Python calculation just takes it to more decimal places, but that's okay. The other thing, these subtle things, notice this time I decided to use a print statement, which I didn't before. And just notice the subtle differences. If I do print, this is what it looks like. Whereas this is what it looks like if I didn't use the print statement. And early on, I like doing this. It tends to format it in a way that might be easier to read at first. But if I already know that it's going to be just a few columns, I just might want to use the print statement. It really just does, it just displays it differently. That's all. So pretty cool things you can do. I'm going to do another example here. Again, reading, URL. So importing everything, date, time, and calendar. We're going to use that later. But you see this one again. I'm just going to, here's the URL of, again, I just picked place, tides. I think that's pretty interesting because, it goes up and down. That's going to link with some stuff we do later with periodic data. And now the URL, again, my array of tables, and we'll see this. Now, if I just comment these out, you see, because if you're doing something exploratory, maybe you're not as familiar with this site, or you're like, oh, how many, I see it, but how many of them are really formatted as tables? We can run this, and it'll say, boom, there's only one table. There we go. So knowing that there's only one table, then I can go back to this and say, oh, okay, print table 0. And again, I'm using the print statement. You could just put table 0 without the print statement. That's fine. There we go. I happen to know that, this is not going to be too big to be overwhelming. And then we have all this. So tides, date, time, and the height in feet, high tide, low tide, high tide, low tide. There we go. And it should alternate. I think, yes, it should alternate. So there we go. Now, this next line, I may or may, don't necessarily need to do this. I could have just kept tables 0, element 0. But just to be consistent, I'm just doing the same thing, converting it to this variable table 1. Because now we can do anything, if I had a bunch of other code, boilerplate code of all different things I want to do with table 1, now I've stored that as this variable. So there we go. And again, table1.head. So notice this, I'm printing it. And then when I do this without the print statement, we'll see how it formats it a little bit differently. Oh, because I already printed it here. So instead of scrolling down, I'm going to comment this out. There we go. Yep. So there, as another way to print it. Now, what I want to show you with this is continuing this example. If I want to do some math to this, again, connecting with some things we're going to do later with periodic data and being able to graph this, but I have a date and a time, which is, of course, AM and PM. So down here, continuing that example, I'm trying some different things. I'm going to convert all of this to all that date and time. Look at this. I have, the day, the month, the day, and all this time. I want to convert this to some sort of numerical data that I can graph. So I'm going to take this time list, date list, and I'm going to create these arrays, hours, minutes, days, and convert this to epoch time. So I'm going to call it epoch array. And really that's going to count the minutes from a certain point. By default, it goes to January 1st, 1970. So, that's a way to make, compare times, because you can convert everything to this. And then you have everything consistent minutes since January 1st, 1970. So I'm going to go through this, I have my time list, and I'm going to loop through this for T and time list. I'm going to split it. I know it's a time, so it's going to have the colon. And then I'm going to take the first part, convert it to an integer. That's going to be the hour. I'm going to take the second part, and I know that that's minutes, so I'm going to convert it to an integer, but I'm going to take it just that first part, because I know we had AM and PM, so I just want the first part as minutes. But then, if the last 2 digits say PM, then, and this if statement, I put the colon and I did not make it on the second line, that works. If you just have one little thing, you can do it all in one line. So my if statement here, if the last 2 digits are PM, or last 2 characters are PM, then I'm going to add 11 to the hours. And there we go. So I'm going to, each time then, for each of those, then I'm going to append the hour array, append the minute array. And then you could do this, I commented it out here, but you could print it out to then show, okay, what do my times look like, just to see that it's right, that it is doing what you want it to do. So a lot of times when you're trying some things, let's say exploratory, you can print things out to test it out. And then I'm going to go to date, but now notice I'm going to have this date. Well, I wanted to skip over I just want the day. And this is just because for this particular data, I'm just going to grab everything that I already know is in the same month. So that really is why. So I'm skipping over the day of the week. I'm skipping over, they're all August, so I'm skipping over the next 3 characters. And I just want starting at character 8 to the end of the array. And then that's going to be just the number. So then I'm going to cast it as an integer and append it to that. And then now I have my hour, my minute, my day. I'm going to store this, in the range. So in range of the length of that. So all of these are are the same. So I just picked one, time list, and the length of that. So now C in that range. So notice if I say D in date list, D is going to be each element in that date list. But C in range, I don't want each element, I just want the number, how long this is. So now I'm going to convert this to a date time. So, it's going to be this year, this month, and then each one, day, hour, minute, and then seconds. I'm just going to make it all 0 seconds, because now I have that T. I can convert that to a time tuple. Calendar.timegm, which is Greenwich Mean Time, and cast that as an integer. So this line here then converts all of that to an epoch array. Pretty cool. We'll print that out, but we'll get to that in a second. And then I just want the heights to float numbers. So, table1.feet, it's all height and feet. So that's why I call it F array, because H was already done for hours, so I can't use H for height. So F for feet. And I'm going through each of those, and I'm going to append this. So the first 4 parts, so I'm taking that substring, which is just the height and feet, or the first 3, 0, 1, 2, 3, because they all work out to 3 characters in that array, so it works out. I'm going to get those 3, which will be the number, cast it as a float because they all have decimals, append it to that. So just showing you some of these acrobatics that you can do. Hey, you have a table. I know I have numbers in here, and I know it's numbers I want to work with, and I'm going to print out that array. So just to show you what this looks like. So you see that first one is going to be the array of times. There we go. And the next one is going to be the array of heights. And once we have these 2 arrays, you can do anything with them. You can bring them into, some sort of graphing utility. You can, graph and do all kinds of things with that. So, pretty cool. We'll get to that other graphing later, but this is really all about getting this data into some sort of math form, getting it from different places and into some sort of math form. Now I have 2 arrays of numbers that I can do math to. I can graph or whatever. You may have data in your Google spreadsheet. There we go. And this is another one you need to authenticate. You can mount your Google Drive. So I have this Google code snippet. If you're looking in Google Colab down on the left hand side, it looks like brackets. You'd have like an HTML or XML tag in. You can click on that, and it'll bring up various code snippets. You can search through them, and then when you pick one, you can even insert it like right in here. I modified a tiny bit just to simplify what I wanted to do. But there we go. So you can get these code snippets authorizing this, all these imports, and the code snippets help because see this like creds, comma, space, underscore, equals default. These are the things, I would never think of that off the top of my head. And there we go. So I'm going to authorize this, and I'm going to open. I made a silly spreadsheet with just a few lines comparing file types. So that's the name of it, and then .sheet1. There we go. But all I'm doing is authorizing this, and then I'm storing this first sheet in here. I opened that file that I wanted, first sheet, and I'm storing that as that variable worksheet. Notice I didn't have a print statement, nothing else happened. But now I can continue that, and now it's already stored there as that variable worksheet, and I can keep going back to that and working with that, doing different things, and I don't have to like make that connection with the Google Drive again every time. This, and if you're ever doing things with Google Apps Script, the fewer calls to the Google Drive, the better. So if you can like call it once and get everything you need and then work from there, that's great. So, now I have worksheet, and so I'm going to use that variable, worksheet.getAllValues. And I'm going to store that as rows. So this is pretty cool. I can print rows. If you know what your how like it's your Google Sheet, and you know how much stuff this is, and it's not too much, you might even just say print rows and just print all of it. You can do that. And then I'm going to print the length, and here's what I'm doing. Oh, what I'm going to do is I will print this, print the length of the rows. It's just a silly sheet, but it's fine. So I'll print the rows, how many, and then now I just want, what I did is I made the third column, the other ones have words, the third column has numbers in it. So I'm going to create this integer array and number in range. All right, so the length of this, and what it does is, even though you have this spreadsheet, each row is its own element. So now I have, I can say the length of the rows here, and that's gonna be how many rows, even though each row will have an element. So it ends up being a two-dimensional array here. This rows, when I say get all values, it ends up being a two-dimensional array, rows, columns. Okay, so and I have a header, so my range, I want to start it at 1 because 0 would be the header. All right, so now I have that range, and I'm just going to go through these numbers. I know they're numbers, so I just call it the variable num. So here's what I'm going to do. Remember, it's a two-dimensional array, so for each one, I know this is the third row, so I want the num is what row it is, and then I know, or it's the third column, so I know it's what row is num, that's what we're looping through, and I know it's the third column, so that's why this is a 2. Remember, start at 0. So there we go. I know that I'm going to take going down that column, each row, and then I know their numbers, but I need to make sure I cast it as an integer, and then I'm going to append this to the integer array. So there we go. And there we go. So again, ways to get to this. And now, once again, I have an integer array. Now, what you could have is, you could have a length of rows, and it's just a sequential count. So you could store this, as, X or something. You could always make this, like X equals length. You could always have a variable like this, X equals the length of rows. And that way, it's sequential, and you could count up through that as some index or something like that. And then now you have this array of all these values in each row, and you could pair them up then, okay? Plot. Different things you can do. So again, ways to get data in from different places, and select, hey, I might have columns with words in it. This course we're talking about math, so we're going to skip those. But even when they have numbers, I need to get it in the right form, usually some sort of array, and then I can do some other stuff with it. And I'm not going to go through all the different file types, but just as an example, you can, let's say if it was, XLS with or without that X. So all our Excel files, if that's online as a URL, and you can work this, sometimes people upload it to their website. Some people have it as something on GitHub. All that, it all works. You can see if it was just uploaded from your local drive, you can use the previous example here of just uploading a file from your computer. But if it's anywhere online, there you go. It's an Excel file. And just knowing that, I'm going to do this, pd.read Excel. And once I have that, now it's stored as a sheet, and I can, print it out. Or display the header. So I just wanted to show you this. This works out as long as you are pointing to an Excel file. There you go. Because if it was pointing to, actually, this would work for a Google Sheet too, but also you can use that URL as well. If it's a public Google Sheet, that would work too. So just all these different file types, how you can get, all this different data in Google Drive. And as you make this, from different things, you can even make them all headers, so you have some examples of, you can have a table of contents for all the different ways that you can bring this in. And remember, table of contents, if you're putting this in there, you put the hashtag, which in the Python code would be a comment, but in here it would mark it as a heading. So some things you can do: getting data from different places, bring it into Colab, and now all different ways. Get a table. You can do a lot of things with it. Get different arrays, and then we can do some math to it. So now let's get into some of the math that we can do with all this stuff. So we'll take a look at that stuff next.
So I just want to briefly talk about drawing lines on the graph, even when there's no function really, but you can get a bunch of points and you can write the code. So most of this we're going to talk about with the code, but just to give you the perspective, you could have, a few points, and you could write the code to, rather than develop a function, say, hey, I'm going to draw from this point, and it's line to this point, line to this point, line to this point, line to this point, and you can finish it up and close it out and go back to the first point and make a shape, or you could create all these other drawings or shapes that you want, whether it be to make art or whether it be to represent data that is definitely not a function. So there's a lot of different things you can do. It doesn't have to be a math function, but there's still some code you can do to get data from a list or something, and we'll look at that, and represent it in different ways. And sometimes maybe you can draw lines and represent different shapes that way, and we'll look at some applications of that. So let's look at the code.
So let's look at drawing lines with code. And sometimes on introductory, learn how to write code activities, you'll find things. But this is the full code that also works, things like this, but this is the full code that works behind the scenes. So we're going to import a few things. I'm going to import Matplotlib library, and I'm going to import this other one from within the same library, path, and then again from the same library, patches, and we'll see how they come into play. So I still want to set up an array, or two arrays, one of them an array of each vertex, and then I'm going to create another array of all the different steps I'm going to do. So if I wanted to just do this one at a time, I could do this. Here would be my starting point. I'm going to take this vertex array, verts.append, and I'm going to append this 0, 0. Notice I do use decimal places. I want to make it floating point numbers rather than definite integers. So I have this, I'm going to append this x, and it's going to end up being an xy coordinate. Notice the double parentheses and everything. And then to each step, steps.append, that's going to be the first step. It's going to be path.moveTo. And so the first step is going to be, I'm going to move to this point, 0, 0. And I could just continue adding. I'm going to add a line now, verts.append to. So now this is my second point. And notice this one is path line to. So move to will give you the path, that's where essentially a starting point without drawing the line. And then line to will go from that point to this one with a line. And this is where I could keep going and I could always put, more here, as many lines as I want. But I'm just going to show this simple. I'm going to start here, draw a line to this point. All right, and then now here's the graph. As before, set up the graph. I'm going to set up the axis, and for here, 5 in every direction. That's going to be fine for what we're doing. So this is where I'm going to create this variable called path. And what it is this Python function path, and it's going to take these arguments of these two arrays, verts, steps. So, that function, I'm going to store it as the variable path, because then I'm going to use that. I'll create this other variable called patch, and then it's going to work on this Python function, patches.path patch, and then this variable path is what's in the parentheses. So probably easier to write the code than to say all this. Path, patches, path, patch, path. Anyway, so then on my other variable for axis, I'm going to add patch, that Python function, and then patch. So we see create the two arrays, and they go into this function for this variable. Then I'm going to use this variable in here to create this variable, and I'm going to use that variable in here when I'm going to add them to my axis, and then I'm going to show it. So if you were going to draw lines, it really is good to start out with your array. You have your imports and your arrays that won't change, and then all this, however many points you want, you can just add them all right here, and then all this graphing code doesn't have to change. So this is just going to be a simple line when we run this. There we go. I didn't even draw XY axis lines, just 0, 0, 2, 2, 2, draw this line. All right, if I wanted to put more, I could, and here's what I'm going to do. I'm going to append this, and if I drew another line, so maybe I'm going to call this 2, -2. I'll go draw a line down to that one. And then I'm going to do one more thing, which is going to be I'm going to go back to 0, 0, my original point. And so that gets its own special close poly function. So I can move the point and then draw, start there, line to that, and then close the poly going back to the original. And you see as many different points as I want to create here. I'll run this, and there we go. Boom, 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 makes a triangle. All right, good times. And there we have it. So I'm going to show you a couple things that we can add and tweak to this. You can definitely do these each step, and sometimes that helps because then you can really just picture, that what lines up, this point, and then going line to that point, this point, close poly. But you can create your arrays right out of the gate. And here I'm going to create my array verts, and you see just each point in this array. And then I just call this one codes, but here's the array of steps, and you just have to keep track of lining these up. Also notice I can continue it on one line like I did with verts, or I can hit enter and then just put them in line here, comma, and then on the next line and put the array here, which it actually is just fine to have a comma at the very end of this array. That works out. So then we just match it up. You see, move to line, that first point, line to that second point, and then you just keep track, line 2, line 2, line 2, closed poly. And I should have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and that works out. So just another way I could define all these, especially if I know what points I have, this method might be easier. And I'm still going to use that same code, BC, verts, and then codes because I need that. And then I stopped the variable here for patch, but I can add some other things. You see, I can change the face color and I can change the line width. So let's take a look at that. Now, it was a light blue, but if I just say blue here, it makes it this nice royal blue, and the line width, you see, it makes it a little bit thicker. Pretty cool. So, I mean, you know, let your artistic mind go and see what, you know, different things you can create just by drawing lines and, you know, running it this way. Pretty cool things. And, you know, this is again just scratching the surface. You can build upon this and do all kinds of cool things with this. So I'll leave that up to your imagination.
Right now we're going to talk about trigonometry. And trigonometry, this long word, we can break it down into 3 parts. So tri means 3, gon means shape, you know, like polygons, and metry means measurement. So metric would make it an adjective, like the metric system, but with the Y, we make it a noun, so trigonometry. And these old Greek words, we read them backwards, so it's the measurement of shapes with 3 sides. Triangle class, as many of my students mentioned. So let's focus on triangles with right angles. So our right triangles. We will get even beyond the right triangles. So trigonometry applies to a lot of things, and we really can break down anything into triangles. Any other shape can be made up of triangles. So that's why it becomes so central to figuring out a lot of other things. And with that, we're going to start with right triangles. So the reference angles here and the reference sides, it's all these relationships to the sides and the angles. So if I call this angle A, then this side is across from it, so it's the opposite side. So instead of saying across from, we're going to say opposite. Kind of mean the same thing. But these are this is the notation we usually use in trigonometry. So if that's the opposite side, now then this would be the adjacent side. But notice they're adjacent meaning next to. But notice from this angle, I have 2 sides that are next to it, but the hypotenuse is always its own thing. And the hypotenuse is the longest side. It's across from the right angle. So since I have 2 sides that are adjacent to angle A, but one of them is the hypotenuse, so then the other one I'm just going to call the adjacent side. So now I have from angle A, the opposite side, the adjacent side, and the hypotenuse. Now, again, these are references to how they're related. So if I was talking about angle B instead, then this side is no longer the adjacent side, and that's no longer the opposite side. Then if it's angle B, this is the adjacent side. And then this is the opposite side. Because now this one would be across from angle B, this one would be next to, and then the hypotenuse is still its own thing. Now, this matters because in figuring out a lot of things about triangles, we set up these ratios relating to the sides and the angles. So we're going to talk about 3 main ratios, and then later on we'll add 3 more, which are the inverse, the reciprocal of these 3. But these 3 main ratios, and we'll see as we talk more about trigonometry how this comes up in different ways. So we have the sine is our first ratio, and the sine of whatever angle. Now officially I'd put it in parentheses because this is a function, but you'll see a lot of times, in the notation, people might skip the parentheses. certainly, as you get into writing the code, we need the parentheses. Again, this is a function. So the sine of whatever angle is the ratio of the opposite side over the hypotenuse. And I'm just going to abbreviate those here. So so when I say the sine, it's the relationship. So if I was talking about the sine of angle B, whatever the measure of this opposite side divided by whatever the measure of the hypotenuse, and that's this ratio. And if that's a certain angle, no matter how big the triangle is, that ratio, the sine of 30 degrees, the sine of 35 degrees, it's the same each time. You can plug that in your calculator, sine of 35 degrees, and that's a constant. So I get that relationship, the opposite over the hypotenuse. And notice, I remember the hypotenuse is the longest side, so the opposite side is always going to be shorter. We're going to have these decimal numbers, usually really long decimal numbers, but we may round it to like 4 decimal places. And we'll also look at some other patterns in that too. So the other relationship is the cosine of whatever angle. I'm just going to call it angle B for now. And the cosine is the adjacent side over the hypotenuse. So that's the cosine ratio, the adjacent side over the hypotenuse. And then the tangent is the relationship of the opposite over the adjacent. So now with these 3 ratios, one of the things we might notice is that if I use now having all 3 of these, depending on what situation I have or what angles or sides I might know or not know, I can use one of these 3. It'll apply. So that's why it's good to have these 3, the sine, the cosine, and the tangent. And later on, we'll look at like how they all, where we got these numbers from, how they all relate. So a lot of things that we're going to do in trigonometry, we'll learn one thing and then that'll come back around again when we learn the next thing. Oh, it relates to this. It's very like, it's not linear. It's very circular and all kinds of, hyperlinks in your knowledge when we talk about trigonometry. So you'll find it to be a pretty interesting subject. So I have these 3, ratios. How can we remember these ratios? Well, there's the sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent. So, and also remember, it is the same ratio, whatever angle I'm talking about. So if instead of angle B, I was talking about angle A, whatever, it's the sine or cosine of that angle, and then, that's still the relationship. So how can we remember these? There's one interesting way that a lot of people have found. So sine is opposite over hypotenuse. So cosine with a big C is adjacent over hypotenuse. And then tangent with a big T is opposite over adjacent. So if we write it like that, then and a lot of people then pronounce this as SOHCAHTOA. It's catchy because then you remember, oh, SOHCAHTOA. So, this is SOHCAHTOA is the mnemonic device that, leads us through our journey of trigonometry. And so we follow SOHCAHTOA, and that reminds us that sine, cosine, tangent, and what the ratios are. Because they're going to be very useful. And we're going to look at how we can use these ratios to figure out some things. If I don't know an angle, if I don't know a side, I can figure this out. And that's what we're going to do next.
All right, so here's how to draw the triangle in code. And I want to show you this because it's going to be relevant. We'll use this as a display. And you might remember the pie plot. We'll import that, import display, import math for some of the things we use, and time, because I comment this out here, but you could delay for like 1 second, the drawing of each line to make it more dramatic. So I just wanted to include that as a possibility. And remember, we set up the subplots here. And I'm going to set this axis. This is how I decided to set it up for this triangle. The x value goes from -2 to 12. The y value goes from -2 to 8. And I'm not going to draw any other lines to show the x and y axis, but that just seems to be a decent size window. Here, then, I will display this text, which is the letter A. I'll display that at this point, 0, 1, and here I'm going to draw a red dot at that point. Well, what does that mean? I'm drawing the points for my triangle. So this line draws one line for the triangle from remember these are the x values as an array, these are the y values, so the line goes from 1, 1 to 7, 1, and it's going to be blue. Then we go from 7, 1 to 7, 4, that vertical line is going to be blue, and back to that original 1, 1, and then to the other point, 7, 4, that line will be blue, and we'll display it. Like I said, you could draw each of these lines and pause and make it dramatic. Also, the fact that I'm drawing a bunch of these lines, Python wants to draw each of these as a different grid altogether. So every time I do that clear out, put in weight, doing that after each line here enables it to not have multiple graphs. So then I'm going to have the text, there we go, adjacent side, the text opposite side, and then we see, I just tinkered with this, and this was a good place to put it. Text that say hypotenuse. So when we draw this, then it ends up drawing our triangle here. So we see a dot that I'm going to label angle A, and because this is angle A, this is the adjacent side, it's next to it. Now the hypotenuse is also next to angle A, but the hypotenuse is always its own thing, as we were talking about. This other complementary point or angle, that's B, and the right angle would be C. So from A, we have the adjacent and then opposite because it's on the opposite side of the triangle. Just as a way to show you that you can draw the triangles with code. We'll tinker with that and draw some other triangles too. So that'll be a good basis. So what can we do with this? We can get the sine, cosine, and tangent functions for each of those angles. Now, we'll talk about radians in more detail. It's another way to measure angles related to, 1 radian is about 50-something degrees because it's the measure of the radius along the outside of the triangle. We'll talk about that in more details, but the short answer here is that all of our trig functions use radians. So if I want my angle in degrees, then inside my trig function, I just have to convert it to radians. And so that's why I imported math, and we'll do math.radians. So math.cosine, but radians tend to be a lot lower numbers, so you'd get your answer and that doesn't make any sense. So just for now, we'll do the angle in degrees and convert it to radians inside there. So what I have is, there we go, given that angle and, change the angle, we can just change this one variable there, and we'll calculate the sine, and I switched these for some reason, the sine, the cosine, and the tangent. So I just saved them as these variables, S, C, and T. So the sine, cosine, and the tangent. And then we're going to round it. 4 decimal places is good. Most of these will be really long decimals if you let it go, so 4 decimal places is good. And then we're going to calculate the sine and print the sine, cosine, and tangent. So looking at that, angle A, and it'll print out sine, and I picked 30 degrees, so the sine of 30 degrees is 0.5, cosine is 0.866, which this one actually works out to something else a little bit more elegant if it wasn't a decimal, but we'll get to that later too. And the tangent is 0.5744. Again, 4 decimal places, that's good. So there we go. And once we're talking about doing code with this, hey, maybe I have this one angle, but I also want the complementary angle. So you remember I didn't label it up here, but the other angle that's not the right angle would be angle B. And so the complementary angle, once I know angle A, then B is just 90 minus A. And if I want both, then I'm going to change my variables here, SA, CA, and TA for sine, cosine, and tangent. And I just usually remember them or think about them in the same order. So you really don't have to, but there we go. So sine, cosine, tangent, and then I'm going to print it out, sine, cosine, tangent. And then I put this down here, so the sine, cosine, tangent of B, and that's what we'll have, sine, cosine, and tangent of B, and we'll print it out, the sine, cosine, and tangent of B. So when we run this, there we go. So we have our sine, cosine, tangent, but then we also have the other angle would be 60, so the sine, cosine, and tangent of angle 60. So there we go. And we're just starting to dive into a lot of these patterns here. So this is just the beginning, just noticing how, well, for whatever angle, you can easily find sine, cosine, and tangent, as well as those 3 trig values for the complementary angle. All right, so not bad. One of the other things, remember all these trig functions, they are constants. So the sine of 60 is always 0.866. And knowing that, then whatever the sides are, if I know one, remember, if it's opposite over hypotenuse, if I know one of the sides, I can figure out the other. And just as another thing we can do, we can loop through, the sine, and, I just decided to go from, 0 to 180, and the only thing here I'm going to import is math, and I'm going to loop through the sine and just show you that for a second here. So notice this one I didn't round it. Python will round it and jump all the way down there. So sine of 0, 0. And just degrees, I just got to, 1 degree. And we see these little, a lot of decimal numbers, a lot of decimal places, but look at the really tiny numbers, zeros, 0.1, and, we keep going. I'm already past the sine of 30, which, because notice that worked out. You see, it really is 0.5 or 1/2, the sine of 30. Sometimes the way Python calculates things, it doesn't round it, but that really is, 0.5 is the exact answer. And then we get to all these others, and we get down to 7, 8, 9, and this one did round it properly. The sine of 90 is exactly 1. And what do we notice about these values? Let's go somewhere around here. So look at the sine of 89, 0.999847, and the sine of 91, 0.999847. The sine of 88, 0.999390, and the sine of 92, 0.999390. We're going to dive into some of these patterns here. But for right now, looking at the sine, cosine, and tangent, and you see it'll go back down. So the sine of 180 is actually 0. So, now, this next thing, supposing I know those ratios. So this is whatever those sides are. If I divide them, whatever those sides are, then I can figure out if this is the ratio. And, if I know the angle, I know one of the sides, I can figure out the other. But supposing I know both sides, but I don't know the angle. And so that's an inverse function. You know, the sine of, I'm expecting an angle, and then the answer is this ratio, which, you know, for like 161 would be like 0.325. So supposing I know that ratio, I know the two sides, I can divide them, get the ratio, but I don't know the angle. Inverse function. And the reason why it's a sine is because the full word is arc sine. Another way to look at this is inverse sine, and there's some other notation for that. So, you know, now we get arc sine, and if I do the arc sine, let's say I knew this ratio, you know, 4/5. So the opposite side would be 4, the hypotenuse would be 5. Then remember, you know, this would return radians. So then I would have to make it degrees. So there we go. In my 3, 4, 5 triangle, the sine, if I know, oh, one side's 4, the hypotenuse is 5, then that one angle is 53. And then I can do the subtraction to get the other angle. So now let's take a look at what we can do with, the next thing we'll do is some things we can do with this information. You know, how to figure out each side or each angle.
So let's see how to use some of our trig ratios to solve triangles. And here's the normal naming convention for a triangle: capital letter for the angle, and then that lowercase letter for the side across from it. So capital A, C lowercase a, capital B, and then lowercase b, capital C for the right angle, and then for the hypotenuse. That also follows classic Pythagorean theorem: a squared plus b squared equals c squared. So I'll make c the hypotenuse. All right, so supposing I know some of these angles or sides and I want to figure out another one. So let's say I know that angle A is 30 degrees. And then if I know that the hypotenuse is 10, but supposing I want to find the measure of the side A. So I know enough to figure this out. So I can see that from that 30-degree angle, I want to know the opposite side, but I do know the hypotenuse. And so then that tells me, oh, these three, I must be involving sine. So I set up my equation, so the sine of 30 equals A over 10. And remember that the sine of 30, that is a constant. It's always going to be the same number. And therefore, I only have one unknown, and I can solve this. And I'm going to do one step of algebra first. Get A by itself. I'm dividing by 10, so I multiply both sides by 10. So 10 times the sine of 30 equals A. And that you can do in one step on the calculator, or you can write the code, which we'll talk about in a minute. So 10 times the sine of 30, and I'll tell you that the sine of 30 is 1/2. They don't all work out so nicely, but that one happens to be 1/2. So 10 times 1/2, so 5 equals A. And then we can figure out the measure of angle A. If I wanted to figure out this, and maybe I didn't know this. Maybe it was angle B that I knew. Now, we always can do subtraction because I know that that's a right angle. But let's just say that angle B, I knew that that was 60. So instead of doing the subtraction, let's just say I still want to figure out the measure of angle A. Oh, well, in this case, it would be the adjacent and hypotenuse that I want to involve. And so then that brings me to cosine, adjacent and hypotenuse. So what I would do is I would write the cosine of 60 equals A over 10. There we go, one step of algebra, and I'm going to do 10 times the cosine of 60 equals A. And I picked these as examples. Cosine of 60 also happens to be 1/2. And we'll look at, these interesting patterns in a little bit. But then that works out because 10 times 1/2 still gets me to that same answer, 5 equals A. Pretty good? So now I'm going to do a tangent example. And let's say now tangent would not apply here because either of these angles, opposite and adjacent, I don't know either of them. But let's just say I didn't know either of these, but maybe I'll go back to this one being 30, and let's say I know this one. I'm going to change it up here a little bit, and let's say I know this one. I'll still say that that's 5. We'll stay consistent with this. So the tangent. So I'm not going to use sine or cosine because I don't know the hypotenuse, and I know that angle, but I know which is the opposite side, and I want to know the adjacent side. So then that tells me, oh, then that's tangent. So I'll set it up that the tangent of 30 equals 5 over A. And I'm also going to do 2 steps of algebra with this because A is in the denominator. So my first step, A times the tangent of 30 equals 5. But notice, not quite there to solve. I need one more step. Divide both sides by the tangent of 30. A equals 5 over the tangent of 30. There we go. And tangent of 30, that is also a constant. And then when we divide 5 divided by the tangent of 30, without doing this on the calculator, it's going to end up being, so A would, oh, sorry, I meant to make that angle B, but that's okay. Angle B, because that's the one I wanted to know. So 5 divided by the tangent of 30 is going to be 5 root 3, because, so B equals 7 times 5, so it's somewhere around like 9. Yeah, so it's really 5 times, the exact answer is going to be 5 times root 3, but then it's like 8.5, something like that. Which is why it's, we will get to the point that we're doing this stuff on the calculator or writing code, because all of these, the 1/2, that was a nice example because occasionally we get that, nice 1/2. 5 root 3 is the exact answer, but, about 8.5. Most of the time when you're solving these, you're going to get, weird decimals. I mean, at this point, a square root answer, that's a nice exact answer. But even most of the time, you're going to get some weird decimals, and all these 3 angles and sides. Yeah, it's very rare that you'll get something where they all work out to like, even like 1 decimal place. So, solving. Now I have, how can I use each of these to solve for the sides if I know an angle on one of the other sides? But what if it's the angle that I don't know? So let's have a twist here. So if I keep this, maybe if I don't know this angle, and I'll tell you this, it's not going to be a 30, 60, 90 triangle. So let's just say, let's do a nice 3, 4, 5 as a nice example. Good Pythagorean triple. And let's say I want to know angle A. I mean, right now I know all 3 sides. I can do whatever trig ratio, but let's just do sine. So if I have angle A, the sine is 3 over 5. I know that ratio, but I don't know the angle. So let's write that. So the sine of angle A is 3/5. Great. So I set up my equation, but how do I figure out the angle? And remember, inverse functions are when we switch the role of x and y. So when I do sine, I'm expecting an angle, and then the answer is this ratio. But when I know the ratio but don't know the angle, that's the switching over, that's inverse. So outside of code, I might even use this inverse sine notion to show that it's an inverse of 3/5. And that works, and a lot of calculators have that notation. But the other word for that is arcsine. And we can write it as arcsine of 3/5 equals A. So that's, the other word for that function, arcsine, which is the inverse sine. I know the ratio, and then I'm expecting an angle. Oh, and actually all these are going to be capital A because it's the angle that I don't know. And then we'll see in the code that it's actually going to be, math.asine. But we'll get to that. So you see, you want to know, on the board or on paper how to set this up, but then we're going to take that and we're going to write code to do all this, because at any point you will be breaking out the calculator or writing code to get to these, yes, you want to remember these ratios. You want to remember how to set it up. You're not, and certain values you might remember, but of all these different, you're not expected to remember, the arcsine of 3/5 or something like that. So you're always going to be, at that point, you'll be breaking out the calculator or writing code. So let's take a look at how to do all this in code and, set it up so that you can plug in what you know and quickly output the answer. So let's take a look at that code.
But right now, everything that we're doing in trig depends on C being a right angle. So that's something that we would already know. If we don't know that, then it's a different situation. So I have my angles, capital A, B, and C. A and B are complementary because C is 90. And then my sides across, adjacent and however. So, we see the naming convention. And it's helpful then to picture this triangle. Even though as some of these angles get bigger or smaller, it's not necessarily drawn to scale. Someone famous said all models are wrong, but some of them are useful. And that's kind of what we want to get to here. This is useful that we can picture the relationship between the sides and the angles. So we can use, I broke this down into 3 parts here, finding sine, using sine to find angle measures. So what you would know is you would know the angle and you would know the opposite hypotenuse if you're using sine. So if you make the unknown value 0, now for all these, I'm going to make it like a 3, 4, 5 triangle. And, something like that. So let's just say I know that the angle is like 57 degrees. And then I'm picturing side A, and I'm going to say that that's 3. Actually, that would be 4. And then hypotenuse, let's say I don't know. So I'll put that as a 0. And see, then that way, if it's something else, if it's the opposite side you don't know, then here we go. So if you can picture the equation that we were talking about, sine equals opposite over hypotenuse. So then if I didn't know the hypotenuse, then I have 2 steps of algebra. So the unknown x equals the opposite divided by the sine. And if I did know the hypotenuse, let's say I knew that, and it was the opposite side that I didn't know, then it really just would be, my hypotenuse, opposite over hypotenuse, that's the denominator. So hypotenuse times the sine would be my unknown angle. All right, So there we go. That we have these two ways. So if I had, this is 5, 57, that works. And notice each time, what would be the unknown, and then it will be the answer. So then we're going to print the unknown is answer. And we'll see how this goes. And there we go. So again, I'm rounding this as just an example that you see that this answer is reasonable. Yep, we would know the opposite side, or if I knew the opposite side was something like 4 and hypotenuse I don't know, I could run it there. And yep. So again, a 3, 4, 5 triangle, the angle would be like, not exactly 57. So we get the idea here. Or if, we could have it as the, different angle. All right, so same thing with cosine. Cosine, adjacent over hypotenuse. So if it's the adjacent side we don't know, multiply both sides by hypotenuse, and we get this. If it's a hypotenuse I don't know, then 2 steps of algebra, and I get adjacent divided by math cosine. So similar idea. So, let's just say, there we go, 57. And if it's the adjacent that I don't know and the hypotenuse, then there we go. Because then that would round, the adjacent side would be 3, and, that would round. But again, the angle wouldn't be exactly, for a 3, 4, 5 triangle, the angle would not be exactly 57. Just using these round numbers to show you how this would work. And let's say if I knew that that was 3, but the hypotenuse I didn't know. So you see our 2 if statements. And, we get to that. And same thing with tangent. Angle, hypotenuse, or opposite and adjacent, if it's tangent that I want to use. So I would do the same thing. Which one, did I not know? Now, supposing that it's the angle that I don't know. So I have this, that we have the sides, A, B, and C. And there we go. So if I don't know this, now notice I'm not solving for this. I could just throw Pythagorean, again, this all works if it's a right triangle. So given that, I could do Pythagorean theorem also and figure out the unknown side. But I just want to take this, whatever side I don't know, I just want to kind of factor that out. So if I don't know A, then I'm just going to use B and C. So arc cosine of B over C equals angle A. So, if we picture that like we were talking about on the whiteboard, if I don't know angle A, then it's, arc cosine of B over C. Or if I don't know side A, I'm just going to not worry about that. I can figure out angle A, arc cosine of B over C, and then what I'm going to do is subtract, because once I figure out angle A, then just subtract to get angle B, and then I can print that out. So that's really what we're doing here, just 3 sides, and if there's one I don't know, I'm just not going to include that in my calculations, because I can do arc, sine, cosine, tangent to figure out the one angle, and then subtraction to figure out the other angle. There we go. Depending on what we don't know. So if I don't know B, then I'm just going to factor that out. So that would be sine, arc sine, using A and C to figure out that angle. Or if I don't know C, then it'd be tangent, because I wouldn't know C, the hypotenuse, so I must do opposite over adjacent. And we're going to put this together. It does seem like this is a lot of different formulas, and we're going to add a couple more and then put it all together to be able to take input, anything, or about a triangle. Our eventual goal is, you see 3 sides, 3 angles, that's 6 things, that if you know any 3 of them, you can solve everything for the triangle. That's what we're building up to. So we'll get to the next thing.
So let's talk about radians. And a radian, as we mentioned before, we could measure angles in degrees or radians. So what is a radian? A radian is the measure of the radius along the circumference. Because remember, the circumference of a circle is 2 pi times the radius. So the measure of the radius, pi is 3.14, twice that is 6.28. So if I measure the radius, I could get that around the circle, about 6 times. Not drawn to scale, but we see, 1, 2, 3, 4, 5, 6, and then we pretend that's only 0.28, not drawn to scale. So if I measure the measure of the radius along the circumference, but then this angle that opens up to that is 1 radian. So we're not talking about the radius, we're talking about a radian, and this angle is 1 radian. Degree-wise, it's like 50-something degrees. And why do we use radians instead of degrees? Well, degrees, it's nice, carry over from the ancient Babylonians. They like things base 6 and 60. It works out for a lot of things. But in a lot of applications, there's no real reason to use that number. Whereas radians, it's always proportional to the radius. And so however big or small my circle is, if I'm talking about radians, it's going to be proportional and then therefore relevant to some other things we're doing. So we get into some physics applications and such. By default, that's usually going to be radians. But sometimes we just, people not using those applications might just reference, degrees. So we want to be able to convert between the two. And given this, radians, that 2 pi radians is the whole circle. So if I have 360 degrees, then that matches up to 2 pi radians. And I can set up a proportion. So as long as I have degrees on the top and radians on the bottom, like I have over here, then if I know one, I can figure out the other. So if I have 60 degrees, and I don't know how many radians that is, I can cross multiply. So 60 times 2 pi is 120 pi divided by 360. And so that'd be 120 pi divided by 360. And then that cancels to nice pi over 3. And most of the time, we're going to have radians as some fraction involving pi. So if you just come across an angle, and nothing told you whether it's degrees or radians, if it's some fraction involving pi, probably radians. If it's a larger number and possibly a decimal involved, then that's going to be degrees. So we can convert from degrees to radians. And we know Python has that built in already. You can have this function, degrees. Input the radians, it'll output degrees, radians, vice versa. So this is just showing you that, first of all, what's it doing behind the scenes, proportions, and then also if there's some other application you just want to convert, you can do that. All right, so this is degrees to radians, but if I go the other way, and remember radians might already have, let's say I have pi over 2. So that might be how radians show up. Again, some fraction involving radians, involving pi. So how can I figure out degrees? Cross multiply. Pi over 2 times 360, and then divided by 2 pi. So I'll do some simplifying there. Pi over 2, so that becomes 180 pi, because I'll do that dividing by 2. And then divided by 2 pi. and we see converting radians to degrees, then pi will cancel out. Whereas degrees to radians, you're going to get pi in your answer. Pi cancels out here. 180 divided by 2 is 90 degrees. And pi over 2 that radians is 90 degrees. So we see how we can convert one to the other. We see that we have radians as a really good measure because it's proportional, and different ways we can convert built-in Python functions as well as setting up a proportion. Depending on the situation, one might be more useful than the other. So let's take a look at the code and see how we can do this.
So first of all, as we were talking about, this is the ratio. 2 pi radians is the same as 360 degrees. So we set up our proportion. Then as long as you have radians over degrees, you know one, you can figure out the other, and we're going to cross multiply. So we just picture that as we set up our code to do the cross multiplying. So here, I'm going to say, and put it in the comments, and a radians omitting pi, because remember, radians will have pi. It's by default, we're going to write it as a fraction involving pi, or integer involving pi if necessary. So we have radians which will have pi, but then we cross multiply, and then when we divide by 2 pi, pi cancels out. So omitting pi, I'll put that in the answer. So whatever the radians times 360 divided by 2 pi. And I'm just looking at this and seeing how pi cancels out, and it's 360 divided by 2 every time. So I'm just going to say the radians to degrees. If I know my radians, then multiply by 360 divided by 2 is the same as times 180. And pi, I'm not going to put it there for radians, and then I will reference it in the answer. So if I have pi over 2 radians, I'll just enter that as 1/2. You can use fractions or decimals in this, but really radians be expected to be a fraction. So pi over 2 would be 1/2, and then I'm going to print out pi radians equals 90 degrees. True statement. And we can even do our improper fractions. We can have 1/2, remember on the fourths, so we could have, anything, 3/2. Let's do something over the fourths. And there you go, 5 over 4, in different quadrants. And still, it's 5 pi over 4. I'll write that as the fraction and convert it. Now, this will always give this part. I know that it was 5 over 4, but this display will be decimals, and that's fine for now. Yes, equals 225 degrees. And degrees, whatever the answer is, decimals are fine for degrees. So there we go, converting radians to degrees. Just do that. Now, converting degrees to radians, notice if I know degrees, times 2 pi divided by 360. And you see, degrees won't have pi, but when I do that cross multiplying, I now am including pi, times 2 pi. But then divided by 360, so times 2 divided by 360 is really divided by 180, and I'm also going to add pi in there manually. So, because I do want a fraction in my answer here, then I have to do some other acrobatics. Python has this nice built-in fraction module, so fraction library. So we take a look. So if I have my degrees, let's say 120, interesting because it's in another quadrant. So not everything in the first quadrant. So if I have my radians, now we would think we're done here. Oh, okay. Math.radians, which is the same we can do that with degrees too, math.degrees. But remember, I didn't use math.degrees here because I really wanted to not have radians as a decimal. I would have to, it would not 5/4 pi, that wouldn't work. I'd have to, that number times 3.14, even go into a few more decimal places. This is the normal way that we would expect the input. So math.degrees, I really would need to already have converted radians to a decimal. So that's why I didn't use that there. But I wanted to show this here, that degrees, oh, okay, I can use math.radians. That's great. But guess what? That's not the end of the story, because math.radians will give me a decimal answer for radians, and that's not what I want. So here's some things. If I convert that to a string, and if I do this, then if I do R2 divided by, so convert this to a string, and then this fraction to a string, and then I have this nice function limit denominator, because that won't always be necessary, but I picked a number here to illustrate that, because 120 degrees, it's going to be 2/3, which would be a repeating 6, and there's all kinds of, that could get into a mess. But now I have this degrees equals this number of pi radians. So if I do that, it will give me 120 degrees equals 2/3 pi radians. So we see just a straight conversion. In other things, if I'm converting it, behind the scenes, yeah, to degrees to radians, it works out, and I don't see all those long decimal numbers. That's, if I wasn't trying to output something, that might be a good way to do it. Yeah, math.radians, math.degrees. But when I do want to output this conversion, this is how we would do it. We get these few lines of acrobatics. So that's why I just made my different steps: R, R2, R3. Convert it to radians. Oh, but we're not done. Convert that to a string and dividing it by pi, because I want that fraction. And then take that string, convert that to a fraction, limiting the denominator. And those are our steps for converting degrees to radians and radians to degrees in ways that I want to display it.
This is the unit circle, and unit because it's one unit that we're really zoomed in on the graph here. So there's still 0, 0, but this is just 1, and then 1 in every direction, even down here. But I wanted to focus on this. We're going to talk about that part. But that's why it's the unit circle, because I have a radius of 1, if we could zoom in on the graph like that. And what makes this so useful, and most things in trig are based on the unit circle, because if I have 1 in every direction, that means the radius is 1. So let's talk about this. If I have an angle here, and I'll call this central angle A, so what's the sine of A? So the sine of A equals y over 1. Over 1, I don't have to write that. The sine of A equals the y value. And then the cosine of A equals x over 1. So every xy point along the unit circle, based on this central angle, every xy point, the x value is the cosine and the y value is the sine. And that's where we get our trig ratios from, the unit circle. So then I have all this sine, cosine, and then of course then tangent is y over x, because it's sine over and it's y over x, the y value over the x value, or the sine over the cosine. And that works out. I have all these different values. So here, cosine, remember that starts at 0, and then we go around this way. So the cosine of 0 is 1, and the sine of 0 is 0. And then we get up to here, so this would be 90 degrees or pi over 2 radians. Then the cosine is 0 and the sine is 1. And every angle, whether it be degrees or radians, all along the unit circle, we have this value for the sine or the cosine. And then we get our Pythagorean identities because we remember Pythagorean theorem, x squared plus y squared equals r squared. And then therefore cosine squared plus sine squared equals 1. Pretty cool. So there's, and then all of these, then it works out nicely if you're in this other quadrant for certain things that you might remember. Notice for the y values, this would be symmetrical. So if I'm at different points along each side, in different quadrants, I could have symmetrical points here, but the difference is the sign because you're in this quadrant, the x value would be negative. Or, in this quadrant, then it'd be kind of symmetrical about the x-axis, but then the y value would be negative, or here both of them would be negative. So, we have some patterns here. Now, there's most of the trig values you don't need to know, but certain ones we tend to remember because they work out to this nice pattern. And so let me take a look at this. If we have, I'll remove our triangle. So we know that exists. But what about some of these key values here? So if I have, if this one is 30 degrees, 45, 60, and then up here would be 90, and then down here would be 0 degrees, or 0 radians. And then if I have these as radians, so 30 degrees, so then that's pi over 6, 45, that's pi over 4, 60, that's pi over 3, and then 90, that's pi over 2. So for these angles, it actually is worth it to remember these because it works out to this nice pattern. And I'm going to start this pattern by changing this. Yes, that's still 1, 0, but supposing I wrote this as, and I'll erase this one too. So supposing I wrote this instead of 1, I'm going to write this as the square root of 4 over 2. So square root of 4 is 2, divided by 2 is 1. That's still 1. But if I write it like that, for these angles, then the pattern is the x value in this one is the square root of 3 over 2. And the x value here is the square root of 2 over 2. And the x value here is the square root of 1 over 2. Again, if I don't simplify it, then we see the pattern. And then here, it would be the square root of 0 over 2. I'm going to erase that part. So the x value does decrease as we go around, but these particular angles, it works out to these nice patterns here. Square root of 4, 3, 2, 1, 0 over 2. Pretty cool. And then the y value does the exact opposite. So the y value here is 0, and I'll write that as the square root of 0 over 2. And then the y value increases as we go up. So that becomes the square root of 1 over 2. That becomes the square root of 2 over 2. That becomes square root of 3 over 2. And square root of 4 over 2. So given these, we are going to look at the code and how to write code to get all these, and that's going to especially help for all these in-between angles. But certain major angles, you can figure this out, and even though we're writing code, we still want to be able to work out some stuff in our head. And looking at that, then given this quadrant, you can say, oh, well, what angle am I talking about? And just picture, oh, if I want cosine, that's the x. And so I just count 4, 3, 2, 1, 0, which angle am I talking about? Or if I want sine, that's the y value, 0, 1, 2, 3, 4, and which angle. And like I said, they correspond to the other angles because if I was in this quadrant, I'll just pick one of them here. So if that's 60, so 90 minus 30 is 90 plus 30. So that would be 120 degrees. Or if that would be pi over 3, then that would be 2 pi over 3 radians. And it's symmetrical here, so the values are the same, but I'm in this quadrant, so the x value is negative. So we see, remembering them in this quadrant, then we can see that the symmetry here, but the x value is negative because I'm over here. And then the y value would be the same. So 45 and then, or pi over 4 is the same as 135. So 1 pi over 4, 2 pi, 3 pi over 4. And we see same values, but the x value would be negative. Nice and symmetrical here. 0, and then remember in radians, then this is 180 or pi radians. So if we get huge numbers, then we can count like how many multiples of pi. 2 pi brings us around full circle, and 3 pi would be the same. The beauty of these trig values is that they're repeating functions. We can just keep going around the circle. And again, things we can write the code for this, and we can look at those patterns, and we definitely will do that. But it's also good to see this beyond the code and see how it all fits together. Because a lot of times you won't see it written like this, but if you picture it like this, it's easy to remember. And then all the nice symmetry. So this is one of the many great things about the unit circle, that all of our trig values come from this. There we go. Sine is your y value, cosine is your x value, tangent is y over x. And then, all these nice patterns for those particular angles. And, we'll look at some other interesting patterns here. But just to see, here's what the unit circle is. And let's talk about, different ways we can create this with code and see this on the graph. So let's take a look at the code.
So here's the unit circle in code. And besides the fact that this is going to look a whole lot better than my drawing, just to show you how you can represent a circle. We've been graphing some things, but you can also graph a circle if you want. And this graphing should seem familiar. Notice I just made the axis 1.5 in every direction. So really it's, we're zoomed in on that part of the graph. Only one unit in every direction, hence why it's the unit circle. And we have, each axis and this. And so I'm going to save this as circle, which I don't necessarily need to do, but I'll do this because it'll still run this code, which is plt.circle. Okay, I can plot a circle. You don't need this extra space, but you can have it if you want. And this is what we have here. 0, 0, that's where it starts, the coordinates of the center. Radius is 1, and ours, I'm going to do fill equals false because I'm going to do some other stuff with this. And the reason I added this is because then down here, I can add artist circle. So we're going to use this for unit circle, but you can use this for other shapes. And this connects with some of the other things, if you've done other, drawing in Python for, different things, I can save that. Here's my circle, and I add the artist. I also am going to add this set aspect equals. Most of the time that wasn't an issue because, I'm graphing something and you might notice that the x-axis is extended a little bit and our coordinates are more rectangular. But for the unit circle, I want this to be equal so that you actually see it as a circle and not an oval. So as we run this, and the suspense here, this is our unit circle. So we see it is 1 in every direction. The radius is 1, starts at 0, 0. And this is where all the trig values come from, as we were talking about. That, and I'm going to show you what that means. But this is our unit circle. And what does that mean? It means in the circle we have triangles. So here I'm just going to redo this. All my circle, include this. There we go. But here's the triangle that I'm going to put. So, a equals 1. We'll get to that. But notice I'm going to have, there's my angle. But we're not worried about that right now. Math.cosine of A, math.sine of A. Remember, the default is radians. So 1 radian, that's, a decent angle to illustrate our point. So notice the cosine, I'm going to store it as x, and the sine, I'm going to store it as y. And after all this, now here's some text I put. You'll see that where this shows up in the graph, text to display. But what I'm also going to do is I have the plots here and these other lines that I'm drawing. So now that I have my x values and y values, I'm going to draw some lines, put some text on the graph, and here we have it. So this is our unit circle with a triangle. Now notice the hypotenuse of this triangle is still the radius, which is 1. And that works out nicely. Given this central angle, it's our rectangular coordinates. So if I plot this point, x, y, how do I plot the point? Go from 0, 0 over x, up y. And that makes the sides of my triangle rectangular coordinates. So we know that this angle is a right angle. And if we remember everything then, we notice that we can do trig here because my cosine is adjacent over hypotenuse, x over 1, which is really just x. And my sine is y over 1, which is y. So whatever this angle is, this central angle is inside the triangle, then my cosine is my x value, my sine is my y value. So if when we were doing before the just displaying the decimal numbers for sine and cosine, that is going to be our x and y values all along this unit circle. So, that's where they come from, and here's the triangle inside, so we can see this visually. And I did one more thing for you to animate this. And the animation's pretty interesting. All the other things, and I'm going to import time. But here's the triangles. Now, notice this is all in a function here. So I have it, I think this animation works. Sleep for 0.3 of a second, clear the output, and then clear the output, and then I'm going to do all this, and in this loop, I just called it A. For A in range, 70, that ends up being enough. So A is my, my counting variable. So this is still in radians, so I just did 0.1 times A. That ends up being enough of a difference. So my angle, when A is 1, it's 0.1 radians. When A is 2, it's 0.2 radians. And again, you'll see that ends up being enough of a difference in the angle. So based on this loop that counts through variable A, I'm going to have these different angles. And then cosine and sine are my x and y values. So going through this loop, I'm doing all the same things I just did in the cell before, but this loop is counting through, plotting that triangle, and then, wait, 0.3 of a second, clear it, and plot the next one. So you can see as this central angle increases, we can just see these adjusting. Then you have your x, y, and this still works for that angle for in all these different quadrants, because I can actually count the angle from 0, 0 in the first quadrant, along the x-axis in the first quadrant, or I can count other ways. Oh, keyboard interrupt, excuse me. So I can see this showing that I have the sine, and notice this angle keeps increasing. So it does go up through 2 pi radians, the entire circle, and it'll still draw those triangles. And you'll see that works out. When we're at one of those points in another triangle, the sine or cosine, there's when we do inverse sine, it actually works out for 2 possible angles. And we'll look at that. And again, the Pythagorean aspect, because given those triangles, sine squared plus cosine squared, because this equals 1, well, 1 squared, because of that triangle. And so I just put this little loop here to show this. Again, I'm just looping through. I'm not even graphing this, but given those angles, so the sine and then squared, cosine squared, and 1. So just to show you, we have the sine, and cosine squared gives us these huge decimal numbers, but look at that every time. And just the way Python calculating works out, every so often you get things like this, but it really is sine squared plus cosine squared equals 1. So we see how all this comes together now in this right triangle. You see, we have this in this triangle inside the unit circle. All of our x values and y values are points along the triangle for those given angles. And remember, at 3, if it were a clock at 3 o'clock, then this would be the angle 0. And we also saw that, at certain times it seems to close up and you wouldn't even be able to make a triangle. So now, as I mentioned, that this would be 3 o'clock. So the animated unit circle, what if I plotted this point here? So I plotted a line, and so what if I plotted from 0, 0 to xy? And what if I comment out all these? This is actually going to be useful for you in a project that's upcoming, just to show you. So we have this, and here's another trick. If I wanted to make this a clock, clocks go the other way. So what I would have to do is just make everything negative. And then if I ran this, you see? And we see this moving around. And as another bonus here, supposing I wanted to start it at 12 o'clock instead of what would be 3 o'clock, our normal trig starting point, then my angle, I really want to graph the angle that's that's before that. So I would make it minus, I would graph this as plus math dot. I want to do this exact, so I'm going to say math.pi over 2 instead of giving the decimal equivalent. And you see how this starts then at the top. And given these, you could have this tick any number of seconds. You can look at that. Okay, and just like I said, that might be helpful for you in an upcoming project. All right, and Pythagorean. There are other Pythagorean triples, but let's focus on this, that sine squared plus cosine squared equals 1. Often a useful thing to know. So let's take a look at how else we can graph these values, not just in a unit circle. And we'll see some other cool patterns here.
So let's talk about how we can graph these trig functions if I make x the angle and y the trig function. So unlike the unit circle, x and y are values on that, but if I just make x the angle, so, and I'm going to make it in radians. So if x is the angle, then our angle, we have 0, but in radians, I'm going to go to the major points, pi over 2, which corresponds to 90 degrees, pi, which is 180 degrees, and then, so 3 pi over 2, and then 2 pi, coming full circle. So we're going around the unit circle every 90, 0, pi over 2, pi, 3 pi over 2, we're going around. And if x is the angle, then let's just picture what's happening to the y value. If I do y equals the sine of x. So as that angle increases going around the circle, what happens? Remember, the sine of x starts at 0. So we do have this point. And then the sine being the y value on the unit circle, what's it doing? As we're going around a circle, it's going up, then down, then it's negative, and then back around. So at pi over 2, you see the y value really only goes 1 to negative 1. So at pi over 2, the sine is 1, and then at pi, it goes back to 0 again. And then going around the circle, 3 pi over 2, now it's down to negative 1. And then back up to 0 here. And I'm going to draw this with a nice curve to it to try to, estimate these in-between values. But that's a sine wave. And the name of this sine comes from the adjective sinuous, which means curvy, because that's what the graph looks like. It's this curve. And it continues forever in both directions. It just keeps going because as x increases, beyond 2 pi, you're going around the circle again. So it just goes around and around. And we get this up and down sine wave. So, and it works out well when we're doing this in radians, because degrees, that arbitrary number of 360, to get that full cycle, I would have to go from 0 to 360, but yet the y value only goes up and down, 1 to negative 1. So, if we did it proportionally, then you wouldn't even be able to see it on the graph. So that's sine. So what about cosine? I just did sine first. So if I take cosine, and I'm going to keep these same major angle values, but what happens with cosine? When I go at cosine at 0, it starts at 1. And then at 90 degrees or pi over 2, then it's 0. And then at pi, so remember we're going around, cosine is 1, 0, negative 1, and then, so 1, 0, down here it's negative 1 when we're at pi, and then goes back to 0, and then back up to 1. So again, I'll try to draw this with a nice curve to it, but there we go, 1, 0. And again, that also increases. And if we saw them, continuously, this continues. The sine, the cosine graph, they are very similar, but there's just a shift to them. And that's why when I have y equals the cosine, why we have because the graphs are similar, but there's a shift to them. And so that, sine because it's sinuous or curvy, and cosine because it's like that, but it goes along with it, but there's a shift to it. So we have sine and cosine. And being familiar with the graph, we can, plot out a few of the key points and then sketch it out in between. We'll also show how to do this in code, built with the built-in functions, or even with, one point at a time. So that's pretty interesting. So we have sine and cosine. Let's do one more here. Let's talk about tangent, because tangent is sine over cosine, but if we remember, that's going to cause some problems, because cosine is 0 sometimes. So if tangent is sine over cosine, so what happens? What happens at 90 degrees? Well, first of all, if it's sine over cosine, then when sine is 0, then the value is 0. But then when cosine is 0, I can't divide by 0. So what we would do is I'd put a vertical line, dotted line there. That's our asymptote. It's that x value can't exist, so therefore there's no possible way for any y value to be along that. And then if we go at pi, so sine is 0, yeah, x is negative, but the sine is 0, so then that value exists. And 3 pi over 2, x is 0, so undefined. And then at 2 pi, it's 0. Now, just knowing that information is not enough to know the tangent graph, but I'll tell you, what does it do? It actually ends up looking like spaghetti. So that's what the tangent graph looks like. And if we continued it on, it would be like this. So tangent graph. And most of the time we won't see these dotted lines. That's just, if we were drawing this, that's our guide. You'll just notice that, hey, there's that x value, that there is nothing. And then it gets, tangent can approach this, but never get there. Now, at least for the 90 degree, then, or pi over 2, that makes sense inside a circle, because if that, or inside a triangle, because if the triangle, I'm just going to draw this here. If I have a triangle, so, A, B, C. So if that angle gets to be, if that angle is 0, then we're at 0. And as that angle increases, the tangent would increase, B over A, because that would keep increasing. But it can't be 90, because then I wouldn't have a triangle. So, for that part, it also makes sense, looking at that comparison. But for the graph, it definitely goes back to, the explanation is sine over cosine. And again, let's take a look at how to do this with code, and, a couple different ways, from a loop and plotting points to some of the built-in functions to graph this. All right, so let's take a look at the code.
So now let's graph the trig functions, not as a part of the unit circle, though I want to start with this and just keep that as a reference here. So here I'm just going to recreate the unit circle, in this case using degrees. So I'm going to recreate it using points. So I'm going to loop through this here, where, from A for the angle in range 360, I'm going to loop through, and each one, remember, sine and cosine, I have to convert it to radians, and then I'm going to plot this. So, that works. There's my unit circle. I didn't put the axis, each axis, but there we go. We can draw our circle. As again, another way to draw a circle, you can plot all these points. So I did that with degrees, because now let's take this as, so A, which is the angle, if that's my x value, and then my y value, I'm going to start with sine. My y value is the sine, so the sine of A. And I made this axis here. This is going to, look silly, but it, now it's all equal. X goes from 0 to 360. Y goes from negative 360 to positive 360. And when I graph this, this is what it looks like when it's equal axes. Because remember, the sine only goes up to 1 and down to -1. So if I use degrees, it's so stretched out. And we can make this, I'll make it like -2 or something so we can see, the edge of the graph. So we can just completely change this aspect ratio. And I still have x going up to 360 and y just going up, to 1 and down to -1. That works. And, that illustrates that we can do this. But beyond that, it's still, radians are nice because they're proportional. It's the measure, that angle corresponds to the measure of the radius on the circumference. Whereas 360, really, that's kind of an arbitrary number, we came up with. I think it goes back to the ancient Sumerians. So many things they did were based on 6 and triangles. So that's where we get 360 and, dividing things up that way. So how do we do it using radians? So again, I just go back to the circle. Rather than just drawing the circle as we were doing before, we can just, plot x and y as points. And that works. And it still looks like so many individual points. That's what I wanted. But, plot even more points and it'll definitely look like a smooth circle. So we can plot those where, radians and then, x and y. So then if I was graphing this, again, my range for radians, I want it to go all the way around, but I want to give enough different values. So I want maybe 70 points. And so the radians, 2 pi radians for the circumference. So that's 2 times 3.14, 6.28. And so each time, for A, then we go up, it will count up these, tiny increments and end up at 7, and that will work out. So x is the angle that will increment enough for us to see our graph, and y is our sine of that angle. So now we really see, a nice illustration of our sine wave, where our ratios, you see, I can have this normal 1 to 7, and even if I had the y value go up to 7, it would look a little more zoomed out, but you would definitely recognize the sine wave. So all of our trig graphs are going to use radians. It just makes more sense. So there we have it. Sine using radians. And I absolutely could do the other thing, do this with cosine too. I'm going to show you this in the next step. But I could just as easily do sine and cosine. But rather than the points, I'm going to use this to start using NumPy, because we were using NumPy before in the algebra with Python. That's a good go-to because NumPy, it creates this array of array of values, which in this case I'm going to use as x values. So that way I can base this all on my graph dimensions, which I can change here if I want. I can just define it x min, x max, y min, y max. And then I create how many points do I want based on those graph dimensions. And if I want more points, this is going to be enough for us 4 times this, but I could always add 5, make this, increment that number 4. And then I create this np.linspace, min, max, and then how many points in that range. So I create this array. And for so many of our functions, that's just going to be a go-to. Create this x array, or this np.linspace array of x values. And then we're going to use that to plot everything. And then I can define this. Hopefully this is looking familiar. If you did the Algebra with Python course, then my plots, and, my axis, and then I'm going to draw the X and Y axis. Still making them blue. I just kind of like blue. So there we go. np.sine. And now I have this and I can graph this, you know, there we go, np.sine. And you might notice, this should have a nice curve to it, and you might notice some, you know, not perfectly curved aspect. So that's where I can say, well, more points would smooth that out. So even if I just increment that to 5, that might be enough. Smooths it out a little bit. You see? And I could certainly increment that to 10. Takes a second longer, and you see how that really smooths it out. So that's where using that np.linspace helps. A lot of these things we're going to be dealing with, you know, very curvy lines. I mean, that's really why it's called sine, because the adjective is sinuous, which means curvy. And, you know, that's our sine wave. And this is usually the go-to for modeling a lot of up and down trends. We're going to get into some of that. But then also, you know, anything curved, because it starts at 0, 0. And now we're going to look at cosine. You know, why is it called cosine? So I'm just going to model this one, and I'm going to comment out sine here. So cosine looks very similar, but notice it starts at 1. And if you remember the unit circle, because at 0, you know, when the angle is 0, the sine, the y value is 0, but the cosine was 1, the x value. So very similar graph, but it just starts at a different place. You could use this, a lot of times modeling something with cosine would be like a spring that already is stretched out. So that's why it starts at 1. But sine, you know, starting at 0, 0 just works out for a lot of things. So that's why we model so much with sine. And we see cosine is named that because the graph is similar. All right. And next we'll get into tangent in the next one. Actually, let's do tangent now. Just tangent. And remember, tangent is y over x. So in our unit circle, it's the opposite over the hypotenuse, which is y over x. And so if I look at these, I'm just going to graph tangent. I'm actually not going to, I have other things down here, but we'll get to that. If I just graph tangent, spaghetti. And we also notice that, you know, it starts at 0, 0, because when y is 0, then we're at 0. And we have these jumps in the spaghetti because it's y over x. So at 90 degrees, or pi over 2 radians, x is 0, which 0 in the denominator makes it undefined. So I have a vertical asymptote here, no, you know, undefined. And then we keep going. There we go. So we see the spaghetti. Not a lot of things that we can model with tangent graphs, but it's definitely, it's interesting. So there we go. And in the next thing, we're going to look at all these other trig functions and other graphs. But for now, you know, taking a look at the sine and cosine graphs and how we can use it, how we can do that with NumPy.
So here's a look at all 6 trig functions. And it all comes back to a triangle like this, with right angles, that if I have the angle here, then this would be the adjacent side, this would be the opposite side, this would be the hypotenuse, just as a reference. So if we have sine, then that's opposite over hypotenuse. And if we're in the unit circle, then that would be the y value, because y would be the opposite from the central angle, and the radius would be 1. Cosine, adjacent over hypotenuse, and in the unit circle, that'd be the x value, the horizontal over radius of 1. Tangent, opposite over adjacent, and in the unit circle, that'd be y over x. And another way to do this, because sometimes this is useful, it's sine over cosine. Then, now we get into the reciprocal functions, tangent and cotangent. So, tangents opposite over adjacent, cotangents adjacent over opposite. Or another way to write that is 1 over the tangent. That works out. Secant is the inverse of cosine. So instead of adjacent over hypotenuse, it's hypotenuse over adjacent. Or sometimes it's useful to see that it's 1 over cosine. And then cosecant, the inverse, so it's hypotenuse over opposite, or again, I can write it 1 over sine. Now, we'll look at the graphs. The as we talked about with sine and cosine, the co-functions are named that way because the graphs are similar. And then the reciprocal functions, so they're not named co because of the reciprocal, they're named because the graphs are similar. So tangent and cotangent, spaghetti but different. And we'll look at secant and cosecant. But I always remember them in this order: sine, cosine, tangent, cotangent, and then secant, cosecant. So to think about remembering the reciprocal functions, tangent and cotangent are reciprocal, and then cosine and secant are reciprocal, and then sine and cosecant are reciprocal. So remembering this way, sometimes that visual helps to remember, what the reciprocal functions are. And when we see that, when we see the graph, we'll see how secant and cosecant match up with sine and cosine. So just a good overview of all this before we get into the code, how all this fits together, the reciprocal functions, and how they're all these 6 trig functions are related to each other. We often don't use these because for a lot of triangle applications, sine and cosine and tangent work. Like if I have this, I don't also need the reciprocal to solve certain problems. But it's good to see all of these together. And again, the big picture as we get into the code and see what these functions look like and what the graphs look like. So let's take a look at the code.
So we have our graph dimensions as we were doing before, and tangent. So mentioned before, tangent, np.tangent, and this line of code, why I put this in there, so that tangent will always be this spaghetti because it's y over x, and then that's always going to work out to be a positive slope, and it looks like this. And then it's y over x, so every so often the x value will be 0, and that makes it undefined. And so that's why we have these breaks here. And so that the Python graph doesn't display that as like a vertical line, which is not really a part of the graph, I have this, that if that slope is always, that difference is always going to be positive. So if it's ever less than 0, I'm going to take that as not a number, and then therefore it won't graph it. So this line of code just makes the graph look better by eliminating those undefined points. And that's tangent. But what about cotangent? So it's so we expect that the graph's going to be similar, and it's a reciprocal function. So I don't need a tangent button on the calculator. Most calculators won't have that because of this reason. I can just put 1 over tangent is cotangent, and that works. And being 1 over, I'm still going to include this line, and it's just different because I have to make it, if it's greater than if that difference is greater than 0, then make it not a number. I'm not going to put these on the same graph, so I'm going to comment this out. And let's take a look at cotangent. So we remember tangent here, and then we have the graph of cotangent. So we see the slope is negative each time, very steep still, but negative each time, and shifted a little bit. Tangent graph did go through 0, 0, and cotangent doesn't. Because as the reciprocal, yes, it's 1 over tangent, but that also means it's x over y instead of y over x. So x over y, now it's undefined when y is 0 at these points. So that's the tangent and cotangent graph. Interesting. We don't use them a lot for modeling things, but we see these graphs. All right. Our next major grouping is secant, and secant does also have a co-graph, cosecant. We're going to start with secant though, and there's a reason why I mentioned secant and cosine in the same breath. As we were talking about, they are reciprocals. So 1 over cosine is secant. That's just how we're going to do it. And then we have this, and it just works out this way. Sometimes you arrive at this by tinkering a little bit, that if the difference is greater than 2, then I'm going to make it not a number. That still gives me a good graph. Sometimes, I found 2 works. More or less than that, it doesn't. It kind of distorts the secant graph. So there we go. I'm just going to graph this secant, and we'll take a look and see what interesting things this looks like. So look at that, parabolas, but you see it kind of alternates, parabola up, parabola down, up, down, up, down. All right, there we go. And you see, our values here. So at 0, 0, when the cosine is 1, there's secant, and then we start, when the cosine is 0, then it's undefined. You can imagine like vertical dotted lines there for these values that don't exist. So that's cosecant, that's secant, but now I actually want to graph this along with the cosine graph. So there we go. So I'm going to graph this along with cosine, which means I'm going to uncomment this. All right, and graphing these reciprocal functions, secant and cosine, we see how it matches up. So you see, look at that. It just looks kind of cool. And you see when it is 1, when cosine's 1, 1 over 1 is still 1, so they'd be the same value. And when cosine's 0, that's when secant would be undefined. There we go. Pretty cool. And cosecant now, so remember we were saying that's the inverse of sine. The inverse of sine. So if I comment this out, and we'll take a look at this. So just as we expect, just as we know that the sine and cosine graphs are similar, secant and cosecant would be similar to each other. I'm only going to show one of it for now. And so just graphing the secant graph, and you see this is what would happen if I don't have the right thing. It graphs that vertical line. So when I uncomment that to remove those values, then the graph looks much better. And this is the true secant graph. That vertical line just wants to connect, the Python graphing wants to connect it, but that line is not a part of the graph. So that's the true secant graph, cosecant graph here. And just like the other one, comparing it with sine. So cosecant is 1 over sine. So if I compare that with sine, we're going to see that pattern also. And there we go, sine starting at 0, 0, making cosecant undefined, and then 1, they're the same. So pretty cool. So now we have all of now you're familiar with all of the trig functions. So truly there are 6 trig functions. And we see that you can imagine that there's not a lot of applications for the graphs of cosecant and secant, think of something that moves along, that particular trend, some sort of parabola, then an opposite parabola, not necessarily. But, they're there, they're useful, they're interesting. And, we also see tangent and cotangent. Not a lot of applications, but, we could have some. And so it comes back to modeling a lot of behavior, still comes back to sine. And, even if I was doing something with, secant, or then I still might, or cosecant, I still might, go back to sine because it's the reciprocal. But it's still, there are the 6 trig functions, but we see why, it's still all of them based on those x and y values from the unit circle. And so just going directly to them, the sine and cosine, that ends up being the most useful. And we have all of these. We'll get to transformations next, things we can do to change these graphs. But for now, these are the 6 trig functions and what their graphs look like.
Let's talk about how we can change the graph of sine. Now, we can apply transformations to any of the trig functions, but the sine wave is really the one that we apply it to most of the time. Number one, because that up and down pattern is a common pattern. The other ones don't seem to show up in a lot of applications. Also, sine, let's say compared to cosine, the fact that it starts at 0, 0, again, a more common pattern that we see. So we apply to a lot of transformations on the sine wave. So I put the regular sine wave here as a comparison. So what can we do to transform? Well, I can change the amplitude. So I can make it y equals, let's say, 2 times the sine of x. And so, working with radians, x is the angle in radians, the y value is the sine ratio. So if I have a multiplier of 2, so what that does is that changes the amplitude and it goes up to 2 now and down to -2. Now notice that the zeros still stay the same, because if it's 0, multiplying by 2 is going to still keep it at 0. But that's one of the things it does. This becomes the amplitude, and whatever multiplier goes up and down. So that's a pretty good transformation. If I was applying this to, let's say, sound, the amplitude would be the volume. Other times, just whatever we might be modeling, the amplitude might change. Not everything goes up and down the same, just only up to 1. So one of the other transformations we can do is, supposing I have the sine of, instead of x, I'm going to call it 2x. And I'm putting just number 2 in here, easier for me to draw. We're going to get into the code and you're going to see how you can apply sliders and really tinker with a few of these and see what the results are. But for now, to illustrate the point, so if it's 2, so if I have the sine of x, then multiplying by 2 here makes it go through that whole cycle twice as quickly. So the sine of 2x, instead of taking 2 pi to go down, that's the end point here. Instead of taking 2 pi, it's going to do that twice as quickly. So instead of just going up and down, it's going to go like this. Oh, it actually would not change the amplitude though. So it's going to go, up and then down like this, and then down and then back up. So notice the whole cycle happened here, and then we're going to go through that again the second time here. Hopefully my drawing isn't too bad. So these are the things, a multiplier in there. So for A, amplitude we can call it A. For the multiplier in here we can call it B. So the period, if this is b, so the sine of bx, so the period is always 2 pi divided by b. So without a number there, it's 2 pi, and then if I have this here, so then the period is half of that, so it's pi. And we can get it smaller and smaller. If this was applied to sound, that multiplier would be frequency. So these potentially could get to be really high numbers. So we can take a look at that. Then one of the other transformations we can do, and my graph's getting crowded here, so I'll erase all of these and I'll start out with the basic sine graph again. So one of the other transformations, we can actually just put a horizontal shift on this. So there's my, let's say, pi over 2, pi, 3 pi over 2, and then that's 2 pi over here. So the normal sine graph, and there, it's going to work better with the code. There we go, somewhere like that. All right, that'll be the reference point. And if I have a phase shift, so if I have over here, y equals the sine of x minus, I'll make it a nice even pi over 2. So we see if I apply this phase shift x minus pi over 2, so that at every point it's graphing, it shifts it to the right, which seems counterintuitive because you're subtracting, but remember you're graphing what was pi over 2 before that. So instead of here, it's going to shift pi over 2, and then it's going to go like this, you see, and then down, and then it's going to continue like that. So that gives it the horizontal shift. And there we go. And we can shift it as much or as little as we want horizontally. So notice then if it was x plus pi over 2, it shifts the other way, which then would line this up at 1. So the sine of x plus pi over 2 would shift it the other way, and then that would equal the cosine of x. So remember, very similar graphs, but they're just shifted. So if we put that exact shift on there, then that would equal the cosine of x. So we have all these. We can also do a vertical shift that after all of this, it's the same shape of the graph and then just shifts it up. That's a pretty common shift, especially when because the sine value goes into the negative. So maybe if we're talking about tides or phases of the moon or something, we can apply a vertical shift so that it doesn't ever go below 0, or even that the minimum isn't 0, it might even be some other number. So we see all these different shifts here that I can apply an amplitude, or the change the period, or a horizontal shift. And then we can also have a vertical shift. But let's take a look at this in the code and we'll see the different things we can do, and then you can create this, and then you can add some sliders and tinker with this and see some of the effects. So let's take a look at this in the code.
I decided to do this with an interactive, which will create sliders. So with that, we need to import the interactive and math inline. So all these other things were things that we used before. Set up the graph dimensions here, and I decided to just give these minimum and maximum values. You'll see how that plays out. The points 10 times that, so 1/10, that should be pretty good. And here creating the x values. So remember linspace, creating the x values that we're going to use. And with that interactive, we're defining this function. I just decided to call it graph. And we're defining this function, which we're then going to pass these values from the interactive. And in this function, everything that I would do to graph the plot, subplots, and here, this is just, something here to display the graph that we're going to have on the plot. So I made these EQ and EQ2 to split out these strings really. You could actually have put them in here directly if you wanted to. That works just as well. And then the values A, B, and C. So I put this in the title. So F and then the single quote, we have A, EQ, B, EQ2, C. So these are all my variables. That's how you would display the variable without having extra quotes. Sometimes if you do it in a different way, it displays with quotes, looks different. So, taking these values that I have and I threw in 2 more string values, so I just put all them, that's going to be the heading for the graph, the title for the graph. And then down here we have the interactive, that's going to create our slider. So the interactive, and then I'm going to say, I'm going to run the graph function, and here's my sliders, A equals B equals C equals, and I give my ranges. That's probably a good range to illustrate what we want to illustrate here. So all of that, and then the last line of code is just, I called it IG, so it's just IG, and that's it. So when we run this, it's going to give us these 3 sliders here, and we see at the top, now when you first run it, everything's going to come in as 0, and your graph is just zeros out. But as soon as I have A is 1, well, that's still, sign of 0 is still 0, so that still zeros out. But if I have B is 1, now that's my normal sine wave. So, sine of X. And then C is the shift. So if I move C, we see that shifts it up. I can move it again. It'll display it here so you know what you're graphing. And we can move these down so we see the shift here. And A is the amplitude. Let's get this back to 0. I like that. So if I increase the amplitude, I get graphs like this. So remember, 0 is still 0, but the amplitude increases. And if this was something, a sound wave, the amplitude relates to the volume. And B increases increases the number of waves. If this was music, it would be increasing the frequency. Just the regular graph, we're saying it decreases the period of the graph. So we can have these. And you see I just increase it a little bit. That's enough to illustrate what we want. And we see, I made, 10 points for every integer. And as we start increasing the frequency like this, we start seeing it get a little bit choppy, not quite as smooth. This is still a nice smooth sine wave. So we see this, and then still we can always move that up or down. There we go. So creating the, we can see the shift, that first number, the multiplier, that's the amplitude, the default is 1, 0 would just zero everything out, that wouldn't accomplish anything. And the sign, so in this case, the sign of 2x, so that 2 represents, that's B, and increasing B decreases the period of the graph, or we could say that it increases the frequency. And C is the vertical shift. So we could change this, you could change these if you want, tinker with this, but you get to see what these different values do with your graph. So what if we have 2 waves and we're interacting? And again, I just picked sine waves. That illustrates our point. I have this. I'm not doing this as an interactive, so I just have the graph dimensions here, the plot information here, and just down here, I have changed these. I can go in and change these to whatever. We're going to run this first, and then we'll come back and change these. And then the last few things, just, plotting. One of them is a blue, one of them is green, and then the combination is red. So what do I have here? My first one, I'm graphing your normal sine wave. The second one, I'm graphing it with a shift. So other than multiplying something times x inside that sine function, if I add or subtract, that shifts it to the left or right. So it's the horizontal shift. And I'm just going to say minus math.pi. So when I have y3, which is the interaction of these two. So look, my one graph, my blue graph, is my sine wave. My green, it shifts it enough that it lines up perfectly to be exactly the opposite. And so the red line is the combination of two, and it zeroes out everywhere. So, this is really how also, thinking about sound frequencies, this is how noise canceling headphones work. And there's enough time to do all of this and still process the audio that it detects the waves and then generates the exact opposite, so that what you hear is this zeroed out sound. But what if I make it, if I make them both the same, that's not going to, well, actually it'd be really interesting here. You won't notice this in the red, in the blue, and the green. But if I make them exactly the same, you see, the blue and the green are on top of each other, so we can't see that. But the red, adding them, it increases and decreases. You see, not quite the same as just increasing the amplitude, but it adds them. So actually, it would be the same as increasing the amplitude, because 2 times sine. So if I have a little shift here, I'll say -3. So you see, not quite pi, and so it, quick glance, it looks like they kind of line up, but then this red line, adds it up a little bit. Now, supposing if I have, some shift like that, like 1, and what do we see? We see that as they get close, and look at this interaction, not the highest point for the blue or the green, but almost the highest for them, and then, in between, that is the highest combination. And so we see, now, this is what we have when we talk, if this was audio, this would be beats. If we have, different frequencies, and then when they line up, it magnifies them because it gets louder. So if we had this, if I just changed it to -2, and we see now this is where it would just be, we could call it dissonance. It doesn't line up. It's, we see the blue line, the green line, and then given that combination, then the highest value would be in between. And so it would just, if this was audio, it would just be all muddled together, because the highest point isn't really, lined up with anything. Now, here's one of the interesting things we can do. For the second one, I'm not going to do a shift. I'm going to have this one as 2 times that. So it's going to be a higher frequency. So we see the blue is our sine wave, the green is the higher frequency, and you see, again, we have the red line, the combination. The highest point is, not quite the highest point of both of them here, but, in between that. And then we get the lowest point, so we get these other interesting relative highs and lows, but then we get the lowest point here. And that again would correspond to, a beat in sound, or something regular when it lines up. So if we multiply it by 3, we see these interesting patterns, the comparison. A little bit more muddled as it's multiplied by 3. But watch this. What if I multiply it by 4? We still start seeing this. And very interesting that the red line seems to follow the green line a lot more than the other. So what makes things harmonious would be if I multiplied this by 3 and this by 2. So now we get something that these won't always line up, where some of the other phase shifts we made them line up, keeping one sine of x and the other one sine of 2x, 4x, or 8x, they're going to line up on regular spots. But if I have this, so now we really see times when they line up kind of nicely, and then that leads to a higher beat, and this is harmony. So these are the things that lead to harmony. We want it to seem clear. Yes, there's times when they don't line up, but then there's times when they do, and then that's really clear. And as Aristotle said, that the things that we look at these patterns, the things that please the eye, that please the ear, that please the mind, are all very similar types things. It's these interesting patterns. So in this, you can tinker with all sorts of things and see how it plays out. What looks like it leads to more harmony and not. There's even, we can even do like Python playing audio sounds related to that. Most audio sounds are much higher frequencies than we're talking about here. It would be more like the sine of 200x, or, everything from, 20, 30x to a really low beat to, 4,000x, the highest notes on the piano. So they're much higher numbers, and looking at the graph would be a much more dense graph, but you'll still be able to see where those beats come up. If we have this 200, and this would be 300. So we see much higher frequencies, but we can see where these beats line up. Yes, and again, cool things for you to tinker with. But you see here the normal graph code, and really what we're doing is we're just graphing, 2 different sine waves, and then the third one is the combination. So that's what we wanted to get to. We look at waves, we look at trig, we look at waves, and then we look at interacting waves, and this is just the beginning. There's a lot more we can do with this.
So some of the things that we want to talk about here, now that we've looked at, transformations of sine waves, is if I have data that shows some sort of periodic trend, phases of the moon, levels of tide, higher or lower, possibly even, a store and then the crowd levels, how many people, fewer people, anything that tends to go up or down on a regular basis. Because if it's irregular, then I can figure out this pattern, but then it's going to change. So, it becomes not that predicting. But if it's established that it's regular, then we can start looking at what formula can I use to predict this? And very often it's a modification of a sine wave. We could modify a cosine wave, and really, the difference is the shift, or the difference is where we want this to start. So if we shift a sine wave, it's cosine. So very often we use a sine wave, but if I have something, I have some data, and it doesn't even have to be a perfect sine wave. We're going to look at just ways we can grab that, some of the key points and sketch out a sine wave that matches this. So that's really what we want to do. We want to see if we can, match up something well enough to make it predictable. Can I match something well enough that I can use it to predict? And that's the thing. If I can, that's great. This is also, as we get into, we're going to do a lot more of this in like other, full-on, statistics classes, more on data analysis, but I definitely wanted to include this throughout this course. Just some different things that you can do. One of the things is, grabbing data from somewhere. Another thing would be, what can I do to, display this and, use some adjustments to see what sort of sine wave might approximate this. But as we'll see, things aren't going to be exact. We're just going to see, can we get a good approximation? That's really kind of the goal here. Can I get a good enough approximation that I can use this to predict? And, if we can, that's great. If not, then we have to keep looking. So let's take a look at this. I just want to, just with this sketch, I just want to introduce it, but with the code, we're going to look at, how we can do this. And this is really going to connect with how a lot of our trig functions even help us with, data analysis. So let's take a look at that. Let's look at the code.
So let's just take a look at a little bit like what we can do to model these repeating functions. And, I like to go back to tides because it's a repeating pattern, high tide, low tide, up and down, reasonably predictable, but it's not perfect. And that gives us that ability to say, hey, can I predict this? Knowing that, my prediction might not be exact. So we're going to look at, as we looked at before, ways to get the data. And in this case, I already downloaded this CSV, and then we have this dialog to upload it from the computer. So, we upload it, and I'm going to store that. So I'm going to read this and store it this time as all data, and I'm going to make this table tide data. There we go. I probably didn't need the extra variable here, but in some other things I was doing, I used tide data, so I just wanted to make that connection rather than rewrite other things that I was trying. I also, good sometimes if you get the data from somewhere, put the comments in there of where you could get this. And I'm going to do a couple things here. So like I said, I already have this uploaded. And then in the code, because I wanted both of these, I wanted this describe, but then if I just print out the headers, if I just do this, I could just do tide data.describe, and if I just did that, it would print it out. If I just did tide data.head, it would print that out, but it wouldn't do both. So I have to put the first one in a print statement, and then this one can be the last line of code here. So everything for uploading it, and then I have this description here, so I can see all of my different headers, water level, and everything. This is kind of what I want, all these different water levels, and the count, and then we have the headers, and what do we have? Date, time, and water level. There we go. So we can convert this date time into something and use that and water levels and graph this. Pretty cool. We've been doing some things like that before so far in the course. So I just wanted to show you that once we have this, I actually used ChatGPT for this one part to show you. I did modify it, but I got a lot of this from there. And that's the whole thing. Like if you have data, now sensitive data, you wouldn't want to use that for, but this was already public data. I already knew that this count was 169, but it's kind of weird going right up to that limit seems to not work properly. So I really made this tied data, all data dot head. But see, if you just put the header, by default, it'll just give you, the first 5. But you can put a number in here, and in this case, I wanted the first 100. So now that's the tied data. Extract the necessary columns. There we go. So right away, I'm just going to convert it to date time. And given the format that it was in, that works out nicely. That just converted it to time. So I know that I have this value, water level, and this extra space, because as I found out that whoever made this table put the extra space in there, and so I needed to include that in my code. So now I have time and height as 2 different arrays. So, convert it days since the first measurement. So we're going to convert this, and in total seconds. So really this is just, the math minus the minutes. So, we're going to convert this to this time, and this defines a sinusoidal function. So we're going to take a look at this. There we go. So remember A for the amplitude, sine, so it's a numpy function, so np.sine. B determines the period of the function, that shift here, x minus c, and then d, the vertical shift. So we just define the sinusoidal function here, taking in these values, x, a, b, c, and d. And now what we can do is this curve fit function based on that sinusoidal function, taking in time and height, and create this, the predictions as the sinusoidal function. So what we have here, we can plot the original. So we're, plotting the original actual and predicted tide height, and we're going to have their X label and Y label. And what we have is this. Now, doing this, on your own, that might take some time, right? Thinking about these sinusoidal functions and, writing some of that code. It's nice to be able to do that in like a few seconds. And what we get is that sinusoidal function based on the data. We can get that estimate, and it's pretty good. So we do see that, the height gets a little bit higher than expected here, and a little bit lower than expected over here. So we get that variability here. We could possibly do more analysis for a better graph, but quite honestly, in tinkering, I'll give you the insight and save you the time. In tinkering with this, I wasn't able to get a better graph than this one. So pretty good. Just some examples of what you can do, creating that sinusoidal function. And you could work it out to, predict if you have this same type of thing. This happens to be time and water level, but you could have, time and water level of a larger data set. Remember going back and just putting all this, in this table name. We could always call this table 1, as I've done in other examples. Once we have that, you can always go back and do, all these very similar functions, to estimate the sinusoidal graph. And that's often what we want to estimate. If I have something that's periodic data, it goes up and down, can I predict when it goes up and down? And certainly, as bonus knowledge for you here, there's a certainly, things like stock prices go up and down. So people would love to be able to use this to model different prices and on the stock market. And what happens is you can create these great models, but it really doesn't hold up. So, you end up saying, oh, my mathematical model says it might be this, but, that's less predictable than the tides. So there you go. Some useful predictions. Try it with some other data and, see how close you can get.
Here's just some ideas for building an analog clock based on trig. So the clock, I need a clock face, and that would be a circle. We could talk about the unit circle, but there's actually also a built-in draw circle function in Python, matplotlib library. So then my angle would, referencing the unit circle would be an angle something like this. And remember, probably easiest to just make it start at 0, 0, and then the end point of whatever hand of the clock would be the x value, if that's my angle, cosine of that angle would be the x value, sine would be the y value. And I'll tell you this, remember, as the angle goes around, it's going to go this way, starting at about 3 o'clock, going counterclockwise. Two things we don't want. So we want our shift, we want it to start up here. So we need to apply a shift to this. And then also, we want it to go the other way, so we could actually have the angle be negative. And that would make it go the other way. So we could just make each of these negative to make it go around the other way, and then apply the shift. And then you could loop through this. You could have radians, and then 2 pi divided by 360 for each second. 2 pi divided by 12 for each hour, and adjust the minutes. So it might be more interesting to also see the second hand. So you could have the 3 hands, and you could make these a little bit shorter or a different color for each. That might be interesting. So I want to give you some hints here as you work on it, and then we'll go over exactly how you to make this happen, but give it a try. Set this up. This would be, and I'll tell you this, to make this shorter, you could have some multiplier here in front of sine and cosine. So the radius is 1 if I have my unit circle, so sine and cosine. But if I made sine and cosine, some other multiplier, if it was 2, then this would be twice as big. If it was 1/2, it would be a little bit less. So we can, you can apply some of those. So that would be it. Set up your loop, set up your drawing a line from here to here. Showing you some animation that you can do on the graph. Decide how long each thing pauses. Have your animation, and give it a try. Tinker with it, run it, see how it goes. All right, let's look at the code.
We will just show this first part, displaying a clock with the hours and minutes. We're going to get the current time and then display it once. Interesting, and you will see then how we can build upon that. The next thing we'll do is the set to show the seconds. All right, so let's jump into this here. So displaying the clock, this is nice because it'll give you an illustration of putting together, displaying a circle, drawing a line, plotting points, and using sine and cosine, and how we have those adjustments here to take the time of day and translate this into lines on a graph. So we see all our imports, pyplot, display, importing math, time, and date time. Okay, so I'm going to set up the plot for the clock face. So classic setting up subplots. Now, I called my variable circle. Here's what we're going to do. We're going to plot a circle. Center, radius, and fill equals false because I want it to be open. You could probably put this, make a different colored clock face if you want, but I want it just open right now. This, a lot of times I graph and I don't worry about this, but remember Python skews the X and Y axis a little bit. So I make this equal so it's a nice circle for our clock here, rather than having a weird oval clock. All right, and creating the circle up here, then add artist, and I'm going to add the circle to my plot. And each axis, there we go. So the radius is 1. I'm going to make this 1.5 in each direction. I don't know, just to tie in the math and, give us a little bit of buffer around the edges. There we go. Dots to represent the 12 numbers. I said dots here, but I actually am going to make it blue triangles. Okay, so in range 13, because remember it's going to start at 0, which is fine. And then if I have range 13, the last one it will do is 12. And that's what I want. Okay, so what am I plotting here? I'm plotting, notice these square brackets. That's going to be one x coordinate. And then after that, it's going to be one y coordinate. Okay, so what do I have? Math.cosine, and what do I want? B is my variable that I'm going to loop through from 0 to 12. And each of these, so if the circumference is 2 pi in radians, and then 2 pi divided by 12 for each number, so that ends up being math.pi divided by 6. And so, I'm going to plot that times, so these are all my angles, B times math.pi divided by 6, because each time. So that value, pi over 6 times 0, pi over 6 times 1, pi over 6 times 2, all my different angles. And then the x value will be the cosine of that, and then the y value will be the sine of that. And notice again, these are just 1 point, that's 1 point. I can do all the math right there within the brackets here. And each of them, I chose to make it a blue triangle just because. All right, so there we go. So that's going to plot, and we could put the numbers there. I actually decided to just make it blue triangles. So now we have our circle. We have a triangle for where each of the numbers would be around the clock, and minutes. Each of these, I'm going to get this variable datetime.now. That's why I imported datetime, and then I'm going to call my variable time now. The and actually just to confirm, because writing some different code in different languages, the syntax is a little bit different. I looked up, another freeCodeCamp colleague of mine, Colade, wrote a great article about writing code in Python to get the date and the time, hours, minutes, seconds. Nice brief article. So that was what I used as a reference. So thank you, Colade. All right, so get the time now, and then time not now. So I like this strf time. So really, it's probably a shortened version of the word stringify. So that percent sign, capital M in quotes. So that's going to get the minutes, and then I want to cast that as an integer. So there we go. So I get my time now, which is my date time object. I want to get the minutes, cast it as an integer. And then what am I doing for these minutes? So I have to do, again, 2 pi for the whole circumference divided by 60 minutes is going to be 2 pi divided by 60 is pi divided by 30. Then I have the minutes is going to be whatever minute this is. But I want this to be negative because as this goes through for whatever minute, remember the way the angles go, where they would start for an angle of 0 at the bottom of the first quadrant, and then the way the angles go around, in trigonometry for sine and cosine, I need this to be negative because I need my minute hand to circle around the other way. So that's why that's negative. And then remember, they would normally start at what would be 3 o'clock, so I have to have this shift of pi over 2 so that it starts up at noon or at 12 o'clock. So that's what we have this part here for the angle. I have this part for the shift, so it starts at what would be 12 o'clock, and then, calculating the minutes, and this is negative so that it goes around in the correct direction. So now that I have this minute and my minute angle, I'm going to plot this. So the minute, get the time, stored as, for that variable minute, and then for this variable minute angle, min angle. So now I'm going to plot, and 0, so the x value is 0, and then for the minute hand, I decided to call it 0.9. We're in the unit circle, so I wanted to make this 0.9 for the minute hand as the length of that hand, and then I'm going to do the cosine of that angle because I already worked out what that angle should be. So there we go, starting at 0, and then the cosine of that angle, and then the y value starting at 0, and then the sine of that angle. And in this case, notice B without anything else, so that minute hand is going to be a blue line going from this point to this point. And hours, now very similar. I already got my time now variable, so now I'm going to stringify hours, cast it as an integer. Now, that's going to give me hours. For mine, I put -4 because that's Eastern time, and that's what my computer is going to display. So store that as hours, and then very similar to the way we did minutes, negative because I needed to go around clockwise, and then the shift because I needed to start at what would be noon. So then also hours, 2 pi divided by 12, which is pi divided by 6. So there we go. So I have how many hours, and there we go. So that's my H angle, and then here's what I'm going to plot. Starts at 0, 0. I decided to make this 0.7 as the length of that. So the x value is the cosine of that angle, and then the y, 0. There we go. And there we go. So I didn't just do this so that it showed up as 007, but it's a happy coincidence. So sine for the y value, and again, that line's going to be blue too. And then after all this, I'm going to show the plot. So there we go. So we have this, set up the clock face, the numbers, how to set up the minutes, how to set up the hours. And then when we run it, it looks like this. So this is the time right now. You see 3:35, and this is what our clock would look like. Nice. It gives you just one simple display. But what if I also wanted the second hand? So I'm going to do the same thing, but I'm going to put everything in the loop for seconds. Same imports, but now I'm going to do a loop, and you could make this, whatever number you want. I just decided to end it here, which is, just over a minute. You display this, it looks neat, and then, maybe at just over a minute, you're not looking at it anymore. I don't know. I just decided there. So time sleep is 1 because I do want this to happen every second. And what am I doing each time? I'm going to clear the output, and you'll see then it'll display this. I have this first. I have the waiting and then the clearing the output first, because as it goes through the loop, I just would rather have this come up first. I probably could have put this last, but I think it works out better to put it first. And the rest of this is very similar. All these same subplots, same thing for the 12 numbers, and minutes and hours are the same. So let's look at seconds. What am I doing for the seconds here? All right, so this angle, 60 seconds. So I'm still doing, 2 pi divided by 60 or pi divided by 30. Still negative angle. This one is just A because that's my looping variable, A, for the angle. And, still the same shift. So there we go. Just like the other hands, the shift, so it starts at 12 o'clock, and then the negative angle so that it goes in clockwise direction. And then I just made this X and Y for cosine and sine. And now, what I have is I'm going to plot. There we go. The X value, this is a line from 0. The X value goes from, so the first XY value is 0, 0. The second XY value is XY, as I have defined it up here. And then second hand's going to be red, just because. So there we go. So all of this, and just notice the indent, all of this is in a loop. Again, I think it works out better because I have to loop for the second hand. It really just kind of redraws it all, and this is not that many lines of code, and it redraws it in a reasonable amount of time. So now I have same time, and we see the second hand. There we go. And it seems like it's right on track with, every second. And that's good. And so this will continue on. It'll loop for just over a minute, and then it'll stop. You could always change the loop, or you could do something else with this if you wanted to make something that displays it, on a right, even longer. So, but there you go. And hopefully, then this clarifies. Maybe you tried this already, and we're kind of getting a little. You might have gotten a little lost on exactly what the shift should be, or maybe you forgot the negative or something like that, to make it go clockwise. So hopefully this clarifies it, and you can see how to make the clock. All right. So enjoy. I think this is just a fun project, putting it all together.
So here we're going to go beyond the right triangle. We don't even need a right angle anymore to figure out angles and sides. And the first rule that we're going to look at that does this is the law of sines. So every side is proportional to the angle across from it. So if I have, that angle C opens up to side C, angle A opens up to side A, angle B opens up to side B. So we have this 3 ways. You only need, 2 of these parts, but A is proportional to side A, B is proportional to sine of angle B, C is proportional to the sine of angle C. So if we have any of these, if I know an angle on the side across from it, that's the key. An angle on the side across from it to set up that proportion. And then if I know one other angle or side, I can figure out the other one. And you see, once we know some things, we can figure out some more, and then, maybe then I know 2 angles, I can do subtraction to figure out the third, I can do law of sines again to figure out the other side, and there we go. Knowing 3 things about a triangle, I can figure out everything else. So let's see how this would work. So let's say, I know that angle C, I'm going to use degrees, that angle C was 60 degrees, and maybe side C was 5. All right, so what else would I know? Maybe I know that angle A was 50 degrees. And so given that, what I can figure out is then side A. So I would set up that proportion here. I would set up, A over the sine of 50 equals 5 over the sine of 60. And there we go. I have my proportion here, and I can figure out, cross multiply, and then figure out what I have. So 5 times the sine of 50 divided by the sine of 60 equals A. And we can figure that out. So since things like this, you definitely would break out your calculator. Rarely you're going to come across one of those angles where we definitely know, I know the sine of 60 degrees, but sine of 50 is not things that we're expected to memorize. So what we would have is, you're going to break out the calculator anyway. Let's write code to do this. Set up the ratio that you can set up, maybe even prompt for input, and calculate the side or the angle that you know. If it was the angle that you didn't know, then let's say we'll do this the opposite. There's going to be one more step here, and let's say I'm going to keep this. So let's say if I have 5 over the sine of 60, and let's say it was the side that I didn't know. So it may or may not work out to be a 50-degree angle again, but let's just say that this is a little bit less. So maybe that's a 4. Okay, and I don't know what angle A is. So then that would be 4 over the sine of angle A. And we see that when we do the cross multiplying, 4 times the sine of 60 divided by 5. Now, when we do this, we have sine of 60 is root 3 over 2 times 4, so it's 2 root 3 times 5. So now we have 10 root 3 equals, so we do this, actually not 10. So we would have 4 times, so it'd be 2 root 3 divided by 5. So there'd be 2 root 3 divided by 5. And normally we would have a decimal for this. We would do this on the calculator. But if I had this 2 root 3 over 5 equals the sine of angle A, we see that the next step is inverse sine, because the sine of angle A equals this. That's what we end up solving for. So then to get angle A, I need to do the inverse sine. And so that becomes the inverse sine, or arc sine, of 2 root 3 over 5, or the decimal equivalent. And then that's what would give us angle A. So we see, we're building upon proportions and solving. We're building upon, sine and cosine, or whatever our trig ratios are. Inverse when it's the angle that we need to know. And still, knowing these steps, then, certainly, that happens to be an angle we know. Most of the time, it's not going to be. So even this, we'd probably want a decimal equivalent. So we're going to write code to do all this, prompt for what we know, run it through the formula, and if it's an angle that we don't know, then we have this step at the end. If it's a side, then just cross multiplying, and we'll build upon that to be able to solve any triangle. But let's take a look at the code to solve using the law of sines.
So if you find yourself in the situation that at least one of these angle and the side across from it, and then if you know one other thing, an angle or a side, then you can do law of sines. And remember, if I do law of sines, if I know side B, then the only thing I can figure out is angle B. At least in the first step. You can run through this now that you know more things, but that's another story. So, you're going to set up a proportion. Remember, 2 of these, but this formula shows that you can do it with any of the 3. So for all of this, I'm just going to picture the first part, A and B. And remember, you can call them A or B as long as you know one side and the angle across from it, and then one other side. We're just going to call them A and B. So these are our known values. I would know angle A and side A, and then I'm going to do the simple version here where I would know angle B. So if I know these 3, then I'm just going back and picturing this cross multiplying. So I know angle A and side A, and then I would know angle B. So what do I have? Sine of angle B cross multiply, times side A divided by the sine of A. And so that's what we have. And I just need to convert this all to radians. Math.sine, math.radians, angle B, times side A divided by math.sine, math.radians, angle A. All right, so we see just my cross multiplying here, and then I get side B. But each time I'm converting it to radians because I'm expecting that people would put in degrees for these. A lot of times in triangles and the situations these come up, it's degrees inside a triangle. That tends to be what people use. So you could have radians here, which simplifies this a little bit, but very often it's going to be degrees. So there we go. There's the formula. You set up the known values, and if I'm trying to find a side, then there's my formula. If it's an unknown angle, very similar, but a little more complicated, I'm going to add another step. So if the unknown angle, known values are very similar. I know angle A and side A, and this time it's side B that I wouldn't know. And so with side B, then here's my cross multiplying. Now, notice I just made this variable B that we're going to deal with and change later. But my cross multiplying, remember, if it's side B that I know, then side B times the sine of A divided by A. But what does that give me? That gives me the sine of angle B, not the final answer yet. So I have side B times the sine of angle A divided by side A, but again, not my final answer yet. Divided by side A, and I think I just clicked there accidentally. Yep. Okay. So just this variable B, I do my cross multiplying, but I'm not done because angle B is the arc sine of that. So I solve for B, but then I have to do the arc sine of B. So math.a sine of B, and then it's going to be, that's all automatically going to be in radians, so then I'm going to convert it to degrees and then output angle B. So then I'll print that. So we see same cross multiplying, but remember that last step is arc sine, because I'm going to get the ratio, and then it's the sine of angle B equals that. So there we go. Then we can get fancy, because this is the value of putting all this in code, that you can set this up once and you can have, prompt for input. You don't even have to change the code here. Up here, to make it simple, I just have it built in that you could just put your known values in here. But we can set this up if either angle or side is unknown. So prompt for the known values. All right, the known ratio. And here I'm going to ask for the known angle input, and then cast it as a float called angle A. Side across, input float side A. And if you don't know the value, put an X. Sometimes I have it as a 0, so in this case I have it as an X. So input the other angle or the other side, and somebody's going to enter a value for one of these and then an X for the unknown. And then if we have this, so if angle B is the unknown, then we're just going to take this. Oh, okay, well, we already would have had side B as an input. And you see, each input here, I didn't convert it yet because the X could be a string. And then once I find out which one it is, then I'll convert the other one to a float, side B, and then I do my ratio here. There's the ratio. I remember it's the unknown angle, so it's ratio. I do my law of sines, but then I convert it because that just gives me the ratio, so I have to do arcsine, and that gives me that in radians, and then there we go. Notice this one, I just did it a little bit differently and made it here just the formula. There we go. Radians times 180 divided by pi gives you the angle. So notice this just manually, converts it to degrees. And different things. Sometimes, you can just use math.degrees, math.radians to convert, and sometimes you can, set up the cross multiplying yourself. Either way. And that's if we have the unknown angle and then the unknown side. So if that's x, now we'll convert the angle. And with the angle, there we go. All one formula. Very nice. Convert everything. Convert to radians behind the scenes so you don't have to see all those decimals. And then just right away output side B. There we go. So now we see how we're starting to build upon these formulas. We have a formula for the sine, sine, cosine, and tangent if I know that I have a right angle. We have law of sines now for this situation if I know the angle and the side across. And there's more that we can do to work with triangles where I don't even have a right angle, as long as I know some things. So next thing we'll get to the law of cosines.
Now let's talk about another way to find the angles and sides in the triangle. Also, we don't need a right angle for this. So we have the law of cosines. And if you take a look at the setup of the law of cosines, the first part of it looks like Pythagorean theorem, c squared equals a squared plus b squared, but then we're subtracting something here, minus 2ab times the cosine of c. So we notice that if it were a right triangle, if angle C was a right angle, the cosine of 90 is 0, so then we wouldn't be subtracting anything, and then you go back to that formula. But this is the adjustment here as angle C gets bigger or smaller, minus 2ab times the cosine of C. So that's how we would get, and remember, in doing this, we would be solving then for side C. So as the angle gets bigger or as the angle gets smaller, then that gets smaller, and then the cosine actually gets bigger so that we're subtracting more, and that corresponds to a smaller side C. Also notice that I usually remember it is this one way. Sometimes people rearrange these A, B, and C and everything, but you can solve for side C, or I could rearrange it to solve for angle C because they each show up once. So if you knew everything else, you could solve for angle C as well. Notice the setup then of what we do know. Solving it this way, if I'm solving for side C, what do I know? I would know side A and side B, and then I would know angle C, which is the angle between them. So that's the situation for law of cosines. If I know two sides and the angle between them, law of cosines. And then the other way, then if I do this, then I know the angle, then the only thing I can solve for is the side across from that angle. And this is where some people rearrange whatever letter they want to put for the side that they're solving for, and then the other two sides. But remember, whatever it is, it's two sides, the angle between, and then you're solving for the side across from that angle, whatever letters you decide to call them. Or if I knew all three sides, that works out because I could plug in everything, and then my last step would be inverse cosine to figure out the angle. So we could do that. And remember, the rearrangement of that is I would subtract c squared minus a squared minus b squared equals, just to show you the setup of this, so then that would, if I subtract these over, then that would equal negative 2ab times the cosine of angle C. And what do I want to do? I want to divide both sides by this. So it would be c squared minus a squared minus b squared divided by negative 2ab equals the cosine of c. And we'll look at this in the code that then after I would solve all this, then I'm going to do get that number, and then I would do inverse cosine to figure out that angle. So, we'll look at this in the code, how we can use this, because at any point of this, you're going to be plugging this into a calculator anyway, and possibly even having a formula already on your calculator for it. So what we want to do is we're going to look at the code to prompt for these sides or these angles, these sides and possibly an angle, and then use that to solve, depending on which side you know. And then we'll build upon that. Now that if I have that situation, two sides and the angle between, or if I know all three sides, whether I have a right angle or not, I can solve one thing, once I have one more, I can do law of cosines again. Maybe if it's another angle, I can do subtraction, and we can put this all together to know everything about the triangle. So let's take a look at how we would use the code to prompt for what we need and then use the law of cosines.
So here's the law of cosines in code. So the known sides are a and b, and if you can picture the triangle, then we have a and b. Well, the other side would be c, so angle c would be between a and b, sides a and b. And we see that if I have a and b and the angle between them is c, that's the situation that we know. So if we take a look at this, let's say I do know side a and b and angle c. We see that that's everything on the right side, and I can do all this, and then I might even just break it up into two steps, do everything on the right-hand side, and then one more step to square root everything to solve for c. Also, that if I wanted to, I could, if I knew a, b, and c, if I knew all three sides, then I could plug this in, and I still only have one unknown, so I can solve this, and I would do that in a couple steps. We'll get to that. So unknown side, let's just work with that first. So remember that I've seen this in textbooks that there's multiple formulas for this just because they're changing what they label as A, B, and C. Just take it that the two sides call them A and B, and the side you don't know, call it C. That way you don't have to worry about it seeming like multiple equations. So that's it. I'm just going to, whatever two sides I know, I'm going to call them A and B. C is the angle between them. And then that side that I can solve for is across from that angle. So I would know side A and B. I would know angle C. And you see how I'm going to do this in two steps. C, and I just made up this variable, but that's not going to be my final, equals, so side A squared plus side B squared minus 2 times side A times side B times math.cosine. And normally we would expect inside a triangle people would tend to use degrees, so that's why I'm going to do the cosine of math.radians. I'm expecting that C would be degrees, so angle C. So there we go. So we have all of this, and remember that it should be equal C squared, so then the next step I'm just going to square root it, and then that's side C. So really good. This is another good use of code because any of these complicated formulas, you're going to break out the calculator anyway. Hey, might as well write code to do it, and then you just have to change these values and then output what you need. So if I have an unknown angle, so very similar. When I know side A, side B, and I would know side C. So remember this, I like to just have one formula and think about algebra beyond that. So if it's angle C that I don't know, that's what I can solve. Notice I still only have one unknown, so I can solve this. But here's what I'm looking at. I'm going to subtract a squared from both sides, subtract b squared from both sides, and then what I'm left with, I'll divide by negative 2ab. And that's what I'm going to do in these couple steps here. So I'm going to have, I just called this part 1. So c squared minus a squared minus b squared. And then what do I have left on the other side? I'm going to divide negative 2ab. Negative times 2 times the side A times side B. And then I have those, so then I would divide, and I'm just going to call it part 1 divided by part 2. And remember that division, I have cosine equals that, so I would do arc cosine. So remember that still gets me my ratio, but I want to know the angle, so arc cosine, and then that's in radians. I would expect that we would want degrees as the answer, so then we store it as that. Pretty good. And then, if I have either side, I could get really fancy with this. So I definitely would need to know side A and B, so I would expect that input and right away convert it. If you don't know the value, put an X. So side C or angle C. And then I just work this in. If angle C is X, then I'm working in these, you know, how I would do this. There you go, side A, side B, side C. And there we go. So same equation, side, you know, if I know the angle, I have to go through all this. Side C minus side B squared minus A squared. There we go. Step 2, the ratio divide, step 1 divided by step 2, and then the arc cosine. And then I just split it up here as one more step, then convert it, the angle. So the angle here. So if I have side C that I don't know, then there we go. I will take that and run everything through. And notice I just did this, and then the next step, square root. Okay. So, and then also notice, instead of doing like math.radians, I just did the conversion here. Here, I didn't need to do the conversion, I just need to square root it. So, now we have this, if I know either side, either a side or an unknown angle. Putting this together with the law of sines, we might start thinking, hey, I can solve other things, but we're going to add another formula, and then we're going to get to that. How we could, you know, solve different triangles. But here we go, different situations for the law of cosines.
So here's another area formula. When we learn area formulas for triangles, we think, you know, it's 1/2 times the base times the height. Now, this doesn't contradict that, but what we're adding is also times the sine of this angle C. So let's just say that this, if C was a right angle, then A would be the base and B would be the height. So it would be 1/2 times base times height. And then again, if this was a right angle, the sine of 90 is 1. So times 1 wouldn't change the answer. So we see how that works, but then as this angle gets smaller, the sine gets to be smaller, so we're multiplying, and then it gets to be less and less of an area. So just a really cool, useful formula here, because I don't need base and height. I can just find two sides and the angle between them, and that's all I need for calculating area. Now we'll notice that's one of the things we need for law of cosines, and then in using those law of cosines, law of sines, I could eventually pretty easily get a situation where I have two sides and the angle between them, so we'll be able to find the area. So we'll take a look at finding the area, and then we're going to put it all together, finding any three things I know about a triangle. I can find everything, every side, every angle, and the area. And this one more formula here is kind of like the last piece of the puzzle.
And here's this new area formula in code. So notice I just put the formula here. If A and B were the actual base and the height, like if this were a right triangle or something, then that angle C would be 90 and the sine of that would be 1. So you see it doesn't contradict. But then as C changes, then the area gets smaller. So we can just put this all in one step here. 1/2 times A times B times C. And here, instead of just putting it in code, I right away jump to the user input. So we're prompting for the input side A, side B, and then angle C. And again, don't get hung up on which one you're calling it. It's the two sides and the angle between them. And this works any two sides and the angle between them. We can figure out the area here. So given these two sides and the angle, input, cast them as float, and then just run it through the formula. 0.5 times side A times side B times, and I would expect that angle to be in degrees, as usual for inside a triangle. So angle C, convert it to radians and do the sine. There we go.
Now let's put it all together. Let's solve a triangle. So that's, any three things that I have. For this example, I said we'll start with, let's say I know all three sides, but none of the angles. So if I have that, how can I get all three angles? Well, we have a law of cosines that if I know all three sides, I can figure out one of the angles. So then let's start with that. Let's say I'll figure out this angle here. So if I do that, then law of cosines, I'm not worried about whether which one I call A, B, or C. So remember, then we have that C squared equals A squared plus B squared minus 2AB times the cosine of angle C, which we don't know. So if I have that, then let's plug in. If I want to figure out this angle, so then I'm going to call this side C. And again, same formula, we just decide which one we want to call side C. So I'm going to do that as 7 squared equals, and we'll call it A and B. So, 8 squared plus 9 squared minus 2 times 8 times 9 times the cosine of angle C. All right, so if I have this, then, I get that that's 49. So 49, 64, 81 minus 9 times 8 is 72. So times 2, so then that's 144. And only this gets multiplied times the cosine of angle C. So if I subtract these over, then I'm going to get, there we go, 64 and 81. Subtract, it actually is end up negative 96. And then I'm going to do a couple steps here. Then I'm going to divide by that. So then I have over negative 144 equals the cosine of angle C. So we see, we'll subtract these and bring them over. And now I can even put this, if I was doing it on the calculator, remember we're going to write code for all this, but then the negatives do cancel, but we would just write code for whatever these numbers happen, these variables happen to be. And then remember, we're going to do inverse cosine. So it's really the inverse cosine, or in the code, it's going to be the arc cosine, math.a cosine, inverse cosine of 96 over 144. And that's going to give us, I'll round it, and then that's going to give us an angle of 48.2. So we would know that one angle, and in degrees, then that would be, I'll put it on the inside, that would be 48.2. And what I can do then is then I'm going to do this again for one of the other sides. If we weren't using a calculator or writing code, we might debate, what would make the numbers, more manageable. Writing code, we just want to have a formula that works every time. So yes, some of the numbers are going to get larger, some of the numbers might be weird decimal places, but that's fine. The code's going to work all that out in a fraction of a second for us. So I'll pick this angle next. And so if I do this, using that same formula, again, not worrying whether I call what I call A, B, and C. So if this is the angle that I want next, so then 9 is what I'll put in for angle C. So it'd be 9 squared equals 7 squared plus 8 squared minus 2 times 7 times 8 times the cosine of angle C. And again, whatever I happen to call it. So we see, I want to show you like on the board, here's how we would use the formula. Whatever the angle, the side is that I know, and then the angle across from it that I want to know. These are the two things that might change depending on, the situation. So there we go. So what I would have now, it'd be 81 equals 49 plus 64 minus 7 times 8 is 56. So times it's 112 times cosine of angle C. And if I subtract 81 minus 49 minus 64 again, then I get a negative 32. And then if those are all subtracted, then this is what's left on this side of the equal sign, and I would divide by negative 112. So it'd be divided by negative 112 equals the cosine of angle C. And again, negatives that cancel out. So we will do inverse cosine, and we're going to use arc cosine, math.a cosine when we get to the code, of 32 over 112. Also, if I was trying to do all this in my head, then I might reduce that fraction. But remember, writing code, it'll work that out, no problem, in a fraction of a second. So we're just going to have it, when we set up the code, it's going to be, whatever variables happen to be there, it'll work it out. So inverse cosine of that, then that's going to get us an angle of 73.4. There we go, rounded. So there we go. Let's call it this, 73.4. And then if I have two angles, I'm just going to use subtraction. And even in writing the code, we'll use subtraction to get that third angle. So we would add these up, subtract it from 180, and then that would make this angle 58.4. There we go. So we have all three sides. We just figured out all three angles. And then what we would do is I could do one more step to figure out the area, because very often that's something that we'd want. So I'm going to pick this angle here. So just because. So the area, remember then that's 1/2 AB times the sine of C. So then that would be 1/2 times 7 times 8 times the sine of 73.4. And there we go. So I would work that out in the calculator. So 28 times the sine of 73.4. There we go. And we could figure out the area of that. So then I would, as we get to the code, we'll look at putting all this together and then setting an output. One of the things that, I rounded in all these steps, but in the code and behind the scenes, we would store these variables and we would not want to round them until the final, because they will end up being a lot of decimal places. We want that for our in-between steps, but at the very end when we are about to display it, then we'll round them. So we'll look at this, setting up all these to have a definite method. What are we starting out with, and then work from there. Just using the variables, not rounding until the end, and then we'll look at outputting. Then no matter what we input, it will output every side, every angle, and then the area. So let's take a look at how we do that in the code.
To solve any triangle. And here, notice I'm also importing the matplot library because I want to just give a triangle, even though it's not drawn to scale. And you'll see I'm going to have some points and some lines just as a reference. So then I'm going to label this, A, B, and C. Don't worry about these numbers, you'll see. It's just as a reference, and, taking out the axis lines. So after that, I'm going to put a menu here where I'm just going to print out each menu option. And this is, how we can put it all together. Of all the different things, let's create a menu. What do you know? Do you know 2 sides and the angle between? 3 sides, side, angle across, another angle. And notice each of these correspond to a different situation. 2 sides and the angle between, then we know we're going to do law of cosines. 3 sides, also law of cosines, but it's going to be different. Side, angle across, and another angle. Side, angle across another side. So the 2 situations for law of sines. A right angle and 2 sides. So Pythagorean theorem, if I know that. Right angle, side, and another angle. So that would be trig. Sine, cosine, and tangent. I could do subtraction to get the third angle. And you see how, given each of these starting situations, we can build our way to knowing the whole triangle. So, given the options, this is what you're going to end up doing. The angle, these variables, we'll just initialize these at the beginning, just so that, here's what I'm using. Angle A, side A, angle B, side B, angle C, side C, and then the area. And throughout all these, we're going to keep these variables consistent, and then we'll work with them. So I did this one as an example. So law of cosines. So to find the unknown side. If you pick option 1 that 2 sides and angle between, it's law of cosines. So having picked that option, we're going to prompt for side A, side B, take them as float integers, and angle C. Again, we expect it to be a degree. And so I really took these from what we were doing before, solving. So step 1, and then I'm going to run through my law of cosines, and then I made another step where I'm going to square root step 1 to get side C. So now, prompted for these, now I also have side C. I can do law of sines to find another angle. Because you see now, I do know angle C and the side across from it. So I can use those to find another angle. So again, just copying this from law of sines and remembering our cross multiplying. So I would know side C and angle C, and let's call it A is the one I'll work with next. So I'm going to do side A times cosine of angle C, times sine of angle C, divided by side C, and that's going to get A, and I just decided to break this up into 2 steps because that's just an in-between variable. A, I need the angle, so I need arcsine, and then convert it to degrees. So now I also have angle A, which, having all 3 sides from earlier, I just got angle A, and I just can use subtraction to find the next angle. 180 minus angle A minus angle C. And then we have our newer area formula. So I don't need base and height. I can just do 0.5 times side A times side B times the sine of the angle between them. And now with all of these, it will overwrite all of these variables here. And I'm going to print this out. You see, angle A, side A, angle B, side B, angle C, side C, and the area. And each of them, I just have this built in that I'm going to round it to 2 decimal places, only at the very end here. Because sometimes it gets to be, really long decimals, and we really don't need that. We don't want to round in the in-between steps, but we also, 2's plenty. Because dealing with any trig, it's very rare that you're going to get sides and angles to all be nice or even decent decimals. There's going to be something in there that gets to be a weird decimal. So when we run it, so we see this is the setup here. So I just wanted a general triangle that you can see the reference angle side and not drawn to scale. These can be any size, but just we get that general reference, and then right under it, what do you know? There we go. So I'm going to enter an option number. And if I enter the option 1, so I'm going to input, what do I have side A? I'm going to, in my mind, picture a nice 3, 4, 5 right triangle. So you see, like C would be a right angle, and I'm going to do A, B, and C. And I'll say that I know the angle between them. So side A, I'm going to say 3. Side B, I'm going to say 4. And angle C, I'm going to say 90. And you see then, it'll run through and give me every side, every angle, and the area. 3, 4, it figured out that side 5. And yep, these are the angles for a 3, 4, 5 triangle. The area would be 6. So look at that, 3, 4, 5, 6. That's why I picked that as an example. I just like how that works out. So I work this out. So this is all of these. Then I have the comments here, law of cosines to find the unknown angle, things we were doing before, and then you would complete the code here. I'm actually going to leave this to you because this is going to come up. Little hint here, this will come up in the big certification project. So I'll leave this for you to do the others. But you see, expect it to be using those variables. And if you copy the code from somewhere else, make sure that your variable names are the same, that you have, like, if I have side A, underscore and then capital A, that matches every time I'm referencing side A. So there we go, law of sines. And you see, I have the comments here of what you need to do, and you're going to, each of these finds one thing. Law of sines, it will find one thing, the unknown side, one thing, the unknown angle. And then you'll follow it up with the other things that you need to do to find everything else. Usually it's like, 2 more steps that aren't that bad once you do the law of sines or cosines once. Pythagorean theorem. And if you pick that option right away, it's going to print out, make C the right angle, and take that automatically. That way it works out that you can do Pythagorean theorem, a squared, b squared. And trig ratios, if you could take a look at that. That would be, hey, I know an angle on the side, and I know one of the angles is a right angle. Sine, cosine, and tangent, we can figure some stuff out. So that's what we want to do. And I want to show you here that, yes, you can put it all together and have something that you can solve any triangle. And then this will give you a chance to practice and put together a lot of this code. And we'll look at some other applications of this later. We can even, at some point, put this in functions so that you can just run a function to do whatever you want with the triangle.
Now let's look at getting a triangle from 3 points. I don't even know the sides or the angles yet, but let's say I have 3 points and I want to first of all say, hey, they would make a triangle. Let's get the measure of each side. So as I look at these sides that I want to get, you see, then I will make my triangle. And what we're going to do is the distance formula 3 times. So remember the distance from this point to this point, any perfectly horizontal distance is going to be the change in x, x2 minus x1. And then any, so exactly across here, and then any vertical distance is going to be y2 minus y1. And since we're on our Cartesian rectangular coordinates, this will be a right angle. And then this is going to be the distance. So that's what you remember. So the distance formula comes from Pythagorean theorem. So when I look at this, I'm going to do the change in, so that's going to be a squared plus b squared equals c squared. So I'm going to do the change in x. So x goes from 1 to 7. So it's going to be 7 minus 1 squared. And then b squared is going to be the change in y only goes from 1 to 2. So it's going to be 2 minus 1 squared equals c squared. But instead of squaring it here, I'm going to say square root both sides. So then we get to this. So, there's our distance formula applied to these 2 points. And so what do we get? 7 minus 1 is 6. Squared is 36. So then I get the square root of 36. 2 minus 1 is 1. Squared is still 1 plus 1. So c is the square root of 37. So I'm going to say c equals, we'll round it to 6.08. I don't want to round it to 1 decimal. I guess I could, but I'll round it to 2 decimals for this one, 6.08. So there we go. I can label this. And when we do this in the code, we were going to save this as a variable because it would have more decimal places. But, this side here is going to be 6.08. Put on the outside, 6.08. And then I'm going to do Pythagorean theorem or the distance formula again for the second side. So if I take a look at this, so I get, if I take a look at this next one here, so from, 1, so the change in x, it goes from 1 to 3, just over a little bit. So there we go, I get, so from 1 to 3, so I'm just going to do 3 minus 1 squared. And then the y value goes from 1 to 6. So then it's going to be 6 minus 1 squared. And then I'm going to square root all that. Again, we will have this in the formula, and it's just going to import, and we're going to run this through, 3 times distance formula each time. So what do we get? 3 minus 1 is 2. Squared is 4. 6 minus 1 is 5. Squared is 25. There we go. And so there we go. So we have 25 plus, so the square root of 29. And then I'm going to get the third one. So same thing, I'm going to do the distance formula again for from here to here. So notice it doesn't, since we're squaring it, the negative values are going to get squared anyway. But if I take a look, let's say I take this one as x1. So if I did that, so then it would be 7 minus 3. So that's fine. 7 minus 3 squared. And then I'm going to do 2 minus 6 squared, even though that's going to end up being negative, but then I square it. and then we square root each of that. So there we go. So that's 4 squared. So then that's 16. And then negative 4 squared is still positive 16. So then I get the square root of 32. There we go. So then this one's going to be 5.66. And let's say then that I want to do the angles. Well, then what I want to do, law of cosines for the angles. So if I have two sides, then I can do law of cosines to figure out the angle between them. You know, any two sides. There we go. And so the law of cosines, I can get, you know, any of these two sides and do the law of cosines, and then I can do the law of cosines again. You know, now that we have the sides, we can apply that. Again, each of these steps, I'd be storing them as a variable, and you know, we're just adding that other layer here, the distance formula. So from 3 points, getting all the sides, getting all the angles from the law of cosines. I'll do that. Maybe I'll do it twice and then subtract for the third angle. Then I can use our area formula. So this is good to be able to get this from 3 points, because a lot of times, you know, when we're dealing with like vectors in space, we might have the points, and then I can use these distance formula and other things to figure out, you know, the components of the vectors. All right, so let's take a look and see how to do this in the code.
Now, maybe if we already had the sides or angles, that we already looked at that. But supposing you just have 3 points, and we can use this in other things, from drawing to, you know, possibly some other, you know, physics applications. So that's why I made this a function. And you see here the first line, define the triangle function. And it's going to take this input of 3 points, x1, y1, x2, y2, x3, y3. And here, what are we going to do? I just put the overall, we're going to do the distance formula 3 times, law of cosines 3 times, because then we get the 3 sides, law of cosines twice for each angle, and then the third angle we can just use subtraction. So defining this, and then everything here, we're going to put the import math inside our function. And then we're going to go down here, and I just put comments for yourself too. Even if you're the only one looking at this, you want to keep it organized, put comments. So what are we going to do? We're going to get side A, and there's our distance formula. And we remember this, you know, change in x, so x2 minus x1, and then square it. y2 minus y1, and then square it. And then it's like Pythagorean theorem. Those would be the two sides, and then is equals c squared. So math.square root to get the whole thing. And what I already did is I actually just copied this and then changed the numbers or letters. But when you do that, be careful that you copy it correctly, or that you change what you need to change. So if this gets stored as A, so B, what I did is, instead of taking x1 and x and y1, now from here to there, I went from 2 to 3. So you see, I'm going from the second point to the third point. So this gets x3 minus x2, y3 minus y2. And then I'll store that as B. And then the third one, I'm going from the third point back to the first. So the order doesn't matter, because it would just make it negative, and then you're squaring it anyway. So I just put it this way, x3 minus x1, y3 minus y1. So we see, you know, the first side, the second side, the third side, and store that as C. I called it A, B, and C instead of side, because knowing that I'm going to use that a bunch of times, it's less to rewrite. All right, now to get angle A, so what are we doing here to get angle A? And remember, there's some algebra involved, the cosine, the law of cosines, And I did this in two parts here. So remember that you'd have, if I want angle A, then I have side A squared equals as the default formula. And so I would have to subtract side B squared. I would then subtract side C squared. And then what I have left on the other side of the equal sign, I'm dividing, so that's why I have divided by this. But that doesn't get me my final answer yet. That gets me the cosine of A, which I just put cosine underscore A as a variable. And the first way to do it, I'm going to get radians. And so if I have the cosine of A, then I'm going to do A cosine, the inverse, to get the radians. And I want that variable. And then I'll do this to convert from radians to degrees. So I have both. And notice in each of these, I'm not rounding anything in my in-between steps. I want to keep all those. That's going to help, especially when you do these and you're dependent on solving this one variable and then using that more than one place or even more than one place later. You don't want to round. You're not going to have to see these displayed, but it just makes your final answer a lot better. Keep as many decimal places as you can. So now to get angle B, very similar. So if I want angle B, then side B, and then I'm subtracting A and C. Same variables over here, and that gets me the cosine. Then the next step, inverse cosine, and then convert it to degrees. And angle C. So you see each of these, I'm doing it just in parallel, getting the radians, then getting the degrees. So how many inside the circle is 180 degrees, or inside the triangle is 180 degrees. So that's also pi radians, math.pi minus these gets me the other angle. 180 minus these gets me the other angle. And the area, remember our formula, instead of base and height, 1/2 b times c times the sine of the angle in between them. If b and c were base and height, then the sine would be 1, so that's 1/2 base times height, but then we can modify it as the angle changes. So, and to have one less conversion, I kept the radians on this, and I'm doing the sine involving radians. Now that I have all of these, A, B, and C are the sides, A radians, A degrees, are the angles, and then I have area. Now, in the final display, I will round it. Here we go. And in this, I just rounded them all to one place. You can always add more, but again, it's the final display. You definitely don't want to round it in between, but there we go. So this is all within a function. You could have it return values if you want. I just had this within the function that it would just print. And again, you can use these. I give you some things that give you a start, and you can, have this return other values or whatever you'd like. Okay, so then that's all within a function. I'm going to call the function. You see how I would call it. Triangle, and I decided to make it, easy values, 0, 3, 0, 0, and then 4, 0. And I put them in that order to make it a nice simple right triangle where angle C was a 90-degree angle at the origin. And this is what we get. Angle A, side A, angle B, side B, angle C, side C. Good times. Okay, so this project is the Foundational Math Certification 4, where we're going to go through, you're going to go through a lot of the things you've already been learning and working on, and hopefully also practicing, from the analog clock to the triangle solver to all the trig. We'll also add a couple trig applications, more about waves and syncing up waves for harmony. So go through this if you haven't already. I designed it for you to go through on your own, work through each step. This is going to be the walkthrough. So if you've already done that, or if you're stuck on anything, then this will give you an explanation of each step.
So this is the walkthrough of the Foundational Math Certification 4.
So hopefully you already gave this an attempt on your own, but then, you want to go over some things, and so we're going to do that. And just like the other certifications, first thing you need to do is acquire the testing library. This just shows you how you can import that or any library. In this case, I have that posted on GitHub. So when we run this, it's just going to go through. It's going to get the library, save it to your working directory, and import what you need. And then the test that we run at the very end outputs, yep, passed, go on to the next step. So we're going to do that. So drawing shapes. So we're going to get to some other things we're doing in graphing. And here's where, you don't have to have a function per se. You can draw based on any points. So here we're going to draw a polygon, and we're going to get an array of various XY vertices, and we're going to plot each point and then a line from that point to the next one. So that first function here is path.moveTo. So I'll move the cursor, that you won't necessarily see a cursor move, but we'll move it to that point. And then path.line_to. So I go from that point to the next, draw a line. And at the very end, path.closePoly, and we'll see this. So here's what we're going to do. You're going to, like a lot of these, I have something where it works when you first run the code, and then you're going to make some changes. So you're going to run the code, then you're going to add these points and change the two arrays. So here's how it's working. All the things we're importing: plot, path, patches. All right, so right now I have these vertices, and we're going to leave it at that. So notice each of these is an XY point, and I do have them with decimal points, just because I'd like to rather use them as floating points rather than integers, so I put everything with a decimal point. So now, as it is, you see the codes move to line 2, and each of these then, I'm going to have this, we're going to keep the code here, path, verts, codes. So we're going to create this path using this array of vertices, this array of steps. So I call them verts and codes, and patches. There we go. Face color blue, and you'll see that. All right, so now I have my plots, and I'm just going to add this patch. So you see, we define these two as an array of vertices, an array of steps. Define this in the path. Patch incorporates the path, and then patch goes into the plot. All right, and I just made this axis 5 in every direction. There we go. So let's see what happens when we run this. So you see, I just made this, given these 4 points from 0, 0, there we go, all these 4 points, and it goes around, and there you go, makes a circle, or makes a rectangle. It actually is supposed to be a square, but remember, Python often stretches out the x-axis a little bit. So then we want to go through and we're going to add these points here to make a hexagon. So I would rather add -1, 1. I would rather add that from 0, 0. I think I would rather add that after 0, 0 over here. So that's where I'm going to put this one, -1, 1. And I'm going to put this here. And then there we go, 0, 2, 2, 2. And then here, 2, 2, and then 2, 0, because we're picturing it's this point and then down to 2, 0. So I'd probably want to add that other point out here for a hexagon. So I'm going to make this there we go. In there. Okay, and now what I need is line 2 again twice, because otherwise I have more vertices than directions, and that won't work. So I'm just going to copy that, and there we go, 2 more times to account for those, and there we go. So let's run this and see. And there we go. So we have a hexagon. So that's part of this, and because it works, code test passed. So there we go. If I put them in any other order, it would have wanted to draw the lines in that other order, and it would not necessarily have made a nice looking hexagon. So there we go. All right. And now we get to this one. So Pythagorean theorem. All right. A squared plus b squared equals c squared. And this is really, we're going to build upon this a lot for the trig that we're doing. But we'll get to that. So side lengths. All right. So write the code to prompt for A, B, and C. So notice I do have this that I think it will do something if, you didn't do anything and write it. But there you go. Prompt for A, B, and C. And there we go. So C string, notice instead of 0, I actually really would want this to be this, something like this. I'm just going to copy this because I think that that's a little bit quicker, and then change that to C. So there we go. So we have each of these, it prompts for the input. But here's the thing. If I want, C is always going to be the hypotenuse. So if A is, if I just type in A, because remember, I first of all have this, if you don't know a side length, just enter the letter. So if A string is A, then that means B and C I have values for, convert them to float. And then what do I have? C squared minus B squared, and then square root that answer to get A. If B, I don't know, then it's going to be very, very similar. We just have the letters changed. So if B I don't know, then I'm going to prompt for A and C, C squared minus A squared, and then square root the whole thing. And then this, if C is there, then what do we have? Then I have, if C is what we don't know, then here I would make it C equals math.sqrt of, remember, C would be the hypotenuse, so we would have A squared plus B squared. A squared plus B squared. And so that's what we would have for Pythagorean, A squared plus B squared, and then get that answer, square root it, and then that's what C would be. And there we go. I could, and then I would have to print that out. Notice, can't skip the print statement. So then print, and I would print C equals C. So there we go. And then if we ran it, all right, so let's run this. Let's do a 3, 4, 5 triangle, and let's run this to show you that supposing B we don't know. So the original code, let's say A is 3, B I don't know, and then C is 5. You see, 3, 5, B must be 4. It also says code test passed because we did add that code. But let's say A is 3, B is 4, and C, I don't know, C is 5. There we go. And then, of course, it will work. The value of that is when it is not a nice 3, 4, 5. All right. So we have the distance formula. And here, I'm just going to show you what this looks like. Remember that it's really Pythagorean theorem. So I have this that you're just going to run this code, which I'm going to do in a second here. And you're going to see that how I plot the points. And, take a look at the code. I just put a delay. So it's going to plot the nice triangle, the points, and then you run the code and you'll see how this relates to Pythagorean theorem. So you see you have your 2 points, and then change in x, change in y, and then that would be the distance. Because on the Cartesian plane, change in x is perfectly horizontal, change in y is perfectly vertical, so that makes this a right angle. And that's how we would get the distance formula. And that's all you needed to do for that one, because now part 2, we're going to solve this. And remember, Pythagorean theorem, a squared plus b squared equals c squared. So then that translates to change in x squared, change in y squared, and distance squared. So we see, that could be a, b, and c as sides. And then change in x is x2 minus x1. Change in y is y2 minus y1. And then the distance, there we go, I'll just call it d. So here I'll use these same example points, 1, 1, and 7, 4. So change in x is 7 minus 1, change in y is 4 minus 1, and there we go. Then we solve, subtraction, squared, solve, and then we square, and then remember you're solving for d squared, so then the last step is square rooting everything. So this is what we're going to do. We're going to prompt for these points, and you see we're going to say without input, enter the first xy point, the second xy point. All right, and here we go. So we expect input that someone is going to put a comma. So we'll take this input, remember, as a string, split it at the comma, and then convert each to a floating point number, x1 and y1. So your job here then is to do this for the second point. Split it at the take the input from point 2, split it at the comma, and now this really is an array with 2 elements, so x2 becomes this. Now, I'm even just going to copy this, but remember, it is not first, but second. And here, it's not first, but second. And remember, it's element 1. So splitting at the comma into this array called second. So second element 0, second element 1, there's my x2 and y2 points. There we go. So now let's write the formula to calculate the distance. So we are just going to say, I'm going to do this, and I'll still do the square root last. So the distance, parentheses, there we go, x2 minus x1, close the parentheses and square it, plus y2 minus y1. There we go, close the parentheses, square it. And then my last thing is square root the whole thing. So I'm going to put math.sqrt and remember to close the parentheses here at the end. There we go. So there we go, distance formula, and print it out. So let's run it. All right, enter the first xy point, and let's do the same ones that we were doing before. 1, 1, and the second xy point is There you go, 4 comma 7. And there we go. We could, if we wanted to, round this at the very end. So, this, past, that's all we need to do. And we'll see in a lot of trig, usually at least 1 or 2 sides or angles will end up being really, long decimal places, because things just don't often work out to nice integers or even nice, like, quick decimals. So we could easily round this to 2 decimal places. So there we go, round. And I could round it to a whole number, in which case I could just close the parentheses there. And you see, so 1, 1, and 4, 7. That's okay. But you see, now you should use this because, you rounded it. That was not a part of what we were looking for. But I just wanted to show you, you could throw the rounding in there. And then, but now you have this. There we go. So let's think, 0, 0. And the next point would be 3, 4. And see, 3, 4, 5 triangle works out nicely, but it's not always gonna, you're not always gonna have nice like that. So we have the length of each side. Now we also have the midpoint formula. So no matter where the angle is, the midpoint of that side is adding the x values. You get the average of the x values and the average of the y values, and that's your midpoint. So you see that works out. I'm just going to use this other as a reference here, that if I have this midpoint, which I guess might be around the e at the end of distance, it really is the, halfway down this x line. So you just take the average of the 2 x values. And you see from the vertical, it really is halfway up. So you take the average of the y values. So that works out. It's a nice formula. We can just get the midpoint. Notice how we can do the same things we're doing, prompt for x1, y1, split it at the comma, convert, x1, y1 floating point, just like we were doing before. But now we want to calculate the midpoint. All right, so what do we have? We have x1 plus x2, close the parentheses, divided by 2. There we go, getting the average of 2 numbers. And we have, in parentheses, y1 plus y2, close the parentheses, divided by 2. And now we get the average of the x's, add them together, divide by 2, average of the y's. And there we go. Now I have the midpoint. So we can run this. All right. And I might go back to our same one that we were doing before. And there we go. The midpoint is 2.5, 4.0. There we go. Now, we're done. We don't have to do any more. You could, in tinkering with this, go back and also plot this point, and you'll see that it's exactly the midpoint. All right. So we're dealing with triangles all this time, but trigonometry is really triangles. The measurement of shapes gone with 3 sides. So it's really triangles, but trigonometry then takes it to the next level. We have some more formulas here. There we go. Tri means 3, gon means shape, metry means measurement. So the measurement of shapes with 3 sides. All right, so all of these, we're going to look at other formulas, and I have some more triangles that I'm going to display. This one I'm just going to run this and display it. And so we see, if I'm talking about angle A, that's the adjacent side, that's the opposite side, and that's the hypotenuse.
the hypotenuse, the longest side across from the right angle, that's always its own thing. But notice adjacent, because this, next to angle A, I have a hypotenuse and this other side. So this is the adjacent side, because the hypotenuse is always the hypotenuse. Then, see, this side is opposite because it's on the other side of the triangle, the opposite side. So there we go. Now, another perspective, I'm going to run the same thing, but instead of A, I'm going to reference this other angle B, and you'll see that if that's angle B, this is the opposite side, that's the adjacent. Because this is this, if I'm talking about angle B, that's the reference angle. So this is the one next to it. And then this is the one opposite. So we need to just be familiar with that. It is relative within the triangle, and then the hypotenuse is still always its own thing, the longest side. So the sine ratio is the ratio of the opposite side over the hypotenuse. So opposite over hypotenuse, and we're just going to run this, and we're going to see that the sine of A and the sine of B are different because the different angles have different opposite sides. So we see this code is just going to generate a triangle, and when we run it, we're going to see a 3, 4, 5 triangle, and then look at angle A. The opposite side is 3, and the hypotenuse is 5. So the sine of A is 3 over 5. Angle B, the opposite side's 4, hypotenuse is still 5, so the sine of angle B is 4 over 5. And now let's take a look at calculating the sine ratio. So this code is going to generate a triangle also, a right triangle, and what I did is generate random integers for the two sides, and then C, I did Pythagorean theorem and rounded it to get a reasonable hypotenuse. And here we go. It's still not drawn to scale, but it looks at least reasonable. So you can see these side measures. And what we're going to do is we're going to prompt for, what's the measure of the opposite side and what's the measure of the hypotenuse. So input gives us a prompt, and then the user input comes in as a string. We're going to cast it as a float and store it as opposite or hypotenuse, OPP or HYP. And then, now yours would have sine of A equals 0. So if you ran it, it would still just output 0. But your goal was then just to change this to sine is opposite over hypotenuse. And then we're going to run this, and then you'll see each time you run it, it'll generate different numbers. And given these, so if we look at angle A, the opposite is 8 and the hypotenuse is 8.1. And then it prompts you for that. What's the measure of the opposite side? 8. Hit enter. What's the measure of the hypotenuse? 8.1. And then it will give you the sine of that. There we go. Cosine, very similar. Cosine is adjacent over hypotenuse. And so this, just like before, this is going to just generate the triangle. So you're just going to run this. And then we see from angle B, from angle A, adjacent is 4 over 5. 4 is the adjacent, and 5 is the hypotenuse. Even though both of these sides are next to angle A, the hypotenuse is always its own thing. And then from angle B, 3 is the adjacent, and 5 is the hypotenuse still. So we see these different ratios. So now we're going to calculate that. Just like we did with the sine, we're going to get, a random integer for side A, side B, do Pythagorean. And we'll see for this one, calculating the sine ratio, the cosine ratio, doing very similar things, random integers, Pythagorean theorem and just rounding it to one decimal place to get the hypotenuse. And then we're going to prompt for the measure of the adjacent side, the measure of the hypotenuse. For right now, don't worry about that red underline.
And when we prompt for these, remember, what's the measure of the adjacent side? Input comes in a string, cast as a float, and that's adjacent. So if I store these as these two variables, then the cosine, this is just what you need to change. You need to make that adjacent over hypotenuse. There we go, the cosine ratio. And then we're going to run this. And you see, this is what it gives you, not drawn to scale. And it gives you these random integers, may or may not look reasonable, and the hypotenuse. And then it's going to prompt you for angle A, what's the measure of the adjacent side? Oh, it's 7. Type it in, hit enter. What's the measure of the hypotenuse? 11.4. And hit enter. And then what it does is it gives you the cosine of that angle. So there we go. So we can see that, these are some things we can do to generate the cosine. We'll do the same thing with tangent. And remember, tangent is the ratio of the opposite over adjacent. So this one, when we run it, it's just going to display this. So you can see from angle A, 3 is the opposite, 4 is the adjacent. And we also could imagine that the other angle B, it would be 4 over 3 because different opposite and different adjacent. So now let's calculate it. Generate integers. And when we prompt for these measures, then, what's the opposite? Store it. What's the adjacent? Store it. And then yours would be equal 0, but then this is what you're going to change it to, that the tangent is opposite over adjacent. And then print out the tangent. So we get to this, and, two random sides, Pythagorean theorem, we get the third one. And so from angle A, what's the measure of the opposite side? Oh, it's 1. Hit enter. And then the adjacent, oh, it's 6. Hit enter. And there we go. The tangent is opposite over adjacent, which is 1/6. Then there's the decimal. So remembering these, there's a nice formula here. And it's written like this because you see the big S for sine, and then a little OH opposite over hypotenuse. The big C for cosine, and then the little A over H adjacent over hypotenuse. Big T for tangent, opposite over adjacent. And you can imagine, using this, and you would pronounce this SOHCAHTOA. There we go. You could see that, SOHCAHTOA. But that way, in picturing this, it's easy to picture. SOHCAHTOA, easy enough, nonsense word to remember. And then it reminds us of sine, cosine, and tangent ratios. There we go. And what you're going to do here is, we see sine, cosine, and tangent ratios, and we're going to calculate the actual values, and we're going to use this as a practice app. So not only are you going to practice, remembering sine, cosine, and tangent ratios, then we're also going to write some code to generate a practice app. So here we have randomly generated side lengths and display the triangle. So then what we have is angle A. I'm going to use the same triangle that I've been using for the other examples. So the sine of A, and remember, so A is going to be lowercase a for the side, C for the hypotenuse, and round it to 4 decimal places. So what do we have? We want to use this for the other function. So the cosine of A, and I can copy this, but we have to remember what to change. So the cosine of A is going to be side B over C, because B is going to be the adjacent side. And then the tangent, I'll just paste this also. So opposite over adjacent, so that's A over B. So we see, we'll get these, and then the sine of angle B. If you can picture sine of angle B, the opposite side is going to be B, because that's what it is. You know, the naming convention, capital letter for the angle, lowercase letter for the side across from it. So the sine is going to be B over C. The cosine is going to be A over C. And you see that works out. It is the sine of angle A is the same as the cosine of angle B. And then the tangent is going to be for angle B. So the opposite side is going to be B, and the adjacent side is going to be A. So we have the actual values here now of sine, cosine, and tangent of those two other angles. The other angle in the triangle is a right angle, and we'll get into the sine and cosine. But setting it up like this, it almost seems like it doesn't quite compute because we have undefined. And anyway, so we have you're going to ask somebody to enter a fraction, but notice when we do this, I can't just automatically do that math and then output the answer, because this input that we're going to get for the sine, this input, it won't parse that dividing line. It wants to take it as a string, but then when I convert that to an integer, it's not going to quite work with that dividing line. So we're going to take that input, and then what we're going to do is we're going to split it at that dividing line. And so when we split it, this ratio is now an array with two elements. So the first element, that one we're going to convert to a floating point, even though realistically it's probably going to be an integer. I'm still going to say float. And then the next element, and I'm going to convert that to a float, and I stored them as n and d, numerator and denominator. So there we go. So now we have numerator divided by denominator. That's the ratio that we're going to get. And again, round it to 4 decimal places. So what we're going to have here is these, it's going to print the actual and then print the input. And we can see the comparison here. All right. So in each of these, it's going to round it to 4 decimal places so it matches. So when we see this, it's going to prompt for the input of all of these, sine, cosine, tangent, which each of these we calculated up here. And then all of this you actually don't have to change, but I just want to show you how this works. Taking the input, it's going to be some ratio using this dividing line. So each time we're going to split it and calculate it. And this is just a good thing to have, tool in your toolbox, taking in, a fraction that somebody types, but then converting it. So there we go. And we're going to test the app. So let's take this and run it. And we see that we generate these random side values, hypotenuse, and you can enter in, as a practice, sine of A, 19 over 20.62. So we'll put that in there, 19 over 20.62. And there we go. As you see, the actual compared to the input, and then you can check yourself. Is it correct? Yep, cosine of A, 8 over 20.62, and we put that in. There we go. And again, compare tangent of A, 19 over 8. Sine of B, 8 over 20.62. And so in addition to testing out your code, you're also practicing your trig ratios. Cosine of b, 19 over 20.62. And hopefully you're also recognizing that, you know, some of these calculations are similar because the sine of angle A is the cosine of angle B. And we have tangent of angle B is 8 over 19. And with that one, there we go. And the code test is passed not because of these correct answers. You know, if you put in an incorrect answer, you would just see the comparison and realize, nope, that's not the right answer. But the code test is passed because of the formulas in there. So, as I mentioned, the familiar pattern. So what we're going to do is we're going to look at just a loop here, and we're just going to change the ratio here. So if I have range 37, I just pick that number as a random number, but it's enough to show some values here. But if I have A as an angle, so there we go, 1 to 36, and then A times 10, so, you know, every 10, that's going to be, every 10 degrees, that's going to be enough. Then 360, because it's going to stop at 37. Well, if the range is 37, the last number would be 36, and that'd be 360 degrees. So we're going to talk about radians in a little bit, but for right now, the sine, we are going to take that angle, but that I have in mind as degrees, so we're going to convert that to radians because math.sine works with radians. So we have the sine value, math.sine, and it works in radians, so I have to convert that angle to radians. And all of that, we know the sine and cosine tangent values tend to be long decimals, so I'm just going to round that to 4 decimal places. So that's going to be the ratio underscore s for sine. So ratio cosine, I'm going to do something very similar. I'm going to take that value. In fact, I am even just going to copy this. And really, the only thing I'm going to change here is cosine. So it's going to loop through this, you know, every 10 degrees, which radians, that's not going to be a nice round number, but every 10 degrees. And what's the sine of that? What's the cosine of that? And this is what we're going to do. We're going to print that out. So I have, you know, the ratio and I have the tab. So we'll see this in a nice. So we see, you know, I just put a lot of extra spaces so we can see all these values. Sine and cosine is 1. And then if we look at the sine value gradually increases, the cosine value gradually decreases. Now, 45 degrees, they are actually the same. So we see this flip, you know, 40 to 50 degrees. You know, we really see that flip there. Sine of 90 is 1, where the cosine of 90 is 0. And then we get into some negative values for these angles that are beyond the triangle, but we'll see where they come into play with the unit circle. So we see all these, and that's all you needed to do. Take a look at those patterns. It's pretty interesting. We'll revisit that as we look at some other aspects of this. So we have radians now. We've been alluding to this, and a radian is the measure of the radius along the circumference of the circle. So that measure, 2 pi times the radius is the circumference, and so there are 2 pi radians in a circle. And there we go. 1 radian, it's about 57 degrees. And then exactly 2 pi is exactly 360 degrees. So, radians, it's good because it's proportional to the radius. So a lot of actual physics applications and such use radians because it makes a difference. It's proportional to the radius. That has an effect. Whereas degrees, we're used to using degrees, and a lot of things, it's kind of an arbitrary number. So for some applications, that's fine because that number doesn't affect other things. But there we go. So we have 2 pi radians, or 3 pi over 2. If I see it as 3 pi over 2, I'm going to say, oh yeah, that must be radians. But then that's 270 degrees. Here, we're just going to run this and just see the comparison. You'll see I have just, some code in here to display pi. Yes, this is the SymPy to display pi. So anyway, we have pi, and I just decided to do, pi over 1. So that's really pi. It's 180 degrees. Pi over 2, 90. Pi over 3, 60. Pi over 4, 45. Pi over 5, 6. So 1, 2, 3, 4, 5, and 6, it works out nicely. 300, we get to 7, all right, that's a messy number. 8's not horrible. And 9, 10, great. 11, another messy number. And then 12 back to... for a lot of ratios, a lot of radians, just remember pi over 12 is 15 degrees, and then just doing multiplication from that. Most of our important angles, the major round number angles, are going to be multiples of 15 degrees. So, pi over 12, reduce the fraction if you need to. So we just see our comparisons here. That's really this one and the last one. I just wanted you to run this to start seeing comparisons, seeing some patterns. And this all does relate to the unit circle. So it's called the unit circle because it's a circle with a radius of 1. So radius of 1 unit, hence the unit circle. And the center at 0, 0. So here's the interesting thing. When you plot an XY point, anytime you plot an XY point, you're counting, from 0, 0, you're counting over X, up Y. So perfectly horizontal, that's X, and then perfectly vertical is Y, and it makes a right angle because of our rectangular coordinates, and then the hypotenuse, there we go, which is 1 if it's the unit circle. So there we go. When we make that, I'm going to run this, and then I'm going to go back to talking about this. So we see if I'm on my coordinate plane, I didn't draw the axis here, but from 0, 0, if I were to plot a point, I count over X, up Y, plot the point. Well, then that makes that adjacent side X, the opposite side Y, because of my central angle here. And if it's a unit circle, then that's because the radius, or the hypotenuse in this case, is 1. So at every point I get what's the cosine of this angle, or what's the sine of the angle? Opposite, which is Y, over hypotenuse, which is 1. And the cosine is X over 1. So that's what we always have here. So sine is the sine of the central angle is Y over 1, the cosine is X over 1. So with this, we have the cosine and the sine for our unit circle. And that's really where all of our trig values come from. That, based on that unit circle, then my cosine and my sine are my X and Y values. And so that links up with here. We see each of these X, Y, and plot this point. So we see, sine value of 0.1736, cosine value of 0.9848. There you go, plot the point. And each of these, plotting these XY points. And when we get beyond 90, you're in that different quadrants. So that's why the cosine is negative. It's negative x values. And then when we get to beyond 180, which, x is -1, y is 0. And then beyond that, you're in the third quadrant. Both of them are negative. We'll see this come up again in a second. So in this is just, interesting if you want to take a look at it. It's similar to what we were doing before about just plotting a display to show this. So we have the unit circle here. And here's, connecting with that earlier step that I was just showing you. All right, so we know now that the coordinates are the cosine and the sine. And we know we did that loop a minute ago, looping through all the sine and cosine values. And then we're going to connect this to that earlier step of creating a path. Line 2. So I'm going to start it with path move 2. And then from that point, it's going to be path line 2 every other point. And then path close the poly. And that's what we're doing here. We're just going to start with this 1, 0. So that's my coordinate point. And each of these, because there's enough that are floating point, even the ones that turn out to be integers, I'm still putting 1.0, 0.0 with a decimal point. So there's my my vertex array that I'm going to build, and then I'm going to move the point to there, and now I'm going to loop through just like I did before. And here, I'm going to put this. I made it one less step here because I did a times 10 here. Still going through degrees, so from 0 to 360, because it'll stop at 36 times 10, 360. So same thing. But now I'm storing that. That's my x. That's my y. And then I'm going to append that to my vertex, my verts array. And I'm going to append this to the line 2. So each of these, I start with this, and I'm going to append each of these x, y points and this. And now when I complete the array after looping through all that, then I'm going to append this last one back to 1, 0, codes that append, close poly, and it all comes together. Now I have those two arrays, and then here's my path. Capital P path, and then that takes these two arguments, these two arrays, verts and codes, as stored as this path. So now when I do the graph, I can add, so you see I have to create this patch. So patches, path patch, and right here I add the path. I decided to make it blue, face color blue, and then the weight, the line weight, I made it 2. I just think that looks nice. And then I'm going to add that. So we see how it builds. We're building our arrays of points and steps, and then I put that together as path. That path variable shows up here in my patches, and that patch variable shows up here in what I'm adding to my graph. I don't always, but I did make this equal, so that it just looks much better when we're doing the unit circle, because it's a unit circle, not a unit oval. And there we go. We're going to plot this, and then when we run it, so this is what we see. We started here at 1, 0 and appended, 36 around every 10 degrees, and that was enough to give it a pretty smooth circle. But there we go. At every point, about every 10 degrees, we plotted an XY point and then connected the line. And that's where we get our unit circle. And this one I did put the grid, so we see that the center is at 0, 0, and our radius is 1 in every direction. And this is our unit circle. So you can really see that that's where all of the trig values come from, because at any point in here from 0, 0, I can count over some x amount, up some y amount, and I'm on the circle and plot that point, and it makes a triangle. So we loop around a lot, and we revisit things that we've done before in trig, not just because it's full of triangles and circles, but because these all relate, and you want to see these and see how one thing relates to the other, and then you come back around and see how something else relates to it. We're even going to take this a step further in the full course and look at imaginary numbers and how that relates to all of this. But there we go. So we see our unit circle by creating this circle of points in a path. So now we're going to solve triangles, solve for an unknown side. Now, the way I have this here, this is going to display something, and we'll just run this, and we're going to see that we have their imports. We're going to display a triangle, and I'm just going to give it a random angle. Then I'm going to put that text in there, and I'm going to give a random hypotenuse measure, as well as display side A and side B. So let's take a look at this, and then we'll go back and look at what the code is doing. So the first thing is, we'll come back to that output, is that we're going to display this triangle with an angle. I'm going to randomize this so every time that angle is going to be a different degree measure. And then hypotenuse, same thing, random number. And then I have side A and B. So if I want to set up my trig ratio for side A, we see the angle, so the sine is A over 8. And that's what I have here. The sine of 32 is A over 8. One step of algebra, multiply both sides by 8. So I have 8 times the sine of 32 equals A. And then when we solve, sine of 32 is always the same number. So we figured out that side A is 4.24. And that's what I want to do. You can do this on a board, without a calculator. At some point you probably need a calculator. Nobody's going to remember the sine of 32 degrees. But there we go. Showing the steps, how we set up our understanding of trig ratios and set up, here's my unknown, and how I can solve for an unknown side. So what we're going to do is we're going to do that for side B. So we see solving a triangle, I can, this works because I know that this other angle is a 90-degree angle. So to get the other angle, I have this one, the other one's 90. To get the third angle, I just subtract 90 minus 32. I'm going to do sine to figure out side A, and then I'm going to use cosine to figure out side B. And there we go. I have, all three sides, all three angles. So we're going to take a look at what we do here for sine. And we can copy all of this. So we want to get to this cosine value. We can copy the sine value if we want. So we can see the key feature is getting to these variables, but we can solve, we can even copy this for this one step of algebra, solve. We can copy all of this, and then I'm going to put this all here, and then we're going to change it. So first of all, we have the cosine of that angle is going to be B over side C. One step of algebra, because that times the cosine again. It's going to give us b. And then so here's what we're going to do. How do I get that cosine value? Which here was just set to 0, just to not give it error when you ran the other part. Cosine value is math.cosine. And remember, it's going to be the cosine of, that angle. And here we go, cosine, because then it's going to be that side C, which is the hypotenuse, times the cosine value equals side B. So we see we're walking through. You don't always, in your future endeavors, you're not always going to write out all these, but it helps you learn what steps you're doing, and then display it and see that everything works well. Okay, so then side A, which we're actually going to make it side B, is, there we go, that times cosine value. So there we go, side C times the cosine value, and I'll round it to 2, and then that's going to be side B. And after doing all that, there we go. We have the code that you just wrote. Great. And copy the model above. And after all of this, we copied it, so we already have side B. And that, it's not interrupting, but we can just delete this. And the question is, did you change every line except for the 3 static print statements? See the print here, solve here. So it looks like we did. Set up the ratio, and let's run this and see what happens. So we have our value there. So we see random angle 2 degrees, side A and B, hypotenuse 5. So side A, the sine of 2 degrees equals a over 5, 1 step of algebra, and we solve. So side A is very tiny. Not surprising, the angle is only 2 degrees. Set up for side B, the cosine of 2 degrees is b over 5, 1 step of algebra. Yep, 5 times the cosine of 2 equals b, and cosine is tiny, so side B is 5. Rounded, it looks like side B is the same, but it's just really because of rounding. They would not be exactly the same at all. The hypotenuse would be a little bit more. So, maybe B is, 4.99 or something like that. And there we go. So we have this. Maybe we can. Now, this is code test pass, so we can go on to the next step. But you could always go back and change this to round any of these to, multiple values. Make this rounded to 4 decimal places or something. But there we go. So now we see how we would set this up and how we would use this to solve. And we're going to apply this to the length of a ramp. Now, here we go. This one, once again, I like to have these where you're going to run the code and then do something to it. But if we have a ramp, so if you know the height that you want to get to, and if you know the angle, then we can use sine to calculate the length of a ramp. All right, so we're just going to run this. And as you see, I put some of the animation in, so there's the slight delay, but it will give you a different angle each time. And if you just run it, it's going to tell you the length of the ramp is 0, and now write the code to solve for side C. And each time, it'll give you a different angle there, and the height, and we can use sine to figure out side C, because knowing that angle, I know the opposite, and I want to know the hypotenuse. So then we go up here and we see it's already built in. You'll get the same animation here, random side, random angle, and then down here, we want to write the code for side C, which is sine. And if we remember, opposite over hypotenuse, and that's what we don't know. So we are going to have 2 steps of algebra like before. So we have, so the sine of 58 equals 5 over C, and multiply both sides by C, divide by 558. So side C equals that angle, which we have here, that side divided by the sine of that angle. So we're going to have, and I even put in this step here for you, radian angle. So we have side A divided by math.sine of radian angle. And it'll probably be a decimal number, but we'll leave it at that. And there we go. So different angle, different side, but the code should still work. The length of the ramp should be 20.7. There we go. And as you can see that way you can build in these variables and write the code, so no matter what the angle, you can figure that out. Oh, I want to get to this height, what angle. You can apply this to other situations in life. I want to get to this height, what angle do I want, and then therefore how long of a ramp. All right, now we have rope tension. So here's another one. Now this one, rope tension, will be cosine, and we'll see why. So tension is the force pulling on the ropes. If I have 2 ropes hanging straight down, then that works. The tension is divided by those 2 ropes. But if that angle increases, then the tension is more. So we'll look at this, then we'll go back and look at the code. So these blue lines, if I was hanging something, a light or a shelf or something, if I had these blue lines that are perfectly vertical, I would just divide the tension divided by these 2 lines, these 2 ropes. Great. But these green lines would be an angle. And as we see, the angle ends up being a hypotenuse, because if the line that's not there would be the ceiling, and so that would make a right triangle. So given that upward force on the blue ropes, then the green ropes would be more of a force. And as we can see, as that angle gets to be more, then that green line ends up being a lot longer than the blue. And we see this, that, if you were, practical applications, if you were hanging something and you have the ropes perfectly, 90 degrees with whatever you're holding up, great. But the more of an angle, the more tension on that rope. And if you're hanging something heavy, that's going to make a big difference. So we can figure this out. What's the diagonal force? Well, given that upward force, and I would know that angle, in this case 25 degrees, then what do I have? Adjacent over hypotenuse, and then that's cosine. So we see, just like a lot of the code's very similar, and I just have notes for each of these, the vertical forces, and there we go. But I have the random angle, or the I have my angle, and then I even converted it to radians for you. And I have the side that we know. So side C is going to be, so remember, cosine the cosine of, in this case, 25, is going to be 8 over side C. And so 2 steps of algebra, side C is 8 divided by the cosine of the angle. So we get side C equals, but I'm not just going to put a number in. It's going to be that side A, divided by math.cosine of radian angle. There we go. So when we run this now, we see the force on the diagonal rope. And as you see, every time you run it, it's going to give you different amounts, but that's why we want these as variables, so then the code will always work. So you see, look at that, upward force 3, we can call this newtons. Upward force would be 3 newtons, but if I have an angle of 78 degrees, which, you know, that'd be a huge angle, not drawn to scale here, but an angle of 78 degrees, then that force on the diagonal rope ends up being 14.4 newtons. Wow. You know, almost 5 times the amount because it's such a huge angle. And if you're trying to hang something heavy, then that really makes a difference. So, you know, an application for sine, like a ramp, an application for cosine, like tension on a rope, an application for tangent, surveying. So, just like the other two, we're going to run this code. And certainly not drawn to scale. But if I have the distance, I would have some really tiny angle here, because this is what we do with surveying. I look ahead and I have something here, again, very much not drawn to scale, but I would look ahead at some post and I have some markers. So I would know ahead of time the distance, you know, in this case, I'm calling it 0.5, but I would know this distance from one point to the other. So given that, you know, some post I have like way down the road, I would know this. And then so I have my surveying equipment and I measure this exact angle. So I'm calling it 4 degrees here, but really it might be something with, you know, a lot of decimal places. And that's what surveying equipment does. It ends up making sure that something is level on the bottom and then measuring an exact angle down to multiple decimal places. So then if I wanted to figure out this distance, what do I have? I would know this opposite. I would know this angle, and it's the distance I want to know. Tangent, opposite over adjacent. So there we go. By default, it'll just say, you know, distance is 0. But just like we had before, so the tangent of 4 is 0.5 over this distance, and 2 steps of algebra, this distance is 0.5 over the tangent of 4. And like the other ones, I have radian angle, and the other side, I have it as side A. There we go. Not as a random number, but it's, for this one, I put it as always 0.5. Again, if you're surveying, you know, your post that you put somewhere, you would know that distance ahead of time. So really then what you're measuring is that angle. So side B equals, I'm still going to use the variable because just in case I want to change this later, I don't have to change it in multiple places. So side A divided by tangent of radian angle. And there we go. So when I run this again, so given this, now this time the angle is 2 degrees, and it gives me the distance of 14. And who knows, maybe, you know, maybe this is in meters, you know, 0.5 meters. And then I have, you know, my surveying equipment. Oh, this is only 2 degrees. Oh, so then it's 14 meters, which, you know, doesn't seem that terribly long of a distance, you could walk that off. But we illustrate the point, and you can use this for, 1,000 meters. And if you have a good scope that you can see, then the process still works. So there we go. Applying tangent, you can use this for surveying. Okay, so now all those we applied sine, cosine, and tangent. This is also very useful, the law of sines. Now we're going to get beyond the right triangle. You can use this for any triangle. And, if you've gone through the other part of the course, you might remember when we were doing this setup, but here's the formula. These are all proportional in any triangle. Side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C. And there we go. These are all proportional in any triangle. So if you have two of these, then you can use the law of sines because, now even without code, let's say I had two of these, cross multiply, given these two, if I know that's four things in there, and if I know three of them, I can figure out the fourth, or any of these two. So if it's the angle that I don't know, remember then that's inverse sine, and the code we're going to use is arc sine. So here we go. We're going to prompt for. I'm not going to draw a triangle here. I'm just going to show you that what we're going to do is, given any of these two, and I'm not necessarily going to call, I might just call them A and B, even though it can be, whatever, A and B. And I'm going to prompt, so the known ratio, and you see, I'm going to ask for the known angle. And then I'm going to ask for the side across, because I do need to know that. I need to know an angle and the side across from it. That's my starting ratio. And then if you don't know the value, put an X. So then it's going to prompt other angle, and then it's going to prompt for other side. And you see one of these you're going to put a number, and one of these you're going to put an X. So, see, angle A and side A, I'm going to cast those as float right away. But angle B and side B, I'm not, because then if angle B equals X, I'm going to do this. This is going to be the model. If angle B equals X, what are we going to do? Now then, that means we must know side B, so then I'll cast it as a float. And then I'm going to do my ratio, side B times math.sine of math.radians angle A divided by side A, cross multiply. I'm going to do side B times the sine of A divided by side A. So that gives me my ratio. So then I need to do arc sine of that ratio to get radians, and if I want degrees, I could have just converted it, but I just decided to do the proportion, the radians times 180 divided by pi. So there we go. So this all works if we, if it's the angle B that we don't know, then we can write the code to solve for angle B. Now, if it's side B that we don't know, so now the next thing is convert angle B. So what do we have? So side B equals, so remember now if I know angle B, cross multiply. The sine of angle B times A divided by the sine of angle A equals B. Cross multiply. So side B equals the sine. Now notice for each of these, I used MP, but I also imported math. You can actually use either one here, which is kind of cool, but I'm going to use math. Math.sine of, and I would expect that somebody would enter an angle B as degrees, so I'm going to do math.radians angle B. All right, so there we go. So I have the sine of angle B times side A divided by, we have already math dot sine of math dot radians and that's angle A. Okay. So that's what we have here. So side B should be, so sine of angle B times side A divided by the sine of angle A. And so side B should be the sine of angle B, taking that input, and that'll be in degrees, converted to radians, the sine, times side A, and then divided by the sine of angle A, which we would already have up here. Angle A, there we go. There we go, pretty good. And so we can run this. So the known ratio, I'm just gonna pick one. So let's say it is an equilateral triangle. So the known angle, let's say it's 60, and the side across, I'm gonna call it 5. And we're gonna test if it's side B that we don't know. So the other angle, I'm gonna say it's 60, and then the other side is gonna be X. Look at that. Good times. So now you have it. You know, law of sines. Anytime you have that situation, I know the angle and the side across from it, and then one other thing, an angle or side, you can figure this out. Now we're going to build upon this, that you do this once. Now I have, both two angles, two sides. I can do subtraction for the third angle, and I could always do law of sines again for the third side. And there we go. And then I have the whole triangle. But we'll build upon this, because now we also have the law of cosines. And the law of cosines, this works if I have two sides and the angle between them. So that's the key. And remember from the course, so notice it's the formula looks a lot like Pythagorean theorem, but then minus this. And if this was a right angle, if it was Pythagorean theorem and C was the hypotenuse, then angle C would be 90, and then the cosine of 90 would be 0. So that means you would be subtracting, 0, and then all that zeroes out, and then you'd be subtracting nothing. But as that angle changes, so then you are actually subtracting something, and therefore we see how it applies. This also works. I always remember just this formula, but notice C shows up once if you don't know side C. If you know side C, you can figure out angle C, or if you know angle C, you can figure out side C. If I know angle C, it seems to be maybe a little bit easier, because all the things that I know are on one side of the equal sign. Solve all this, then square root the answer and get C. But if it's side C that we don't know, then I can do all this. If it's side C that we don't know, or if it's angle C that we don't know, then I can do all this, subtract everything, divide, and then do inverse cosine. A few extra steps, but it's doable. Either one, you know. And then whatever I call them, A, B, or C, it's always, you know, two sides and the angle between them. And then I'm either figuring out that angle between them if I know that side across, or, you know, so you potentially could know all three sides and no angles. And whichever angle I'm calling angle C, that's the one I'm solving for. Or if I know two sides and the angle between, then that angle between, it's the side across that I'm figuring out. So this one also, we're going to prompt for input, side A, side B, and then either side C or angle C. All right, and so I'm going to solve for angle C and then have this code over here for side C. So if it's angle C that you don't know, so now side C, cast that as a float, and then I just have this, notice is a bunch of steps here. So I'm just going to call this step 1 because side C squared, and then I'm subtracting side B squared, I'm subtracting side A squared. And then, there we go. So then step 2, if I have these, then if we take a look at side B, I just am calculating this part here, -2 times A times B, which I just expanded as side A, side B. I'm just doing this part here because you see the first part, I'm subtracting these over to the left side of the equal sign. And then step 2, I'm just doing this multiplying. And then ratio C, I'm dividing step 1 divided by step 2. And then now that I have that ratio, I'm going to do arc cosine. And we know that that becomes radians. And I'm just going to do the conversion. Radians times 180 divided by pi becomes angle C. So in doing a lot of these steps, you know, that's it. Math is a bunch of steps. You can write each step in code, you know, come up with your own in-between variables. I think that works out. It kind of keeps it organized for yourself and for, you know, anybody else you might be sharing the code with, and you really see the steps. Because I probably could do all this all in one step. Now, Python code convention, we kind of pushed the limit on the last step, that we only kind of shorter lines. I don't want to have to side scroll to get to the end of the line. So Python code convention, if I did this, I'd probably be a much longer line of code. So I also like to keep shorter lines of code. But the other thing is it just works out. Just you're seeing each step, you know, these independent variables, these in between steps. There we go. So now let's take a look at side C. So let's say this is the one we don't know. So if that's the case, so we have angle C is my variable. All right, so I might even just keep this here, but let's look at it in between step here. So just checking the 4 spaces to make sure that we're still in here. So what do I have? I have side. Now, notice each of these, I have side A, side B, side C that I already know. So, we have side A squared plus side B squared minus 2 times side A times side B times math dot cosine of math dot radians of angle C. Now, I need to store that as a variable. Because now, given all this, this equals C, but it equals C squared. And then I could square root it. We'll see. I don't use just C as a variable here, so I could see. Let's see if we have. Yes, and you see it get this line. I'd rather a shorter line. So I'm actually just going to call my variable C2. And then down here, C2. So you can come up with whatever in between variable you have here. And then you have, there you go, angle C. Once I have that, then I do this the full side A squared plus side B squared minus 2AB times the cosine of angle C. There we go. And I know that that's C squared, so I'll just in between variable C2, and then I'm going to square root it. So let's take a look. Now, let's say it would be, if I would know AB, so let's say this is a 3, and it's side C that I don't know. So 3, 4, and then the angle between them, side C I don't know, but the angle is 90, and we'll make this a nice 3, 4, 5 triangle. Look at that. There we go. And once you have this code, you can test it, apply it to a bunch of other triangles that you might know. There we go. So now we're building these, and remember, if you've been going through other parts of the course, this, hopefully it's enough of a review and extra practice, and make sure that, you're even better at writing all this code. And we're building upon, these situations. Okay, right angle, but I don't need a right angle. I have my situation for law of sines, my situation for law of cosines. And then the next part is, well, how do I calculate the area if I don't know the base and the height? So we take a look at this. Here's this new area formula. Now, notice how similar this is. 1/2 AB. Now, if this was a right triangle where A and B were the two sides, the angle would, and the angle C was a 90-degree angle, they would be the base and the height. And it would be area equals 1/2 base times height. But if that angle is anything other than 90, then that changes, but this is the exact adjustment. AB times the sine of angle C. Because if angle C was 90, sine of C is 1, and then there we go. It becomes the area. But that changes proportionally as the angle changes. So look at that. But also, what you need to know is very similar to the law of cosines. Two sides and the angle between them. So I'm just going to plot here, side A. In this case, there's no other options. It's the area that I don't know, but I would know these three things. So I'm going to prompt for side A, prompt for side B, prompt for angle C, and then just write the formula there. So 0.5 times side A times side B times angle C, I expect it to come in as a degree, so it would be math.sine of math.radians of angle C. And there we go. And this one, I will do other ones other than side B, and then if that's 90, there we go. All right. Oh, that's interesting. So there you go. And that is the area. We did write the code. And I will change that for you because that is the code to write the area. So now we're going to put this together and solve any triangle. So, depending on what side we have, what sides, what angles, our goal is that if I know any three things about a triangle, I can figure out the other four things, including the area. And so this, as we put it together, draw the sides. So this is, I'm just going to draw a triangle, not drawn to scale, but here's a triangle, and I'm going to label the sides and the angles, and then I'm going to show the options. What do we know? 2 sides and the angle between. Do I know 3 sides? Do I know side, angle across, and another angle? Notice side, angle across, another side. And you see the different situations. 2 different ways to work with law of cosines, 2 different ways to work with law of sines, and then other trigonometry, a right angle and 2 sides. Pythagorean theorem, a right angle and a side and another angle. Other trig functions. And so we're going to keep all that, display the triangle and the options, and then here are all the variables we're going to solve for. There we go. Angle A, there we go. All these. And then if you get option 1, then here's what you're going to do. Input. So if option 1, then it goes to this, input side A, and then you're going to complete this code. Well, you can, if you want, then go back and copy the code from this. So option 1 is, do I know 2 sides and the angle between? And you can absolutely go back to the law of cosines and we know the side. So I know 2 sides and the angle between. I'm going to solve for side C. So we're going to do this. And all right, so do I have, if I have side A, we have to prompt for side A, side B. There you go, side A, side B, and side C and angle C. So this is, just an example of being able to reuse your code, but then make sure it applies to this. You don't ever just want to copy and paste. You want to see. So, so in this one, we did side B. I'm going to make it a capital letter. I'm going to make it an equal sign. And I am also going to apply the new line so that this is going to be consistent. And I don't need this because from picking that option, all right, and I know I don't know side C. All right, so again, we're side A, side B, and then angle C. And we're storing it as those variables that match up with this. Again, the little things, you don't want to misspell your variables. So now, if I have this, now I have this extra step here, which that's fine. If you didn't, if you didn't feel like rewriting it, you don't have to. But remember, since I already know this, I can keep this. I can make it more consistent here, and I can change that to a float, which means I don't need this. And then that means I definitely need to make sure that that variable matches. And now we figured out side C, which the variable that I want has no underscore. And there we go. If you want, you can delete this. And so what we have here is, I now will take that input, and then I know now side A, and I know side B, and I know side C. And we'll come back to this. But then what I can do is, after here, I can, so angle A, angle B, and angle C, and area. There we go. So then we'll add the area variable up here. And down here, we don't need angle C again because we already have it. So we can delete that from here. And there you go. You have an example of what we would do with just that situation. And filling in the rest of this, I'm not going to repeat that it was in the other video about solving any triangle. And there you have it. Displaying a triangle, getting different inputs, and no matter which input, you would have a complete example here of starting with that, how would I get every side, every angle in the area? And then starting with something different, how would I get every side, every angle in the area? So now let's look at just a refresher on the look of a sine wave. So remember, sine comes the word sinuous, which means curvy. And so we're just going to run this to show a graph of a sine wave and how we define the array of x values. Remember, the graph is in radians, so I'm going to go from 0 to 7 and 280 points. That should be plenty detailed enough. And then the y value is just sine of x. Both of them, importing numpy, importing time for no major reason there. And there we go. Just setting the figure size, and here's the angle measure. So let's run this, and that's it. Just a refresher on the sine wave. Y equals the sine of x, and then we see the graph here, angle measure in radians, and we go from 0 up to 1, down to -1, and there we go. So let's talk about how that relates to sound. And of all the different transformations we can do, I'm really just going to focus on two of them here. A, so that's our multiplier, which would give the amplitude of the wave, and with sound that would represent volume. And then B, so as B increases, then the wave gets more compressed, and that would represent frequency. So just some examples here of setting up sliders for, notice I'm defining this function, and I just call it f just to make this part short so that this line doesn't get too long. But I'm going to define the function and do all the graphing in the function. I'm going to import inline, import interactive, and then we'll see that I just defined it like this. We'll show you here. The sliders always default to right in the middle, but then we can see if I change B to be a smaller number, and if I bring it down to 1, that should be a normal sine wave. We're going through, remember, radians, so 6.28. There's your full cycle, and we go through a little more than twice. So just looking at B, as B increases, and then you can play with these sliders here. You see it gets more and more compressed. There we go. And A being the amplitude, there we go. If it's 1, then you see it goes up to 1, down to -1, our normal. This would actually be our normal sine wave. I just decided to increase this a little bit. And then as A increases, notice the zeros stay the same, but the amplitude increases. And you can play with this and change these values here. I mentioned the sound reference. A lot of times then frequencies are much higher than this. 20 at the very smallest number, but we're talking usually in the hundreds. And, it can go up into a few thousand, and that would be, the range of frequencies we would normally hear in music. But there we go. And with this, now this one, I didn't make sliders. I just I noticed some of these here at the end, just some things to tinker with so you can see, change the frequencies. I did make the frequencies pretty high here, and they would represent a couple frequencies right in the middle of piano keys, if you're looking at that. All right, defining the array for the x values. And here I'm just graphing two things here. So the frequency 1 times x and frequency 2, not changing the amplitude, just changing the frequencies. And I'm going to make the title of the graph illustrate that. So, yep, there we go. And it's pretty cool if you put these frequencies together. Now, notice I didn't even add frequency. You have these frequencies, and what I did here is I'm plotting y1 plus y2. So if you heard both of these frequencies together, and even though it's a little bit muddier than your normal wave, at this scale you can see that it still kind of follows its own wave here. And that's what makes harmony. Whereas if I changed this to 400 and let's say 31, some awkward number, there's some values you can tinker with this. There's some values that would be you know, that make better waves than others. So you can tinker with this. You could even rewrite this and make it all sliders. This is all that you needed to do for this. I wanted to give you some chances to combine these frequencies, and I just put them in changing the code instead of a slider. I think that works out better for these higher numbers. And there you go. You can see how some of these combine. Yep, and you'll notice, which numbers and which combinations produce better patterns. All right, so pretty cool. Then this all leads up to the certification project, bringing back some of the things that you were doing before. And this is creating, for the certification project, I have built an analog stopwatch. Though what we have is you already have the video and the assignment of creating the whole clock. So this one I just said build a stopwatch, and that would just be the second hand cycling around, but you already have the project that looks at the entire clock, hour hand, minute hand, and second hand. So really this whole certification is a little bit of a review, a little bit of a culmination, cumulative review of some of these topics so far and some of the projects. And going through this, you can borrow code you've already written, use some things you've already done, and that should strengthen your knowledge and understanding of all of this. So by now you would have, completing all of these, you should have a good understanding of, trig, sine, cosine, but all the other trig values, degrees and radians, graphing, solving any triangle, plotting points for a unit circle, plotting points for, a stopwatch, and all sorts of other things. So hopefully this is a good start, and we have more to come.
So let's talk about The Matrix. And yes, The Matrix was a math movie because it was all about what you can do with special effects, which really are algorithms and math at the core of it. And the structure of that's a matrix. The structure of a lot of things we can describe as a matrix. And the root of a lot of other words are related to the root of the word matrix. Matrix, structure, matter, material. The French word maître, the English word matron. The core, the fabric that we're using as building blocks. So in math, in a lot of things, we want to translate things into a matrix so that we can do some math to it. And that's what we're going to get into. Some of the things that we've been doing, we're going to show how to do some of these with a matrix. So let's start with how we describe the matrix. So this is a 3x2, which is, it's always rows and columns. So if this is a 3x2, so then it's 3 rows and then 2 columns. And then this one, by contrast, is a 2x3, 2 rows and then 3 columns. So we'll see how we can create a matrix and call them using code. And you would define row, row, row. That's how you would define them when you're setting them up. So if we take a look at a 3x2, 2x3, I can name these. I'll call this one matrix A, call this one matrix B. And if I wanted to call one element from a matrix, I'm going to use row and column as my address. So I would call it B, and then a little subscript, let's say, row 1, column 2. I'll usually put a comma there, and row 1, column 2, so then that's a 2. And then that's how I can call, each unique element in a matrix. So, setting them up setting up this matrix, and we'll look at how to do this in code too, but this is how it would display. Then what else do I want to do with it? Well, the simplest thing we can do is we can add two matrices. And yes, that's the official plural, matrices. So if I wanted to add these two, they need to be the same dimension, and then I just add each element, and then the answer is in that same place. But these are not the same dimension, so I could not add these. Now, we'll get to multiplying. I actually could multiply these because that's a whole different situation, but we'll get to that. So if I wanted to add two, well, I couldn't do this, but let's just say I have another one. So it would also have to be a 3 by 2. I'll erase this. So I could have another matrix, 3, 4. Let's just say I had these two and I wanted to add these two. These I could because they're the same dimension, and then my resulting matrix would be those same dimensions. And so in the same place, 1 plus 3 is 4, and I would add like that. 2 plus 4 is 6. There we go. 3 plus 5 is 8. 4 plus 6 is 10. 5 plus 7 is 12. And 6 plus 8 is 14. And then that would be my answer. That would be the result. So one way to match up things that are corresponding, and if I want to add these, I would use a matrix. And we'll look at some other applications of these, but a lot of times it's really useful to have a matrix. We can even have a Python array and convert it to a matrix pretty easily, and convert from a matrix to an array, so that some of the tools for an array are more useful, some of the tools for a matrix are more useful, and we'll use both. But we'll get into some other things, solving equations and graphing and all kinds of things with a matrix. So let's take a look at how to do this with code.
I just had this to display to show you. I made each of these an independent variable. A11 because we're in matrix A, row 1, column 1. A12 because we're in row 1, column 2. A21 because we're in row 2, column 1. A22 because we're in row 2, column 2. And each of these is its own variable, and then B, same naming convention. And this code cell, I just made it that we have a place here to enter in all these values. And we're going to do other things with it. So this you can just run and, they're all entered in. So looking at these, if I was just going to add or subtract, I would just add the corresponding parts. A11 plus B11 would be C11, and, still go in that top left corner. So when we add these, then I just wrote out the code for each step so you can see all the corresponding parts. And I had it output, I'll run it again so I just had it output that this would be the resulting matrix, 6, 8, 10, 12. And there's other ways we can format that output, but just to show you the steps in setting up a matrix. And adding two matrices, that's the most basic thing you can do. They have to be the exact same dimension so that this works. And next we're going to look at multiplying and doing some other things with a matrix.
So let's talk about how to multiply two matrices. And multiplying, unlike adding or subtracting, they don't have to be the same dimension, but order does matter, and these two dimensions need to match. So if order does matter, and so if I multiply this times this, then these inner numbers match, which is the number of columns here and the number of rows here. So then the resulting matrix will be these outside dimensions. So my resulting matrix will be a 2 by 3. We're going to fill that in as we multiply. So then why do these need to match? Because what I'm going to do is I'm going to multiply everything in the first row times everything in the first column, and then add those together. So we see if those match, it's kind of like it turns this times this. So what do we have here? We have, I'm going to do 1 times 1 is 1, plus 2 times 4 is 8. And so that's everything in the first row, everything in the first column is 9. And then that answer goes in the first row, first column of my resulting matrix. So then if I get a 3, if I go the first row, second column, so then if I do 1 times 2, I'll erase this. We'll put all our in-between work right here. So if I have 1 times 2 is 2, plus 2 times 5 is 10, so then that's 12. And so that was in the first row, second column is 12. And we see it proceeds like that. Everything in the first row, third column, 1 times 3 is 3. And then 2 times 6 is 12. So then 3 plus up, then that's 15 in the first row, third column. And so we see how when this goes, then this number here can be anything. And then we see how then the result of that could make a matrix that's, whatever dimensions. Then if I do the second row, first column, so then if I do 3 times 1 is 3, 4 times 4 is 16, so then we have 19 here. And second row, second column, 3 times 2 is 6, and then 4 times 5 is 20, so then I have 26, and second row, third column, 3 times 3 is 9, and 4 times 6 is 24, so then I'm going to have 33 here. And there we go. So as we see, it becomes a lot of small multiplication problems, and we're going to look at how to do the code for this. In one time I'll show you how to set up the code, like even just writing out all these multiplication problems based on, input, storing them as variables. But then we'll look at some other ways we can multiply two matrices without having to even write out the code for each of these in-between steps. So we'll look at this, and then we'll look at some applications of multiplying. One of the applications, and that's why I picked these particular dimensions, a lot of times we can store XY coordinates as, first row might be my X coordinates and second row might be my Y. So like the XY pair might be this, like 1, 4 as a coordinate point. And then you could have a matrix of 2 by however many points. And having a matrix that came first, multiplying that does different transformations, like rotating it around the origin or things like that. So we could have, that, and then we would store this, a 2 by 2 for transformation, a 2 by whatever for all the points. These are some applications we can get into. But here's how, the setup of matrix multiplication, and let's take a look at how to do this in a few different ways with code.
So now here's how to multiply two matrices. And I just have to display here matrix A times matrix B equals matrix C. And we're going to just enter all the values in. We're going to do a 2 by 2. So here's all the values again, just some basic numbers so you can see. And I'm going to show you a few different ways to do it. So the first way is these are the actual steps. And remember then, it's everything in row 1 times everything in column 1. And the answer is in row 1, column 1. So you end up doing A11 times B11. You're doing that multiplying, but then A12 times B21. So we see these, you're doing that multiplying, and you add them together, and all that comes together as C11. So we see how we're building this, all these steps doing the multiplying so you can see that, this works. And I'll output, no special formatting, just outputting these, and that's going to work out just fine. I'm going to run all this at once. So besides doing that, this is the same matrix. I still have it referencing all the original input values, so we don't have to change that. But if I just make each of these an array, so I can say, each of these, so row 1, row 2, and I can make these an array, and this is why we imported NumPy. So I made this capital A, capital B, referencing each matrix, and then if I'm multiplying, A dot B, put the period, then write out the word dot. So this is A times B, and then we're going to print that answer. And that works too. We'll see this in the output, but also I can actually just make them a matrix. Also in the NumPy library, np.matrix. And notice it's actually the same dot formula, E dot F, because I just made each of these. So, and I made each of these its own matrix, even though we're referencing the same numbers. So we have it, output, writing the code by hand for each step, using this as a NumPy array or np.matrix. And when we run this, we're going to see 19, 22, 43, 50, same answer each time. So each of these will work as different ways to multiply a matrix. And we'll see some examples in a little bit of why you would do each way. Maybe you have different reasons or different situations where you would use just, writing the code by hand or an array or a matrix. But math-wise, they work out to be the same answer.
So let's take a look at a couple things we can do with a matrix. And both of these, the determinant and the inverse, you need a square matrix to do this. So 2 by 2, 3 by 3, 4 by 4, etc. So in doing this, the determinant gets the matrix to one number. And then one of the things we can do with that is we use the determinant to get the inverse of the matrix. Now, when we get to the code, this is going to be, like one simple step, built-in formula, inverse or determinant. But I'm going to show you the steps to get to this. With it beyond a 2 by 2, it actually gets even more involved, but this will illustrate the point. So let's get the determinant here. So the determinant is you're going to multiply each of these diagonals and subtract them. So the determinant is going to be, in this case, 2 times 4, and then 4 times 6, or 2 times 8, and then 6 times 4. So we have 2 times 8 is 16 minus 24. So we see, that's how we get the determinant, that minus that. If it was a 3 by 3, it becomes even more steps and you carry over the other 2 columns. But there we go. So what we have is, so if the determinant then is -8, we might use that for some things. There's some ways we can boil down a matrix to a determinant for other things, encoding and decoding, all kinds of things. So here we have this, but we're going to use it to get the inverse. So then once I have the determinant, then 1 over, I'll put the negative here, 1 over the determinant times that original matrix, 2, 4, 6, 8, then that gets you the inverse. So we're just going to take this and distribute that. So 1/8 times 4. So I'll just reduce that fraction. So that's -1/4, 2 over 8. And then there we go, 1/8. So that's -1/2. And there we go, 6 over 8. So that's -3/4, and 1/8 times 8, so then that's -1. And it worked out nicely to fractions. I decided to put them as fractions, but a lot of times they're going to be decimals. And this is another thing where I pick numbers that work out nicely. Very often you get decimal numbers and quite a few decimal places. So what you would do is you would store each of those values as a variable. That just works out better. But there we go. So now this is the inverse. So this is the inverse of the matrix, and we have these. Now, one of the things, if I multiply a matrix times its inverse, I should get the identity matrix, so which is 1, 0, 0, 1. So I would get the identity matrix. Then this would be the result if I multiply the matrix times its inverse. Or if I multiplied anything by the identity matrix, I get the same matrix. But there we go. So we often use the inverse we can use that for solving equations. We'll get into how we can use that application. But there we go. Here's how we get the determinant and then the inverse of a matrix. And then now as we look at it, how to do this with code, we're going to find out that this is even easier because we have some built-in functions. So let's take a look at this with the code.
So here's some other matrix operations that will be useful in different situations. One of the things would be the inverse of a matrix. And remember, we really officially don't divide matrices, we multiply by the inverse. So if I'm going to build upon this, I already made these matrix A and B, and I can run this again. So there's matrix A and B, and now that that's stored, and remember, with Colab, that those variables will be active and available for maybe 20 minutes, a half hour if you don't do anything else with that code cell. So we can build upon that if I get the inverse. Now notice within NumPy, we have linear algebra within that, and then even that dot inverse. So I can get the inverse of matrix A. And the determinant tends to be more, messy decimal places, so I will round that. And the determinant is a way to get the matrix down to one number. So, and we're going to, that's actually used, if you did this the long way, that's used in the inverse. But also, some other things you might use the determinant for. So I can just round that. And then matrix multiplied by its inverse. So now that I have the inverse, I'm going to use R dot A dot. And then what am I multiplying it by? I'm multiplying it by the inverse. And I'm going to print that. And the determinant will be one number. So I can just round that. But I can't use that round function with a matrix. I have to use np.around. So that's how I get the rounding of that entire resulting matrix. So if I run this, so we see still referencing matrix A, I have the inverse here, and then I also have the determinant, and then when I multiply matrix A times its inverse, this is what we expect to get. This is, remember, the identity matrix. So if I multiplied this matrix by any other 2 by 2, I'm going to, it comes out as that other matrix. So multiplying a matrix by its inverse gives you the identity matrix. Just like multiplying a fraction by its inverse equals 1. Multiplying a matrix by its inverse gets you this identity matrix. So just some other things within the NumPy library, things you might want to do with a matrix. I just want to throw in here another way to multiply. So here I created these just right here, matrix C and D. And just to show you, you can output what type they are, what object type. And here's another way to multiply these. So instead of, like we did here, A dot and then the second matrix in parentheses, you actually can just do NP dot and then each matrix in parentheses, CD. It works out the same. So here we have this matrix, both of them, what class numpy dot matrix, and here's the product, the dot product of 2. And remember, as I set this up, that this was a 2 by 2, and then matrix D was a 2 by 3. So the result's going to be a 2 by 3. The order does matter, and those middle dimensions need to match, and then the outside dimensions are the dimensions of the answer. So there we go. Another way to multiply these. Sometimes this might be more useful, and this is also just showing, what type of object these are. All right. More cool things we can do with the matrix, and then we can make use of some of these things in other operations. All right, next we're going to apply the matrix operations and solve some problems.
So let's talk about reduced row echelon form of a matrix. But to get to that, let's talk about each part of this. So first of all, echelon. Echelon is a word beyond math that means levels of command, potentially rows or status. And in military formation, echelons are rows where each row extends out a little bit beyond the one in front of it, almost like you picture a triangle. And so that echelon, we can see that, level, status, and start seeing how this can apply to a matrix and rows. What do we want to happen in these rows? So then we get, echelon form, but echelon form in a matrix has specific rules that, if you have a row of zeros, that has to be the lowest row. If, you have, sometimes people say the leading coefficient should be 1, but sometimes people say that, that rule doesn't have to apply. And it's really about how the leading coefficients get to be, further to the right of the other ones. We'll see how this plays out. But that's kind of like where the idea of echelon form comes in. Then, specifically to a matrix, we have row echelon form, which again follows that there's going to be a leading coefficient of a 1, and then there's going to be that leading coefficient of a 1 in the next row is going to be over, not in the same column. That we get into row echelon form, but that limits what the matrix can look like. We're going to be really interested in building upon all that to get to reduced row echelon form, which gets us to a unique matrix where combining what we've been thinking about, in terms of like the definitions of all these other words, reduced row echelon form is going to have our leading coefficients of 1. It's a unique matrix that will give us the answer to our question. And before we look at what that final form, let's look at how we get to that. And then it will all come together. So we have a matrix, we have a system of 3 equations here. So we have 14x plus 11z equals 3. Now notice this one doesn't have a y value. The next one, 22x plus 25y plus 4z equals 7. And then negative 12x minus 34y minus 3z equals negative 4. So I can put this matrix, all these coefficients and what's on the other side of the equal sign in this augmented matrix. And we say augmented because sometimes we can put this as one matrix, a 3 by 3, and then as another matrix for everything on the other side of the equal sign. It is possible to do that. And then, that's another way to solve it. So this augmented matrix, now I have this, and I can use reduced row echelon form to solve this. Now, the beauty of this is that's one function, in math, in a lot of calculators, and certainly built into Python. So what that does is that's going to give us 1, 0, 0, and then the answer. 0, 1, 0, and then the answer. 0, 0, 1, and then the answer. That's the idea, that this becomes this reduced row echelon form. And that's follows all these definitions. I have a leading coefficients of 1, and each one is to the right of the row above it. And so then whatever comes in this last column ends up being the answer to our matrix, which is really cool how that can work. So that's what we're going to do for reduced row echelon form. We're going to look at how to do this with code, but this is kind of, what our situation would be to set up the code. I'd have a system of equations, 3 variables, set up this way so that it's always x, y, z equals a number. And then notice the missing y value, I need that 0 as a place value. So this would be our situation. To get to reduced row echelon form, I would have a system of equations, put that in the matrix, and then I would use reduced row echelon form to get the answer. Now, if you didn't have the computer to do this, the way to get this is essentially all of the different substitution, elimination, all the different row functions that you would do to gradually solve this equation. Some substitution, some elimination, combining rows. So it would be very tedious, but it's doable. But here we have, if we have it in this form, it's going to be one function, boom, 2 seconds, and then solve it. So let's take a look at how to do this with code. We want to see, this would be the setup of what our situation would be, and then we get to the code. So let's write some code to use reduced row echelon form.
Here's how to solve a system of equations with a matrix, and I like the reduced row echelon form the best. I feel like it's just really straightforward. So that's the way we're going to look at it here, also in the code. And in addition to that, we're going to look at how we can convert. We were looking at np.array or matrix, and I want to show you here we're going to convert from one to the other. So I just put this in here. I'm going to create an array. So right here, I'm going to create a matrix as an array, and then I'm going to create a matrix from that. So I have the array, and then I'm going to create a matrix. Now I'm importing NumPy. I'm importing SymPy, but I feel like I've run this without importing that, but I still have that up there. So right here, we're just going to show you that when we run this, that this works. And also notice just an interesting print statement, the braces here inside the quotes, and then dot format the matrix there. So there we go. Create an array, matrix from that array. And I just commented this out because I'm going to show you the other way. But you could have just started with a matrix. But the reason why I started with an array is to show you that you can create a matrix from that, and we're also going to convert it back to an array. So it works both ways. You can do this, as I may have mentioned before, maybe some situations you'd rather an array, some you'd rather a matrix. For a lot of the matrix operations, you want the matrix. So, here we go. You can convert from one to the other, though. And we are going to do the reduced row echelon function. So it is a matrix, and it's going to be m.rref. Now, that's going to give you the reduced row echelon form. Then I really wanted to split this out. And notice the matrix is the first element. So every one of these, it's a 2-dimensional array, but you have the first element is 0, so my x value, and this is going to make sense when we see the output, is 0, 3, my y value 0, 7, and my z value 0, 11. And so I created those, and then we're going to print, x equals y equals z equals. And this is the output that I like. I want to show you, how we get to that here, but then we're also going to print out the echelon form so you can see where this comes from. So we run this and we have, here's the matrix. So we see, it formatted there, and it will just give you this matrix here. Same matrix, and we see, there we go. It was we converted it back to an array and printed it that way. So that's where we get this form, which you may or may not want that form. And then now we have the answers, but I'm going to skip over that. Let's take a look. Once we get that down to the reduced row echelon form, so you see this whole matrix was the first element. And remember, it would have been, x, y, z equals. So you see the 1 here, x is 1, and then y, the coefficient of x is 1, and the coefficients of y and z are 0. So x equals this number, and that's the same that we got here. And you see the coefficients again, y, the coefficient would be 1 and the others would be 0. They would drop out. So the y value is this, and then 0, 0, 1, so the coefficient of z, and there's z. And given that, we see that the elements are 0, 3, 0, 7, 0, 11. So it's not row and column as you might expect, but there we go. So we get these, and if you're ever working on this, you can, output this form and then, tinker with, what elements you need to put in here just to be sure. But there we go. So that way, if you have a system of 3 equations with 3 variables, you can, put that into a matrix, reduce row echelon form, and then output your answers. And, you could output these because then these would be stored as those variables if you needed to use them in something else, or you could output here and you can see, what it would look like. So that would be a way to solve any system of 3 equations, 3 variables, and then we're going to look at a specific example next, quadratic, and developing a quadratic equation. So we'll take a look at that next. So here we're going to look at developing an equation from 3 points and using a matrix to do that. So I'm going to pick a quadratic because linear, we just need 2 points. Quadratic's complex enough to demonstrate this. So if I have the standard y equals ax squared plus bx plus c, then here's 3 points. Let's say I have these 3 points, and I want to find out, I know this is going to be a parabola going through these 3 points. What's the equation of that parabola? So I'm going to plug in the first point, xy, and we see plug in -1 a couple of times for x, y is 0. Then I'm going to simplify it, and we get down to this. I'm going to go to the next point, plug in the second point. There we go. 1, y is 6, simplify it, and we get to this. And I'm going to plug in the third point, 2, 12. There we go. Simplify it. And so let's put all these 3 together. Notice and it is important, I put the equals on this side, so I always have A, B, C equals something, because all of those coefficients become the augmented matrix, and augmented because I include what's on the other side of the equal sign as that 4th column in the matrix. There's other ways to do this. make a 3 by 3 with just everything on the left side and another matrix, but this is an augmented, and I just happen to like this method. So we see all the coefficients from the first equation, 1, -1, 1 again, 0 on the other side of the equal sign. All the coefficients become our matrix here. So, and I'll just call it matrix M to give it a name. So if I do the reduced row echelon form of that matrix, abbreviated RREF, and then, of matrix M, this would all appear at one time, but let's look at it one row at a time. So it always has to be A, B, C, and then the number on the other side of the equal sign. So the only coefficient with a 1 is A. A must equal 1. And then the next row, B is the only coefficient with a 1. B equals 3. And then C, the only coefficient with a 1. C must equal 2. So A equals 1, B equals 3, C equals 2. We see that nice pattern of diagonal ones, and then this last column gives me my A, B, C values. And then the full equation is y equals x squared plus 3x plus 2. We just put it in that A, B, C. And there we go. 3 points, put it in a matrix, reduce row echelon function, and we can develop an equation. So let's take a look at how to do this with code. And we're also going to look at the patterns that we did so that we can just set it up once, and then whatever number shows up as, the XY values of these 3 points, we see exactly how to then plug in 3 points and do the rest automatically and output an equation. So let's take a look at how to do this with code. So now let's apply this matrix reduce row echelon function to developing a quadratic equation from 3 points. So here's how I would take the points, and each of these, x1, y1, x2, y2, x3, y3. So these would be the 3 points. And that's going to be enough information if I have any 3 points, because if we take a look, so here would be the standard quadratic equation. And there you go, ax squared plus bx plus c equals y. So if we had any of these 3 points for the first point, we would plug in x1 here, x1, and then c would still be there, and then y1. Second point, we'll plug in x2, and then y2, and then third point, x3, and y3. And then converting these 3 equations into a matrix, so we see that we're going to solve for a, b, and c. So given those variables, the coefficient for a is going to be x1 squared. The coefficient for b is going to be x1. The coefficient for c is always going to be 1. And then y1 on the other side of the equal sign. Same thing for x2, y2, x3, y3. So that would be the matrix that we'd be using. And I just have this set up here, import numpy, and here's just a place where we can enter in any of these. I picked a couple, points here so that we can take a look. So you would enter in the points here, and then define this matrix based on those points. So here's the first row of our matrix, and then the second row, and the third row. So we're creating all these as a matrix. Points into this matrix, and from there, m.rref. And so I just made the variable name the same. m.rref is the function. I just made this variable name. And given this, m_rref is our answer. So now I'm going to take that, and the x value would be at this part, and I'm going to round it, store it as a. The y value would be in this location, round it, store it as b, and the c value. So there we go. A couple steps, and I'm going to print out A, B, and C. Now, I could do something else with this too, but let's just take a look. So row echelon form. Let's run this. And so my first print statement would be these answers 1, 5, and 6. Great. And row echelon form, just so you can see it to compare, then our coefficient is 1 here, x. So x is 1, y, there's my coefficient, is 5, or sorry, A, B, and C. A is 1, B is 5, C is 6. And we always could add another print statement if we wanted to. Knowing that the goal of this was the quadratic, we could have, A and then x squared. I'll use the Python notation here, x squared plus, and then I would have b and that would be x, keep that space, plus, and c. There we go. And a lot of times we put the y equals in front, so I might do that. Y equals. There we go. So we could take this now that I have a, b, and c, and I could just print out that equation. Y equals ax squared plus bx plus c. And there we go. So that works too. And you see then, now, this quadratic, if I have 3 points, I can figure out the equation. And that's kind of what we want to do in math and applying this to other things. Can I have just a few points, in this case 3, and then develop an equation that would go along with that? All right. We can apply this matrix and RREF to some other things too, but there we go. Developing equations from 3 points. A little bit about encoding and decoding. And even if we're not using a matrix, so Python has built in, if you have any character, so you can bring in a string and then run through each character in that string. If you get any character, we have built in ORD, ordinal. It turns that character into a number based on the ASCII code, American System of Computer Information Interchange. So that's the standard that, you can look up these tables so you can see, every letter, capital, lowercase, some with accents, some numbers, symbols, punctuation, all that. Every one of those corresponds directly to a number. And then you can convert that to the standard number, and then the other function is CHR, which you can take a number and then convert it to a character. If you had a number that's out of range, it'll give you an error, but you can type in the number, character 65, and then it's going to output a capital A. So we're going to use that in the code. I'm really going to show you how to prompt for these things, get that string, and then convert it. And the cipher, or the code that we're going to use to transform it, it's going to be a pretty simple just shift. I'm going to get that number, I'm going to add something to it or subtract, and there we go. We could take this and convert these to each to a different matrix. That's another possibility, and maybe in another video we'll explain all the levels of converting using a matrix. But for right now, I wanted to show you how to do this, and then you can modify this or expand on this on your own, and create something you can send a secret message.
Okay, so let's take a look at it in the code.
So you can use a matrix to encode and decode messages, and you'll see in here where you could potentially put a matrix, but I'm going to show you this even without a matrix, but we're going to use some math. All right, so the only library we need to import really is NumPy, and here's some comments here. So we're going to get the input, and this input, prompt for input, remember it comes in as a string, so I'll store that as in_text. And then I'm going to set up this empty array here in_numbers. And what I'm going to do then, I'm going to loop through all this text that comes in. So for A in text, so then what that's going to do is every character from that string, one at a time, I'm going to go through and here's the inner function. I'm going to convert that to a number. So ORD converts everything to a number based on the ASCII code. So capital A is going to come in as 65, etc. So one at a time, convert that to a number, and then I'm going to append that to our array here. So then I will have this array of numbers. Nice. Then I'm going to encode this. I'm going to have this blank array of encoded numbers, and I'm going to loop through that. So looping through every element in numbers. Now, I just put this comment here. This is here's just a simple example, but this math can get more complex. And this is where you could potentially put an array. So, all right, here's the cipher. I did just a basic shift. And the reason why I picked 37, so capital A is going to come in as 65. You might have a couple symbols before that you might use, but most of the text is going to be 65 or more. And so adding this gets it up to a 3-digit number. So everything that comes through should be a 3-digit number then. I could have added 35. I decided to add a couple more. So just a simple cipher, that's about what I would add, anywhere between 37 and you could have really big numbers. So, anything in the hundreds. All right. So anyway, this is the cipher, and all we're going to do is just each of those in the array, we're just going to add 37 to it and append it to our array here. And I split this up because then this, you could add something. You could do like linear algebra. You could do a quadratic formula. You could do anything you want to change this. I just wanted to do a simple example, but you could do anything you want in that math. And that's where this is really the only place where then a matrix, if you wanted to pretty much one at a time, you wouldn't use a matrix. 2 at a time, you might do some matrix multiplication, but we're not going to worry about that right now. And then I just have this that you're going to print out the encoded message. So that would print it out. Now, if you did this, you could run this, print out your encoded message, copy that, and then paste it anywhere. Whether it be text, a text message, an email, or anything else, and there you go. That's it's one little extra layer of encoded message. But there you go. You would copy it and paste it and send it to somebody. Now, on the other side, now we're going to decode, and we're going to prompt for input enter text to decode, and I'm going to store it as this variable encode. And this one, since I know that this is going to come up, the encoded numbers, you'll see that array, when you print it out, it's going to be each number separated by a comma. So here, we're going to split it at that comma. So now innum is an array. Each element then becomes an element of this array innum. But now I have to decode that. So we decode, and rather than an array, I'm going to have a blank string. So this string just starts out with a space called decoded letters. Okay, so now as we loop through that, remember they're numbers, but they all come in as a string. So first of all, the math of it has to be the inverse of the encoding. So if the other one I added 37, then this one I'm going to subtract 37. But first of all, I have to convert that to an integer. And I chose to do it in this step here, convert it to an integer, and then, the math of it, which is the inverse of the encoding. And I'll store that as a variable decipher, and then each of these, so decipher then, still, remember, that's still just a number. I converted it to an integer, and decipher is still a number, so then the opposite of the ORed is CHR, converts that number to the corresponding character. So we see that's, the encoding, convert the letter to a number based on the ASCII code, then do some math to it, and then here I need to do the opposite. I need to do the, convert it to an integer, do the opposite math to it, and then convert it back to a character. So then we're going to just, it's not an array, so we're just going to append our string here, that plus equals, and then this should be a string, decoded letters should be a string, which is the message, and then we're going to print that out, decoded letters. So we have both of them here, and you could always split these up into their own functions, but for right now, I'm not worried about that because you could always, you could just run this right here. So text to decode, secret message, hit enter, and then we see it prints this out. So if I was going to send this to somebody, I would highlight this and copy. Now I would paste that in a message. The other person would get that and highlight it and copy, run this program, enter text to decode. So paste that into here and hit enter. There you go, secret message. So interesting way. And what you would have is, so you could potentially, I'll keep this, but you could potentially then just share this, and that's what I'm doing. I'm going to share the code with you. This could, go to anywhere, and anybody could just change what math you do in this step. That's pretty much it. If you just change the math that you do in this step, and of course then it's going to match the math that you would do in the cipher, and somewhere else, as long as you and the person you're communicating with have that math that they're, the same math that they would modify this, hey, you could send a secret message. And this could be encoding and decoding, because if my main purpose is to decode and I don't care about encoding, I'll just say A, there we go, and then I would have this other message that I previously copied, and I could still then, just run that one step. That doesn't take long, and then still print this in here. There we go. So pretty cool. Always fun to make something that, sends secret messages and, applying some math to it. And as you see, the math and very much a lot of the converting from one thing to the next. There we go. And this, a simple cipher, but you can make it a lot more complex than that. So now let's look at using a matrix to encode and decode. And this is also encoding and decoding that works, because I tried a lot of things, so I'm bringing to you the stuff that works. And through that, I'll give you some hints on how you can modify this for your own encoding and decoding. So first of all, the matrix that I use, I'm going to store each message as a 1x2 matrix. So we'll see how we do that. And as a 1x2 matrix, then I'm going to have an encoding and decoding matrix that's a 2x2. And you see order does matter. So then when I multiply this 1 by 2 times the 2 by 2, my result will be a 1 by 2. And that's going to be the message again. So you could do this, certainly. And that 1 by 2 is going to be, grabbing 2 letters at a time, or characters, 2 characters at a time. You could absolutely do this as a 1 by 3 and, use a 3 by 3 as the encoding and decoding matrix. I feel like depending on how big the message is, that's some extra processing power. But you could absolutely do that. That's another way to do this. And then, use that. Certainly it would be more difficult to break the code. But I decided to do a 1 by 2, and this will also illustrate the example for you. So I use arrays, even though we're talking about a matrix and we're talking about matrix multiplication. As we looked at before, you can use an array, you can use a matrix, and you can convert from an array to a matrix. Well, for this stuff, I like the way it plays out with an array a little bit better. So that's why I chose that. We can still think about this as a matrix and the setup, but officially I am going to use NumPy arrays. So I import NumPy and I'm going to do NP array. So this is where you can add yours. I just have, 2, 4, 6, 8. I decided to do that. And, you can have whatever numbers you want. This is where, as you see, I call this one that works. I have a lot of other blocks of code where I tried some different things, and some numbers that you might pick for your array, the end result looks weird, and sometimes that might be, I don't know, maybe too difficult to break the code, or too easy to break the code because certain things jump out, or maybe certain things put you in negative numbers. Remember, even though we're not going to really see this step, but behind the scenes, when you do an inverse, you can't have a determinant that's 0. So, there's going to be certain things that work or that look better. Anyway. And so, but there you go. This is the main thing that you would need to change. And then everything else, see, this decode matrix just builds upon that. I'm just going to do the inverse of that other matrix or array. And yes, again, even though it's an array, the inverse is np.linalg. It's really the inverse. It's an array. We look like we're doing linear algebra, and it's really the same thing as, mathematically, it's the same thing as a matrix inverse. So some of this stuff is going to be the same here from when we were just doing the simple cipher, a little bit of a shift. Enter the text. I'm going to store it as an array. And then I'm going to get the order, use this function to turn each character into a number based on the ASCII code. So that's good. But now, knowing what I'm going to do with my array needs to be even. If it's not, it actually will just drop off the last letter. And who knows, maybe that's important. So what I did is, because our array is going to be a 1 by 2. So if the last one is not a 1 by 2, that might cause some problems. Well, it will cause problems. How severe, I don't know. But so I will do this, and then to make sure it's even, I just want to check if the length, the modulus, if that's not 0, then it's not even, and I'm just going to append this, which in ASCII code translates to a period. So maybe I don't have a period at the end of the sentence, and therefore I would just add one, and that'll make it work out. In code, some of this is similar. I'm going to, but here's what I have my array of encoded numbers, but here's what I'm going to have, because I'm doing this, 2 at a time to make that a 1 by 2 array or matrix. I have these temporary values that I'm going to initialize here as 0. And Pn, that's a variable I like to use for positive, negative. So I'm going to start out as -1. So all those encoded numbers, remember, it goes back to that variable in numbers. if Pn is -1, which it starts out at, then I'm going to store that value as, for B and in numbers as I loop through that, then that value becomes temp1. And then I'm going to multiply Pn by -1, so now it's positive. So there we go. The first time it goes through, that value becomes temp1, and then the next time, that value becomes temp2. And that way I go through and notice after doing all this, then I'm going to multiply it again. So that's kind of why I like using the 1 by 2. If you used a 1 by 3, you would have to go through and, you have to count up 3 times, and, other things become more difficult. But again, this illustrates the value, the point you can do here. So here's what I'm going to do. Then I'm going to turn this into, I called it the variable mat, like matrix. I'm going to turn this into an array as temp1, temp2. Boom, that's an array. And then I'm going to do the dot product. So I just called it encoding using the dot product, n dot. And I'm going to multiply, and remember, order does matter. So np dot dot mat comma encode. So that way here, once I have this, now I have the 2 values and store it as an array, as a 1 by 2 array, dot product, which will then also end up being a 1 by 2 array. And then I'm going to encode the first one. So that first one, encoded numbers, is going to be my array up here. And I'm going to append, that one. Notice item 0 and then item 1. So this is how we're going to do the encoding. Going through each character. There we go. Turn it into array, dot product multiplied by the encoding matrix, and then store it as this encoded numbers array. And then just to show, I'm going to print out the message. Now, if you're using this for an encoded message, what you would do is you could then copy that message and paste it in wherever you want to paste it. And you're going to end up pasting this. You'll see it's an array of numbers separated with commas. So then to decode, you would have that enter code to text decode, and you'd be pasting this. So then we would split it at the comma. And now in num is my array of numbers. So with that array of numbers, in decoding, I'm going to turn this into a string. So there's my string of decoded letters. It starts out with a space. And I'm going to do the same thing. I changed it a little bit just to make a different variable here. So pn, I just use the underscore here as -1, because now I'm going to take that. Remember, these come in as an array, and I want to make sure that I store it as a float number. So there we go. That for everything in that array, each one, I'm going to store it as a float. Now I go through again. If it's the pn is -1, so then temp1, and you see that this one I just used. This, it's within my loop, it's within my array, and I'm overwriting it, so I actually felt fine using the same variable. Because again, it's a variable I'm overwriting, and it only it exists here. So therefore, temp1 is dfloat, and then I'm going to multiply this, and then when I go through here, then temp2 is dfloat. All right. So now I have this. I've brought these numbers in, converted each of them to a floating point number. And the reason why I'm using the floating point, a lot of times it does work out nicely, and the numbers I picked, I made it work out nicely for integers, but that won't always be the case, especially if you tinker with using different encoding and decoding matrices. So I definitely want these as float values, not integers. So now these float values, once I have them both, now I convert them to a matrix or an np.array, temp1, temp2. I have that array. And like before, I'm going to do the dot product. And we see there that Matt, again, I'm using this same variable, but that's okay. I'm overwriting it every time. So Matt, and then decode. So now I'm doing the dot product here. Okay, so once I decipher that, I hope it's an integer. Sometimes, we might be dealing with a lot of weird variables and we hope it rounds correctly, but I still need to get that item, and I definitely want to cast it as an integer here. So there we go. And I just called that variable decipher. So now that that's an integer, my decoded letters, I take that decipher integer, cast it as a character, CHR, and I'm going to add it to my decoded letters string that I initialized up here. So you see, slightly different on the encoding. We start storing things as an array that I'm going to output here. Here, I'm going to put it all together as a string. So I get things as an integer, and then cast that as a character. Get the character that is associated with that integer. Again, this is again based on the ASCII code. That CHR will turn that integer into the appropriate character, and I just keep adding to my decoded letter string. So here's the next thing. The weirdest thing is I found that I use this. Notice how this is very similar. I have decipher here for that integer, for that one character, and then store it. And then I have decipher 2, which I'm going to get from item 1 because my array, item 0 and item 1. What I found, though, is that I need this rounding adjustment. It seems that this one seems to be, for whatever reason, consistently good. I haven't really had a problem with this. But this one, I do need to also round it. It just happens to be that seems to be the case. So I do that. I throw in that extra, I wanted to put that comment there. That's why this one's rounded and the other one isn't. I rounded it, again, cast as an integer. Now this is decipher 2, and then convert it to, that which is an integer, convert it to the appropriate character, and add it to decoded letters. So we see, bringing in, doing this matrix multiplication, and then getting this item as a part of my decoded string, and then the next item as a part of my decoded string. And this is another thing, these are different enough steps that, I'm not going to loop through this little part twice. I'm going to write the extra line of code. And then I'm going to output the decoded message. So pretty cool. And let's see it in action. So I hit Shift Enter instead of just clicking the button. Enter text to decode. There we go. Python is fun. There we go. And so we see this. What I would do is then I would copy all of this. And I would paste that somewhere that I wanted to send that message. But here I'm going to paste it here because then, if you got this message, you would copy it from somewhere and then paste it in here. And I'm going to hit enter. And there we go. Python is fun. There we go. So if I didn't have that adjustment, you see, fun, I didn't put the period there, but because this was odd, we have the extra period there. Because if it cuts it off, then, might be, there you go. Python is FU, that's probably not the message you were trying to send. So there we go. We have this. Now, I have this as 1. Just like I did with the other cipher, because if I'm running this to encode and decode, if I just wanted to encode something, just encode. I mean, I could take this. Now, I'm going to copy it here, just because. But if I just wanted to encode something and then send it, and I have nothing to decode right now, I could just type in, like some random number, 65. There we go. And, yep, it might be, yeah, that's very interesting. So I wouldn't have to, I just typed in 65 and it didn't do anything. Though I expected it to be like a period, but anyway, that's it. Or if I just wanted to decode something, then I could again just type in, I just keep thinking 65, there's all the characters before that, and then this is capital A. But if I wanted to just, text this, and you see it's odd, so it would give me two different things. So if I just wanted to decode something, I could just type in any number there and get that output. It doesn't matter to me, and then I will paste this in here. So you see, like, I didn't need to split this up as having an encoding function and a decoding. You might as well do both of them together, and then whichever, if there's one you don't need, then just enter a letter, or just enter a number, and then call it good. There you go, just encode. So this is a good, I really think it's matrix makes it interesting, because now you're taking two characters at a time and you're doing this matrix multiplication. The possibilities are pretty big for all these different matrices you could have. You could, if you really wanted to, also put a shift. Like once you get that encoded, you could put a shift. And if you did, I would put it here. I would do all the encoding, and then, like, let's say if I wanted to do this, and then besides that number, I would just want to add something. I don't know, add 10 to that number or something like that, or 50. Just I would do it there, and then at the end, I would do the subtraction right away. So you could do that. Matrix encoding is complicated enough, but you could also add the adding or subtracting. But I would do that after the multiplying here, and then just, add or subtract something. And then here right away, when you get the number, do the opposite, add or subtract. So these are some things where you can, that's why you can see all this code, what can I do to make a secret code? But then you see where you can make it your own. And, who knows, even if you keep it just like this, and the only thing you change is this, that's 4 numbers there that, whoever you're sending the message to would somehow have those 4 numbers, and therefore the two of you can encode and decode things. So yeah, seems like a lot of fun, sending secret messages. So there we go. Here's how to do it with Python and a matrix. So let's look at another way of solving a system of equations. And this one connects more with a lot of algebra methods that you might be familiar with. So I'm going to take this matrix, and I'm going to take this system and turn this into a 3x3 matrix of the coefficients on this side of the equal sign. And then it's that times a matrix of x, y, z, the variables, equals a 3x1 matrix of the numbers on that side. So this works, that we can create a matrix of all of our coefficients times the variable matrix equals this. Now, how we solve it, remember, if you're multiplying, you divide, dividing, you multiply, do the opposite to cancel things out. So I want to get the inverse of this matrix,
and multiply the inverse times each side. So when I get the inverse of this matrix, so remember, this is a 3 by 3, so we can get the inverse, and the inverse will be also a 3 by 3. And then when we multiply this by this matrix, which is a 3 by 1, then we'll see that we can do this because these dimensions match up, and then the dimensions of the result are going to be 3 by 1. It's going to be a 3 by 1. So what we end up getting is this matrix of the resulting matrix will be like, x, y, z equals a 3 by 3 matrix of our answers here. Pretty cool. So this is another way to solve it. I personally often use the reduced row echelon function, but this is just as good, just as viable. And for some other things beyond what we're going to do in this course, but you get into other, more advanced calculus, some matrix algebra, then you might end up using this inverse method, more often. So I wanted to make sure that we talk about it. But now let's take a look at the code, and we'll compare this also to the reduced row echelon function, how we do this in code, and then what the answers look like. So let's take a look at the code.
So let's look at doing this with code. Inverse matrix to solve a system, and I'm going to use the same numbers. So notice I'm going to make them arrays. I'm going to import NP. I'm going to import everything from SymPy. It's kind of weird that it just works out when I do that, even though it doesn't seem like I'm calling SymPy for anything. So I'm still going to talk about them as matrices, but I'm creating them as NumPy arrays. So here's the same, and we see, row 1 in brackets, row 2 in brackets, row 3. And notice this one are numbers on the other side of the equal sign. It's a 3 by 1, and so I'm just going to make, row 1, row 2, row 3. Each of them have one number in the brackets. All right, so because I'm doing this, then NumPy has that linear algebra, so np.linalg.inv to get the inverse of that array. And I'm just going to store it as m underscore inverse, and then the dot product. And so this function calls, two arguments. What am I multiplying? And order does matter. So I'm doing the inverse times a1. And then inverse times a2. Now, this second one is really what I need to solve. I just did this because I wanted to show that this should give you the identity matrix. Okay, so I'm just going to print this, and that's really the answer that I'm looking for. All right, and what I also have is the answers that I got from doing reduced row echelon function. It gave me those fraction answers, so I'm just printing out those, and this is fraction. So the print statement will combine these, or we'll do the math and actually output a decimal. This will also output a decimal. So we'll see them to compare. So this is what I'm doing. I did the dot product, the inverse times a2, and I get my 3 by 1 matrix of the answers here. And then to compare, so this one gave me 0.330, and the one I got before was 0.327. There we go. So, and then the next number is 6. So almost 0.003 off. There might be a rounding error somewhere, or just, but notice, this is about the comparison here. There we go. So the x value would be that, the y value would 0.014, and this one is correct to that many, but then the next number is a 7, whereas this one's a 1, so off by about 666 10 thousandths. And then here, negative 0.1443 and negative 0.1476. So again, off by a little bit in the order of, 10, in the order of the thousandths. Close. But depending on what you're doing and depending on how you're rounding, that might be fine. That might be as close as what you need to get. If not, it would be worth it to, try some different things and see which one really is, more correct. But there we go. So the inverse, and see, just printing that m dot, I have this that, there we go, m dot, and there we go. So I could, you see, create multiplying the inverse times a1, and that should give you the identity matrix. And I made this as two different variables, so maybe I'll just make this one m dot a, and then I'm just going to print here, print m dot a. There we go. Now, this is really the identity, because all these are e negative something. So I need to go up here and then say around, and that gives you the rounded. So notice we have the math function round, but this is around, and it will round every element in that array. Pretty cool. And so I just wanted to put that in there to show you that that's what we're doing. We get this array, multiply by the inverse, which gets the identity matrix. And so it would be the identity matrix x, y, z on the left side equals this matrix, which x is 0.33, y is 0.01, and z is negative 0.147. All right. Pretty good. So I just wanted to do another example here, connecting with solving the system of equations to get a quadratic. We can do the same thing. And I followed the same, using the same points here. I'd have, two x value, x1, y1, x2, y2, x3, y3. And just like we have here, I have the reduced row echelon function. And so therefore, I'm creating a matrix of these values. And then I'm going to do that function and then get that. So here we go. Now, if I do this, then remember, this is how I got these values here for x, y, and z, or for a, b, and c. And it's just one value here, so therefore I'm using the round function. So that we've already done, and so just using the inverse matrix now, I'm just doing the same values here, but I'm making it np.array for each. There we go. And just like we were doing before, therefore I'm going to do the inverse, there we go, of that array 3 by 3. And then I already have this written in. I'm going to round it. So just again, to comparison, you really don't need to do this. I just wanted to show you. But then I multiplied that inverse times that 3 by 3, should get the identity. And then the values, I multiply the inverse by the 3 by 1. So when we run this, with numbers like this that work out to nice integers or easily rounded, you're not going to see the same discrepancies. So, yep, A, B, and C become 1, 5, and 6. Identity, yep. And the others were 1, 5, and 6. So this is a lot of extra output just to show you, how some of it works. But there we go. So this is getting the answer using inverse. This is getting the answer using reduced row echelon function. Or maybe I have it reversed, but then and they're the same. So some of these become a matter of preference. There we go. But now we can see how to use an inverse to solve and write the code to do it. So let's look at a few more things with matrices, like transformations. Okay, so here's how to do a few key matrix operations with code. The only library we need to import is NumPy. And here I'm going to create a matrix. I'm just going to call it points because I have it in mind that these could be XY points. So np.matrix, and then here I have, there we go, row 1, row 2, row 3, and these could be XY points. So now I could just pull out one of these points and notice how we number these. Row 0, element 1, so that'd be a 2. And, because this is row 0, row 1, 2, there we go. I could pull out that one particular point. And then I'll also just print the whole matrix just so you can see that. Then let's transpose it. So I'm going to create another matrix called T points, and I'm going to transpose that original matrix, and we'll see what that looks like, because then I'm going to print that out, transpose, and then I'll print that matrix. And just for fun, we're going to transpose it back. So I'm going to transpose it back, and we see same np.transpose. So I can transpose points, and then I can transpose T points, and that will transpose it back. And then again, we're going to print this. I did make it another matrix called original points so that it doesn't overwrite that. So now at this point, I have 3 matrices: points, T points, and original points. So I can also convert it to an array, and this one I went back to the original points and converted it to an array. np.array, and then take that. And notice array has the same function, r.item, and there we go, that's 2, 1. So back to the original, so it's row 2, row 0, 1, 2, and then element 1. So that should be a 9. Then, still keeping in mind that these could be XY points, some of the things we can do, we can pull out different elements for this. I'm going to start a blank array for X, a blank array for Y, and I'm going to append one item to that, so x.append, and then I'm going to pick an item. All right, so I picked 0, 0, so as we see, that's a 1, and then y.append 0, 1. There we go. So we have 1, 2. So therefore, I just made this x and y are just that 1 point, 1, 2, and we'll print that out. So we see point item 0, 1, that's a 2, because there we go. And here's that array. Here's how it would display as an array: row 1, row 2, row 3, or as a matrix. And transpose, so we see what this does. Transpose makes column 1 row 1. So the 1, 3, 3, there we go, and 2, 6, 9, there we go. Column 2 becomes row 2. That's the transposed. And transpose back, and you see we still get it back to column 1, row 1. So sometimes the reason to transpose it could be to do some multiplying that you'd rather multiply this way. So there we go. And again, I picked one element there, and then as an array, you see I just made that array. So that X array and that Y array. So it was 1, 2, which was the first point there. So some different things that we can do with this.
All right, so this is the part of the course where we go into the imaginary world. And we can even graph complex numbers. So we have our whole new axis that we can graph, where instead of x, that's the real axis, and instead of y, that's the imaginary axis. And the way we would graph complex numbers, so let's get a complex number. So if I have like 3 plus 4i. So remember, it's complex because I have a real part and an imaginary part. And then I would graph this as the real part would be my x value and the imaginary part would be my y value. So essentially this would correspond to like a point of like 3, 4, not drawn to scale. But I wouldn't, that's how I would write it in the Cartesian plane, 3, 4, but because we're in this axis, I would still write it as this. It would be 3 plus 4i. So I would still write it like that, but we would know that that's where we get the real part, the imaginary part, plot the point. Pretty cool. So other than going into the imaginary world, what are some of the uses of this? Well, a lot of fractals work on this. And the equations that generate fractals do involve in some capacity, the square root of -1, which gets us I. And then iterations of going through these and therefore plotting the points here. And how do we get those particular points? Only by dealing with imaginary numbers and those types of equations. So that's why it becomes a useful axis. Another thing that's going to connect with something that we're going to build up to here is if I have cosine of x plus I sine of x. So if I have this, then that's something on my unit circle. But remember, x is the cosine, y is the sine. So if I have cosine of x or I sine of x, and again, I'm going to say x is a variable because these are not x and y, it's real and imaginary. So my real part would be the cosine, my horizontal axis, and my imaginary part would be the sine. And so I could plot points on an imaginary circle. So we're taking, from Plato saying that the perfect circle doesn't exist to now we're going to get into imaginary circles, but that's okay. That's where we get to some interesting patterns. So we're going to continue on this, but let's take a look at how to do this in the code, how to get complex numbers, work with complex numbers, get the real part or the imaginary part, and do some other things with that. And then we'll build upon that and get some fractals. So let's take a look at how to work with complex numbers in the code.
All right, so here's the code for complex and imaginary numbers. So we're going to import math, but we're also going to import CMath to deal with complex numbers. All right, and that's going to work behind the scenes. We're not going to see CMath dot anything, but we will use math dot a few things, but we'll get to that. So if I want a complex number, I'm just going to call this function complex, and it's going to take 2 arguments, 2, 3. So the real part is going to be 2, the imaginary part is going to be 3. And to see how this plays out, I'm going to just print this out, what that complex number looks like. And I'm also going to show, you see, if I have this as a variable, in this case z1, I can do z1.real, and then I can do z1.imaginary. So we can split those up, because sometimes that might be useful. All right, so we'll print that out, but then I'm also going to show you another complex number. And here's another one where my real part is 0, but the imaginary part is math.pi. So this is I pi, is really pi I pi. And then I'm going to create this as another variable, though we don't have to, but I'm going to do this. So math.e to the exponent, in this case z3, so that's going to be to the exponent I pi. So it's e to the I pi. Pretty cool. We're going to get even more into this, but these 2 lines here, we just made e to the I pi. All right, so you can if you have a complex number, you can even subtract. So that's why I created a second one, because I can subtract complex numbers. I can take one of the complex numbers and I can take it to an exponent. In this case, I'll just square it. All right. And here, yes, even though I have z4 as e to the I pi, I'm going to show you that I can even just do that math right in the print statement and print that out. And then here, when we see what that looks like, you'll see why I have it built in. I'm just going to round this. So I'm going to round the real part plus, and then I'm going to round the imaginary part. And here, I'm just going to concatenate all this. So it's going to be this. It's going to display the plus sign, and it's going to display I. So it's going to look like a complex number. So let's take a look here. So here's my print statement for this Z1. So it will print this out as 2 plus 3j. It's really interesting that the Python code, it will use the letter j with nothing in between. You know, it's not multiplied by anything, instead of I. But that represents I, the imaginary number. So there's your complex number in Python code. And then we can split it up. You see, the real part is 2, the imaginary part is 3. And here I have this next print statement because we subtracted that and my other imaginary number. So the real one, 2 minus 1 is 1, and the imaginary one, 3 minus 2 is 1. So we can do the subtraction here. We took it to an exponent, and there's the answer. And then we have e to the I pi. This is the answer. But notice it seems like a long decimal, but the key feature of this decimal, this ironically is not the letter, is not e like Euler's number, it's exponent to the negative 16j. So what that is, this number here, 1 times 10 to the negative 16th, is essentially 0. It's so close to 0. So when I have this built, when I'm rounding it here, it absolutely will round to the 0 because that's what we have. So this is the notation. You might remember this from something else. Scientific notation. So that's exponent negative 16. So yeah, 10 to the negative 16th is really close to 0. So what do we get? We get here that e to the I pi is essentially negative 1. There we go. That might not be so amazing now, but it's just one way to look at that. And we'll look at some other even more interesting patterns within that beautiful equation. So, some key features, how to work with complex numbers. Let's graph them. So I'm still just going to import NumPy and Matplot library. I'm going to set my, just like I would with normal graphing, and I'm going to set my x-min, y-min, etc., just like normal graphing. Notice we're really zoomed in, -2 to 2. Really zoomed in on the graph. I do want to add a label. I put this in here, but I decided not to put a title. But I'll add a label so that we see it is the x label, but that's our real axis now. And the y label is the imaginary axis. So here's a complex number. And if the complex number 1 and then 0.75, so then essentially that's 1 plus 0.75i is the complex number. And we would graph this that the real part essentially becomes our x value, and then the complex part, or the imaginary part, becomes our y value. So that's how we would graph a complex number. The real part is the x value, the imaginary part's the y value. So it looks like one number, but we take it as like an xy coordinate. So this could just be, 1, 0.75 as an xy coordinate. So I'm going to skip over this for now because I'm not going to yet so this is x2 and y2, but I'm not graphing them yet. So we're going to ignore this, and we're just going to jump right down here to plot it. So I have my x1 and my y1, and I'm going to plot those. There we go. And when I run this, now I also did not put an axis anywhere, but it just naturally will zoom in on where it wants to be. So there we go. So on the real axis, there we go. The x value is 1, and on the imaginary, 0.75. We see the labels. We see where it is. 0, 0 would be, off this graph. But then, it just zoomed in on that. Okay, that's nice. But we can see that we can plot a point. All right, so now we'll revisit this. I actually also can create np.linspace. So remember, that is an array of values. So I want it to go from 0 to 7, and then I want there to be 70 points in between. So every 1/10 is a new array element. So there's going to be 70 of them here from 0 to 7. And the reason why I did this is because we're going to be thinking about angles, and angles in radians, going around the whole circle is 6.28. So I just rounded up to 7 as the next integer, and 0.1, that's enough of a jump, that we'll see this graph. So there's my array. I'll just call it A. And then points is going to be another array. And notice I have, so np.cosine. So I have the cosine of A plus the sine of A times j, times 1j. So what we have here is, I just created a complex number here called points, and notice I use this without even creating complex, but this is actually going to work very nicely. Points.real, so I'm going to get the real part of it is going to be x2, and the points.imaginary is going to be y2. So if I change this, instead of graphing one point, it's going to graph all of these points, which would go around in a circle. And I could have more points in there. You see, instead of 70, maybe I'll make this 140. There we go. And we graph all these points around in a circle. And this is mathematically even. You see on the y-axis, or the imaginary, it goes from -1 to 1. Same with on the x, or the real axis, -1 to 1. But it displays it just more rectangular. We can also square it up if we wanted to, but I just wanted to show you this. That's what we're graphing here. And in this real and imaginary axis, we can have, the cosine as a real part and the sine as an imaginary part, because cosine is our x value, sine is our y value. And in this real and imaginary axis, we can graph a circle. So these are two interesting things that, in working with the actual equations, we got that e to the I pi. So the complex part is e to the I pi ends up being -1. And we also get that we can graph cosine plus sine I as a complex number, and that would be a circle. And we're going to build upon that to really appreciate the levels of depth for this beautiful formula. But these are some things that we can do with real and complex numbers. Calculating them, graphing them, and we'll see what other interesting patterns these lead to.
The Mandelbrot set, this equation seems to be very simple. It's z equals z squared plus c. And really then what you would do is you would define z equals and c equals at the beginning. And quite often z starts out at 0. That's pretty common. And we'll talk about the c value here. So what makes this so cool? Well, we're going to get into the visuals of this when we look at the code, but it becomes this really great pattern, especially when you graph it on the real and imaginary axis. We're not talking about x and y axis here. Kind of doesn't accomplish the goal. So what we're going to do is define c, and it doesn't have to be an imaginary number, but if you have something like, c equals like, I don't know, like 0.5i or something like that. So you would plug those in, 0 squared plus, so it would be 0 squared plus 0.5i, and of course that zeroes out. So then z, the next round, then that's the z value, that's a 0, so it becomes 0.5i squared plus 0.5i. And then we would get that answer and then plug that into z. Now this one works out nicely. I squared then becomes -1, and then I have I in that part, so we see it's a complex number that we can graph on the real and complex axis. Well, anything that continues to get larger and larger, that's not a part of the Mandelbrot set. But there's these few values that tend to get not much larger, and they define, they define this central part, and the edges of the Mandelbrot set, they're saying that, we'll say that those are a part of the Mandelbrot set. And then some things on the edge that are not really a part of the Mandelbrot set, because at some point they'll get larger and larger. The way we would usually do it is code it to have, how many iterations does it take to get beyond this threshold? And then I might color it. So, in the Mandelbrot set might be a really dark color like black. And then I'll get to like blue if it's a few iterations gets it beyond the Mandelbrot. If it's a few more, then I might go to, green, and then, out through the spectrum. And then a lot of times you'll see these, and then something like red on the edges where, that right away wasn't even in the Mandelbrot set. So yeah, just really interesting. Just a very simple equation, and then just each iteration, we just change the z value, plot the point, and then count how many iterations it takes to get beyond a certain threshold. And really then what happens is these really cool patterns. And the first view is pretty cool, and then we could zoom in on different parts to get other views. So that's what we're going to take a look at. And in addition to looking at the code, so it's Mandelbrot because the guy's name, Benoit Mandelbrot, he did a really good TED Talk where he just talks about fractals and everything. Yeah, just a really interesting guy. So if you come across that TED Talk with Mandelbrot, it's worth watching. But let's take a look at the code, and we're going to see some these and some other examples, some other iterations, and see how this leads up to what the Mandelbrot picture looks like. Let's take a look at the code.
Here's the code for the Mandelbrot set, and yes, I will admit that I actually used ChatGPT to create this code. So doing this in, 5 seconds saved me potentially a day because understanding the idea that we can take these points and then plug them back into this formula and then plot and then color code the different parts for how many iterations it takes to get to that point. Yes, we can wrap our heads around it, but writing the code to get that to work and to really generate the good graph, you know what? Some things that AI does pretty well. So we're going to still only need to import NumPy and Matplotlib. I'm going to define this Mandelbrot function, and see, here's what it is. We're going to go through taking what C value we want. We're already going to define that Z starts at 0. And we're going to loop through, however many iterations. We're going to loop through, and then this is what we do. Z times Z plus C. And then we're just going to keep overwriting that. That's what we want to do. It would seem that the formula is straightforward, but again, to make it work correctly, you see, anytime Z gets to be greater than 2, so then we're going to return I, and then we're going to return max of iterations. So that's kind of what we want from this, is how many iterations it took to get to this point. And then here's the plot, where we're going to take the inputs x min, max, y min, y max, the width and height of the graph, max iterations. And here, we're going to create np.linspace, 2 different arrays for, one for the x, one for the y, and then we're going to create a mesh grid. This was, again, some nice insight that the GPT gave, that working with a mesh grid, this works out nicely. So we define this XY mesh grid, and then I'm going to say, notice these are capital letters here, Z equals X plus 1J times Y. And here we go. We're going to create this image, and we're going to loop through this, calling this function. So it's going to loop through the height and width and take, this Z function to generate variable C. And there we go. Then we're going to call that the Mandelbrot function, and then C, max iterations. So now when we get to show this image, there we go, the extent, and some labels here. So one of the things that we can do, these original numbers are the ones that GPT returned, but I'm going to run this first and then show some other numbers that will zoom in. But anyway, so we have these minimum, maximum, width and height. And there you go, max iterations 100, that works. And now we're going to call the plot function. So after that, then we call this plot function here. So you could have this code, you can change these values, call that plot function, which will then also call the Mandelbrot function, and there we go. If you run it, we get the Mandelbrot set. And that one function saying that it was hot, that defines the colors a little bit. And we see all these different patterns here for how many iterations it takes to get to one part here. And one of the things then we can do is change this. Probably could put these on sliders, but that might be a little bit of take a while to process. All right. And so I'm just going to switch these around so that we have there we go. So we'll just switch that around, and then negative 1.5 here. Okay. And and make this 1.5. Comment there. All right. So in looking at this, I was looking at one of these and zooming in to this. You see, this gives you the Mandelbrot that you might be familiar with. This look. Well, actually, either of them, depending on what zoom level you often see. But we see this Mandelbrot set here, and so notice the zoomed out version with these different values here. We get that zoomed out version. This is nice. And then the other one, we can take a look and see like the zoomed in on all these edges that of course are blurry here. But if we were to zoom in on them, then we get to that value that we had before. Pretty cool. And again, another usefulness of imaginary numbers. A lot of the usefulness is the artistic or visual representation, because it actually ends up being the math of imaginary numbers behind the scenes. Other sorts of fractals, again, things that might seem random, just because you don't fully see all the little calculations going on in the background. But these are some of the uses of imaginary numbers. And Benoit Mandelbrot, he was pretty good with these. Interesting character. All right. So again, just some use of imaginary numbers. A little example of some AI code that you can generate to plot this, and some things you can tinker with. Go in there and change some of the values and see what you get.
So let's talk about sequences and series. So a sequence is any collection of numbers, kind of like an array, but there's a definite order to them, a sequence, if you will. And a series is when we have that, but we add them up. So let's talk about the sequences first, and then we'll see what we're going to do to add them up. So a few different types. The first one we're going to look at is arithmetic. And just like the word arithmetic, arithmetic is when I add or subtract something to get the next number. And one thing that binds these sequences, I have an equation that I can use to generate the next number. So here's my equation. I'll call it, I'll call my sequence A, and for arithmetic, and the subscript n. So A sub n is the nth number in the sequence, and A sub 1 is the first number. So a lot of times in array, we think about counting. 0 is the first term, but for these and for this particular math, n is 1 is the first number. So A sub 1 is the first number, and then I see the common difference here. So I start with the first, and then plus d times, and we see the common difference times n minus 1, because I already have my first number. So when n is 2, then I have a common difference. But when n is 1, I have my first number there. So let's look at an example of this. Supposing I have just odd numbers. So I would have A sub n equals 1 plus 2 times n minus 1. Whereas I've already accounted for my first number, but then I'm adding 2 each time. And so then if I generate that, 1, comma, then notice n is 1, so 1 minus 1 is 0, that's why then that drops out. Then when n is 2 for the second number, then I have 2 minus 1 is 1, times 2 is 2, plus 1 is 3. And n is 3 for the third number, so then 3 minus 1 is 2, times 2 is 4, plus 1 is 5. And we know this pattern, so we can see that, the next one is 7, which is the fourth number. 4 minus 1 is 3, times 2 is 6, plus 1 is 7, etc. So we can look at this and we can generate every number in the sequence here. So as I was saying, it's similar to slope-intercept, y equals mx plus b, but the difference is the sequence is discrete, meaning that I only want n to be integers. It's not continuous where n can, like on the graph, can be any decimal in between. I have 1, I have 2, I don't have any of the numbers in between 1 and 2. So I can generate this sequence here. Now, what I can do then, if that's the sequence, my series is I'm just adding them. And that's the difference between a sequence and a series, if I just add them up. And what we find is for various sequences or series, there's some cool patterns to adding them up. So certainly for this one, I can add them, and I could. We'll look at the code in a little bit and how we can run through a loop and just add them. If I have code at my disposal, that's probably what I'm going to do, because setting up a simple loop is pretty easy. But then I could, there's a couple other ways I can do it. Let's talk about the notation of this first. So if I have the sum, then I'm going to say that the sum in my specific case here is going to be capital sigma for sum, and then I'm going to have the sum of this as n goes from 1 to, and I can pick something. I can pick 4. Let's say we ended it here. So there we go. So this is the math notation of essentially a loop. I'm going to, what's the sum of this as n goes from 1 to 4? So I plug in n is 1, then n is 2, then n is 3, then n is 4, generate my numbers, and then add them up. There we go. So we see, we can make this. But supposing I had the numbers 1 to 100, so then I would have all of these. I'm going to stop this plus 2. And then if n is 100, minus 1 is 99, times 2 is 198, so then plus 1 is 199. That would be my last term. So how could I do this? Well, certainly, again, if I have code, I might just like create a loop. And that's kind of how we're looking in this course, like the difference if I have, code at my disposal or am I crunching the numbers on paper. But Friedrich Gauss figured out this interesting pattern here that, so what's 1 plus 199 is 200. But then my previous number before that is going to be 197 because, all the odd numbers. So 197 plus 3, also 200. And if we keep working backwards in there, the one before that would be 195 plus 5 is 200. And so in summing this up, we have this interesting pattern here that anytime I'm summing up an arithmetic series, it's always going to be the first plus the last. And then remember, I'm pairing them up, so it's that times n over 2. So that's the sum of any arithmetic series. And what's cool is as we get into these series, so we get the idea we can, generate a sequence, we can find any number in that sequence, we can sum up that sequence, which would be a series, I can sum it up, and then for a lot of things, we can find formulas to sum this up. And having, your brain, paper, code, all at your disposal, different situations, you see which one ends up being the better, which one's a better solution. Geometric is the other one. And geometric series is, sequence or series is when we're multiplying something each time to get the next number. And here's our formula. I'll call it G. So G sub n for any number. G sub 1 is the first term. And then R for the common ratio since we're multiplying. So it's R to the exponent n minus 1. So that's how we would generate each term. And let's, come up with one. Let's say we have g sub n equals, let's say 3 plus 2 to the n minus 1. Just, a simple example here. So my first term would be 3, and then times 2, because, when n is 1, then that drops out. So 3 times 2 is 6. And then when n is 3 for the third term, 3 minus 1 is 2, times 2 is 4, and 3 times 4 is 12. Even if I was counting individually, times 2, and then I'll do times 2 again, since I know that that's the pattern, 24, and then we can continue. So there we go. So we have our geometric series, and if I was going to, that's a sequence if I just have this, so then I can just switch this out to, be a series if I wanted to, and if I wanted to write the formula, saying that I'm summing this up, so then it would be, again, Greek letter sigma as n goes from 1, and in this case, we'll just say 1 to 4. There we go. So there's our geometric series, and we see the similarities. There is also, if I was going to sum this up, if I'm writing code, I'm probably going to write a loop. But I would, there is also a formula for this. I feel like it's not as intuitive as the arithmetic, but the sum in this case is going to be, if we call a the first term, a times r to the n minus 1 over r minus 1. Kind of an interesting sum here, though. It works, and that becomes the sum if I just wanted to generate it this way. And sometimes that connects with some things, as we'll see with sine and cosine. When we have an interesting formula for generating a sequence, sometimes that's useful in other places. So we kind of want to have all these different tools available to us, whether we use a loop or use a formula, or just use our brain and do the math that way. We want to have these different things at our disposal. So let's look at one more sequence here. So another type of sequence or series is recursive, and with these we really can't generate an equation like we did before, because recursive means it depends on what came right before. And one of them is the Fibonacci sequence. So, we're all familiar with this, 1, 1, 2, 3, 5, etc. Because how do we get this? It's, understood 0 to begin. So then I have a 1, and then this 1 is 1 plus 0. And then this 2 is 1 plus 1. This 3 is 2 plus 1. We're always adding the two previous numbers. So as a formula, it really is a sub n equals a sub n minus 1 plus a sub n minus 2. And you see, that's recursive. I need to know the two previous numbers to get that current number. And it builds upon that, so I can't just jump up what's the 50th term. So this is what one of our other types of sequences. Getting into the code, probably more likely something we would do with a loop, because I can easily build that up quickly. Processors are quick. So this is recursive, and that Fibonacci sequence. Why does it show up everywhere, this recursive sequence? It's because the cumulative effects of things growing in nature, adding, and then the next thing is, adding on to the previous two. So, shells or things. And like, for example, if I had, the area of this square, it's 1 by 1. So the dimensions of this square is 1 by 1. So then if I put another square, so then this next one is 2 by 2. And you see, then this next one is 3 by 3. because it adds that one from before and then that 2. And then, so now that was 3. And so then this next one is 5 by 5. And then this next one would be, 5, 6, 7, 8, because that's the 8. So then this one would be 8 by 8. And, just with squares, we can see how it builds that. Each of these are squares building upon, each side is the measure of the 2 previous sides. Pretty cool. And then the Fibonacci spiral, once we build this, then we can just take a curved line, imagine this, 1/4 of a circle. So if this was the center, a curved line from that corner to that corner. And then a curved line from that corner to that corner. And then in each square, I'm taking a curved line from corner to corner. And then a curved line from corner to corner, and a curved line from corner to corner, and a curved line from corner to corner. Hopefully my drawing isn't too bad. But that's where we get the spiral, and that's where we get the recursive, and that's sequence and series, and that's where we get the, this cumulative growth in nature, and then we get this spiral. So our goal is to build upon things, and your knowledge of math and algorithms becomes cumulative growth. So let's take a look at how we can do some of this stuff in code.
Here's how to generate sequences and series with code. And as we were saying, we'll loop through it. We'll start with an arithmetic sequence. I just put as a comment that, you could define your sequence just so it's there for your own notes as a comment. And here I split it up. Sequence, what are we going to do? We're going to create an empty array or list. And then as we loop through, I just decided to make it range, 11. As we loop through, I'm going to generate each element, store it as this variable next, and then append it to the array. And notice I usually will have a starting point, and then it's always times n-1 mathematically, because the first element is element number 1. But since in Python our ranges begin with 0 unless I tell it otherwise, so I don't have to put that n-1 because it's already going to start with 0. There we go, and then we'll print that out. I'm also going to do the series here. We'll print this all out together. So with the series, I have a sum variable, start at 0, and then as we go through our range, also generate each next element, and then I'm going to add it to my sum variable. So then we can print that out. So, just a simple sequence here. And what do we have? We're going to generate starting with 3, and then we're going to do the odd numbers because it's 2 every time. So there we go. And then the sum, for this particular instance here. And we'll do this with a geometric series too. Notice how similar, start out with your empty array, comment up here if you want, and then, generate the next element, append it to the empty array, and at the end we'll print it out. Same with the series, start out with a sum variable, loop through, generate the next one, add it to the existing sum. There we go. And we see, so we can see the answer and the sum. Now, I'll do one more, and this time notice you were probably thinking, hey, I should put them both in the same loop. So I did that on this one. So sum variable starting at 0, empty array for the series. And now for this one, I just picked a range of 50. And I'm going to do a harmonic series, 1 over 2 to an exponent. So you see 1 over 2 to the a, and I still kept this as a equals 0 as the beginning. So my first element will have that, and that will end up being the element will be 1, and we'll see that here. So then my next element, append it to the series array, add that to the existing sum, and we're going to print out the series, we're going to print out the sum, and there we go. So remember, this is going to be 1, 1, 1/2, 1/4, but this will put them out as decimals. And the sum, we see, we remember mathematically then looping this, the sum of this as the number of elements approaches infinity, this sum approaches 2 because it converges. These converge, and so I can have even more, and it's just really going to approach 2. So that's the sum as n approaches infinity, but I only went up to 50, and we can still already see how close that gets to 2. So I could loop this. Instead of 50, I can make it 100, I can make it 1,000,000, and we're still going to be, just about at 2. Just more 9s. There we go. So we see the sum of the harmonic series, as our other example. Now, we also might have mentioned Fibonacci and the recursive sequences. So I just want to point this out. There's this online encyclopedia of integer sequences. How cool is that? So what you can do is you can type in the name of the sequence if you happen to know it, and you can or you can type in the first few. If you type in the first few, one of their tips for searching is you don't put the first number in. Sometimes people disagree over where a particular sequence starts. So the first 1 or 2 elements you don't have to put in, and then you put in at least 6. More than that, you probably don't need to. So, skip the first number or 2, put in about 6 elements, and search it up. So that's what they put out an example there. I'm going to hit enter, and you see it gives you this, that particular sequence is the number of trees with n unlabeled nodes. Kind of cool. As well as some comments, some references, history, and other links. So you can do this. You can just type in, so, for Fibonacci, I'm going to skip the first 1. I'm just going to put 1, 2, 3, 5, 8, and that's probably enough. Hit enter, and look at that. It tells me that it's the Fibonacci numbers, illustrates this, and, all the other notes, including some other references and mentions of other people that came up with a similar sequence before Fibonacci. So really cool stuff. And there we go, just to expand, beyond any of the sequences you might know. And remember, these are sequences, but to make them a series, all you have to do is just add them. So once you have an equation to generate that, you can add them up. All right, there we go. And now we're going to go on to look at using sequences and series to generate other numbers, especially series, to generate numbers like Euler's number, E, even sine and cosine. It's amazing how many different numbers you can get from, there's a sequence or series definition to that number. So we're going to take a look at that. So that's what's next.
Let's take a look at E, Euler's number, and how we get this by definition. There's actually a couple ways to get this, but this is possibly the go-to. So E equals the sum. So let's look at this notation here. This capital sigma, the Greek letter sigma, is for summation. So this is the math notation for doing a loop and adding every time. So I'm going to say n equals 0 at the beginning, and then so n goes from 0 to infinity. So that's how I define my loop here. So I'm going to say n goes from 0 to infinity, and then every iteration I'm going to add this all up. And so it's the sum of this, 1 over n factorial. And remember, factorial is that number times every number less than that. So let's work this out here. So then 1 over 0 factorial. And so this is what we're doing. We're summing this up. Plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial. And it goes on forever. till infinity. So this is how we get e, but let's look at these values here. 0 factorial, it seems weird that you have 0 in the denominator, and yet I'm also saying multiply that times everything, wouldn't that zero out? But by definition, 0 factorial is 1. Because factorial comes into play really in situations where I'm calculating probability of things. And so if I have no things, how many ways can I arrange that? I only have one way, which is to do nothing. So it's kind of weird, you know. Sometimes math explains some other logic or written things, and in this case, we need some verbal explanation to explain the math. But that's why 0 factorial by definition is 1, because if I have no things, I only have one option, which is I can't arrange them. So 1 factorial is 1. 2, remember, so 2 times 1, which is just 2. 3 is then 3 times 2 times 1. And then it would go on 4. 4 factorial is 4 times 3 times 2 times 1. But even looking at this, we're going to get this 1 over 1. So that's 1. That's 1 again. That's 1/2. 3 factorial, so then that's 1/6. And that would be 4 factorial, which would be 4 times 3 is 12, times 2 is 24. And again, that would continue. This is almost enough for us to start seeing that E, remember it's 2.71828, 1828. Well, 2.5, 6.5, you know, we're getting just that part, we're almost to 2.7. And then you see we keep adding smaller and smaller amounts, but it gets up to that, you know, just over 2.7. And we'll see with the code that if we loop through this, it might even take like, you know, 10, 11 times. That's, you know, that's enough to get us a few decimal places, you know, correct to E as we know it. So that's pretty cool. But this is the factorial definition of E. So then, you know, then that's what we get. You know, all this then will eventually equal 2.71828, 1828. And after that, the next number is a 1, but the pattern kind of breaks down a little bit. So it doesn't exactly repeat those 4 digits. So there we go. Summation of 1 over n factorial as n goes from 0 to infinity. Cool. Let's take a look at how we can do this with the code.
Here's how to generate Euler's number, E, but using the summation, using the series. So the series, remember, it's the sum of 1 over n factorial. So I'm just going to give this range here up to 50, even though the official definition is up to infinity. 50 will almost do it for us. And then I'll show you. So I'm going to just generate the sum, and then we're going to keep adding to it. Each time we go through the loop, we're going to add to 1 over math.factorial of a. And then after we go through that loop, I'm going to print that out and then also print out just the general math.e, and we see how close we are. So look at this, even up to 50, we're close down to this many decimal places, and it even rounds. So that's why I stopped at 50. And you see, we can generate E with this sum. This really is, you know, one of the ways, you know, we get E. And now then we're going to connect this with sine and cosine to build up to a big reveal here.
So let's look at the series definitions of e to the x. So another way to get e, so it's always x e to the x. So this is not just e, it's e to an exponent. So this would be x to the 0 over 0 factorial, which works out to 1. X to the first over 1 factorial plus x to the second over 2 factorial plus x to the third over 3 factorial. And that keeps going. So each time, you know, the numerator x to an exponent, then that exponent factorial. So as you can see, even though the numerator is getting bigger, the denominator factorial is also getting bigger, and we're adding this tiny, tiny amount. We're adding a different amount each time. And so that's how we generate e to the x. What's x, and then, however many exponents. So we're going to connect this with sine and cosine because, first of all, you might notice how similar they are. Cosine as the even exponent, so it starts out, and I wrote it this way, 0x to the 0 over 0 factorial, but then we alternate minus x to the second over 2 factorial plus x to the fourth over 4 factorial minus again, and then that continues that pattern. And sine, similar to cosine, but we have the odd exponents. So we don't have x to the 0, that's even. X to the first over 1 factorial minus x to the third over 3 factorial plus x to the fifth over 5 factorial. And we go on like this. So these are interesting in and of themselves. And we have ways that we can, use summation notation. There's, a formula for this. But I wanted to write it out this way so you can see this. And we're going to look at how this connects to e to the x. Because I want to look at what if we have e to the ix. X to the 0 over 0. So that would still be 1 ix over 1 factorial, which is, 1. I'm actually going to keep that denominator because that'll be important. And then the next one, x squared. But then if it's ix, then x squared. So that becomes, so we still have the x squared, but the I squared becomes -1, which changes that sign. And then we go to x to the third. So we still have x to the third, but then I to the third is negative I, and still the same denominator. And then we have the next one to the fourth. In just doing this a few times, I want you to notice then that the I over 1 factorial, and then so that is a lot like sine, but I'm multiplying by I this time. And then minus x squared, that's a lot like cosine here. This next term, minus I x to the third over 3, a lot like sine, but I'm multiplying by I. This one, a lot like cosine. The next one's going to be a lot like sine, but multiplying by I. So it ends up, it's threaded together because instead of even odd, I have all of them, but each one of them lines up with sine, but multiplied by I. So what we really get is e to the ix equals the cosine of x plus I times the sine of x. And that's the formula that Robert Coates, many years ago demonstrated. That when we look at the series definitions of these, it's really cool how it lines up when we have e to the ix. And if it's e to the ix, doing that substitution, it works out that the cosine ends up being the same, and then the sine, it's just like the sine terms, but multiplied by I each time, so we can just do that out here, and that's what we get. E to the ix equals cosine of x plus I times the sine of x. And there's some other cool patterns we can do, but I wanted to talk about this as it leads up to our, e to the I pi equals -1 explanation. All right, so let's take a look at, in the code, doing things like this with values and, showing that, this does get to cosine, this does get to sine, and how they connect. So let's take a look at the code.
So here's how to generate sine and cosine using a series. And another interesting thing we can do with the series, and also combined with E, we're going to lead up to a big reveal here. So we looked at the formulas, how cosine, we'll do that one first. How we generate cosine with it's all the even numbers and 0 is even. The numerator is x to that exponent, and then the denominator is that number factorial. So what we're going to do, have my sum variable as 0. I'm going to use x as the angle, remember in radians. And for our demonstration here, that really does need to be an integer because we're going to end up using that in factorial. Okay, and I created this other variable, pn, positive, negative, and I'm going to start it out at -1. So here, if I have this range 50, and that might be enough. We might even increase it to 100. This officially would be the sum up to infinity, but 50 to 100, sometimes you'll see how many decimal places it goes to, and that will be enough to illustrate this. So remember, this pattern goes for the even exponent. So I'm going to start out with this if our a is even, so a modulus 2, if that's 0, and then each time I'm going to multiply by -1 because, again, that's the pattern. One's positive, one's negative. And then I'm going to keep adding to the sum here. So the sum plus positive or negative times x to that exponent, and then the denominator is math factorial. So there we go. So it goes through all the even ones. There's another way to do this with counting through each one and just multiplying some of these by 2. That works also. I decided to do it this way. And we're going to print out cosine, and we're also going to print out just the normal math.cosine so we can see the comparison. And we'll do the same thing for sine. I'll do this all before I run it. So very similar formulas. So I'm going to sum that up, start out with that variable, and then again, my angle x is 1. There we go. I can make these different x values because it's just going to overwrite it each time. So that's fine. I can make it 2 just to compare. And see, we have that same range. Now, here, I want the range to start at 1 because if I don't have a number there, it's going to start at 0. But for sine, remember, it goes through all the odd numbers. So I want it to start at 1. And then the modulus if statement, if it's not equal to 0, then I want to continue. Same thing, same pattern. It alternates positive, negative. And then once we have that established, this part of the formula is actually very similar. Well, new line, and I'm going to print out the sine. Again, that sine, and then just calculating it, and we'll see how close we are. So look at the cosine. Using that, we're pretty close down to that many decimal places. If it was, anywhere further away, maybe these last two numbers changed, I would increase and loop through it more, and you would see it, it would match up. But yeah, it really officially goes to infinity, but looping through 50 times is actually enough. So we see that works, that we actually can generate sine and cosine based on summation of a series. All right, so pretty cool. And then we're going to look at combining that with E and some of the other cool patterns that follow.
So we're going to look at e to the I pi equals -1 and why this is such a beautiful equation. So it connects with the real and imaginary axis. If we are graphing, notice I have I, which is the imaginary number, square root of -1. We can graph these. And remember, the real axis is the horizontal. So it's not x and y. The horizontal is real, and the vertical is the imaginary axis. So when I plot a point there, if I would really have it as whatever real part, that corresponds to the horizontal. So I'd count over from the origin, and then I times something, the imaginary part, then that would be, the vertical point. So if I have, cosine of x plus I sine of x, and remember, it's this complex number, so it's real plus the imaginary part, but we would graph that as, if it were on the xy coordinate plane, cosine x comma sine of x, or, that'd be cosine of theta or something like that. So we see that, writing it like this corresponds to plotting this point, cosine sine, the real part, the imaginary part. What's cool is that this guy, Robert Coates, in like 1714, he figured this out, that e to the ix equals this, cosine of x plus I sine of x. Now, when we get into the code, we're going to look at all different ways that we can now demonstrate that that's true. I'll show you like loops and see all these different values that for any value of x, this works. They come out the exact same complex number to many decimal places. But it's kind of cool. He worked this out, that many years ago, that the e to the ix equals this. So what that means is that I can plot this point and I can actually just write e to the ix as the coordinate of that point. And it kind of just boggles the mind because of the way we write the notation here as, this complex number, and then that's how I plot the point, the real part, the complex part, plot the point, which is really cool. So Pythagorean theorem then also applies here because in this case, the horizontal is still cosine, the vertical is still sine. So sine squared plus cosine squared is 1, and then I get the radius 1, just like our unit circle. So when we look at this, I'm going to throw one more thing here in. Then since we've established that the radius is 1, if I think of polar coordinates, so we go from xy to real and imaginary. Polar, they're not rectangular. The coordinates there are r theta. So theta, remember, is the angle. So r is the radius from the origin. So how far out am I going from the radius, and then what's the angle? A lot of air traffic controllers or satellite dishes that they'll use polar coordinates because that's what I want. How far out am I, and then what's the angle? Well, then in this case, if the radius is 1 and then the angle is theta, or I'll continue calling it x, so therefore 1x, and that is e to the I pi, or e to the ix. Just kind of cool how that works out everywhere. So that's kind of why people talk about this being this beautiful equation, e to the ix. Now let's talk about this exact value. So if I have this equation here, I'm just going to get this out of the way, but it's just one more connection here. And then if I talk about I pi, so this works for all those different values, but some of them, are more elegant solutions than others. But if this is pi, so if I have e to the I pi, so then that's the cosine of pi plus I times the sine of pi. And remember, pi radians, you're going around. So the coordinate here, the cosine of pi is -1, and then the sine of pi is 0. So e to the I pi, that's where we get e to the I pi equals. So we build upon this established equation here, and then for this value, when I plug in that the angle is pi radians, e to the I pi equals -1, plus 0 if you want to be official. It's just really a cool thing because to fully appreciate the beauty of that, besides the fact that it brings together all these, e, I, pi, -1, all this, but the explanation of it brings in sine and cosine and complex numbers and graphing on the imaginary axis and verifying it with Pythagorean identity and connection with polar coordinates. It's just really amazing that as you've been going through math up to this point, you can kind of bring it all together. You needed to know all the things you've learned up to this point to fully appreciate, oh, it all comes together in this equation. But that's just why it's cool. Graphing on the, this equation and then graphing on the imaginary axis and plugging in that particular value gets you e to the I pi equals -1. So when we look at the code, what I'm going to go through is also look at other ways that we can verify this with code and some other sequences. So let's take a look at that.
So now we're going to show this with with code, that we're going to import math and our code CMath for the complex. And what we're going to do, I have two variables here. I probably could have done it with one, but a and then x. So I use that one just for the complex. So if a is 1, so then I have, my real part is 0 and it's 1i. So that makes this value comp is I. So I feel like that's kind of the best way to do it. And now that's I. This is I pi, which I'm going to deal with later. But notice my complex, the real part is 0, and the complex part would be math.pi. So the answer to that would be I pi stored as this variable. So anyway, so this is how we could show a complex number. So I'm just going to print out the complex number to show you. And then e to the ix. So notice, yes, I can do math.e, but I'm going to do cmath.e because we want our answer to be complex. All right, so cmath.e to the exponent comp. So this is to the exponent I. So this is going to be e to the I. All right, and then these, I have math.cosine of x and my complex number I. So I have I times cmath times the sine of x. And I split this up just to, if you copy this code, you can tinker with this and change some things. So what we were showing on the whiteboard was that e to the ix does equal cosine of x plus I sine of x. That's the idea. So I'm going to print out and show you there's e to the ix, and I'm going to show you that cosine of x plus I sine of x is actually the same value. And along the way, we're learning how to work with and use imaginary numbers. So there's my complex number. Python tends to output, yes, we know it's I, but Python uses J for illustrating that this is an imaginary number. So there's my complex number. So that 1J is the Python way of saying that's I, the imaginary number. So e to the ix, we see, does give us this complex number here. Like, that's it. If I have e to the ix, that's what I get. And notice cosine of x plus I sine of x is exactly that same complex number. Pretty cool. So that's what we want to show. We can see it in the factoring way. We can see it with sequences and with series. And we can see it with code that we get e to the ix. This does work. And showing that Robert Coates was right in 1714, we're also going to loop through this with all different values. But it shows that e to the ix equals cosine of x plus I sine of x. Really cool. That way, in the imaginary graphing, the real axis and the imaginary axis, that this e to the ix ends up, whatever x is, it ends up being this complex number that works out to this. And so that's what we're going to do here. We're just going to loop through this. And again, just a way to represent I. So I just didn't use another variable. I just said, okay, yeah, 0, 1. That's my complex number. And in my range, I called it 63 because, my first thing is my angle is going to be 0.1 times that. So it's going to go up to 6.28, one complete cycle in radians around the circle. And I have in mind the left and right of an equal sign. So the right side is going to be cosine of A plus I sine of A. And then the left side is going to be e to that c-num is my complex number, but it's really I times A. So whatever that angle is, then I have e to the IA equals cosine of A plus I sine of A. And that's what we're going to do. And, just in case, I threw this in an if statement, just in case you don't want to look at all these. Only if these are equal will it print out on 2 lines, because we'll see these are a lot of decimal places. It's going to round, that the angle, round it to 1 decimal place, and then give you the e value, and then the left side. And then it's also on the next line, again, because it's going to be a lot of decimal places, going to print out the exact value. So when we run this, scrolls down here. I have each of these angles in radians. You see the e value is 1 plus, because when it's 0, we're on the real axis, but no imaginary numbers, which would be equivalent to the y value. And then the cosine sine would be 1 plus 0. There we go. And we see for the next angle, the e value is exactly this complex number, but cosine sine is exactly the same complex number, down to all those decimal places. And this is just a way of showing, Robert Coates worked this out, on a chalkboard probably but definitely or paper in 1774. But here, just showing you that, yes, calculating this through all these decimal places, these are going to be the same, that at every point, then we get e to that exponent equals cosine plus I sine. And if we go through all of this, so this leads us all up to the grand finale, showing that e to the I pi equals -1. So all these, see, and we can see how all this fits together. Really cool. All these answers, e to the I pi equals -1 is nice and elegant. If I said e to the, 6 radians times I don't know, equals this number, you might say, okay, yeah, all right, I believe you, but it's not that elegant of a solution. Here, we're going to show that, it works for all those, but what I'm going to do is my variable I pi is going to be this. Remember, the complex, so it's math.pi, that's going to be the imaginary part. So this is I pi. And then so I'm going to print out that exact value, e to the I pi. But then what I'm going to do is, that's my complex number, so I'm going to, this answer is e to the I pi, but I want the real part. So notice I have my complex variable, c answer, and then I want the real part, so it's c answer dot real. And then I want the imaginary part. Now, I know this real side, is going to be 1, or -1, but the imaginary part, it's going to be 0, but it's not going to look like that. It's going to be this long decimal that rounds to 0 easily, but it's going to look weird. So I do want to round that imaginary part. So I take that c answer dot imag, and it'll round it. So now I'm going to print c real plus c imag. And so what we're going to have is, yes, for when it's the I pi, I'm going to print e to the I pi, and then I'm going to print that real and imaginary part, and we get e to the I pi, and you see that's the full thing. But notice its exponent, this is not e like Euler's number, this is the exponent -16. So really we're saying that, a decimal point, then about 15 zeros, then a 1 is where this is. So that's essentially 0. So when we round it, it's 0. And that's what we get. E to the I pi. If I don't round it, it looks like this. But when I round it, it looks like this. And it really shows e to the I pi equals -1. So pretty cool. And that's what makes this so exciting. That it's just so interesting that it all comes together. Yes, we see all these patterns, but to fully appreciate all these patterns, all these series that, you learn about, the graphing, the trigonometry, the real and complex axis, and how all that is true at each step, and we see that it matches up. But then when it comes down to the variable where the angle is pi radians, it all lines up perfectly, and it comes down to this nice elegant solution. E to the I pi equals -1. And so there we go. So we go from, how many hundreds of years ago, some cool patterns that people were discussing, to more modern technology, reproving that and just adding a deeper dimension to this, that, yes, it's kind of cool that here's one more way to show this. So there you go. And that's a big part of what math is at this level, is appreciating the elegant solutions. So that's what we want to be able to do.
We're talking about probability. And this really leads into a lot of things that we're going to do with statistics, data science, because we can't always predict the future. We go on probabilities and what's likely to happen. And the general probability equation is the number of correct options out of the number of possible options. So that's it. If if I'm thinking of a number from 1 to 10 and somebody has to guess, there's one correct number out of 10. Probability of them guessing is 1 out of 10. If I want to roll dice, rolling 1 cube, then whatever number I want to roll, if I'm only rolling 1 cube, then I would have one number out of the 6 possible sides. That's the probability that I rolled the number that I want, 1 out of 6. So anytime, we're always counting up, and that's where we get into some of our counting rules. How can I count up the number of possible options? And then of those, what are the ones, how many am I considering correct options? So let's go back to the rolling dice. 1 out of 6 probability if I roll 1. But supposing I want to roll 2, and so let's think about like a 12. There's only one way to get a 12. I have to roll 6, then I have to roll 6. So I have to roll the first one as a 6, and I have to roll the second one as a 6. And anytime it's only correct if this happens and that happens, then I multiply the probabilities. So, I roll 2 dice. The probability of me rolling a 6 is 1 out of 6. And then on the second die, it's 1 out of 6. So I multiply them. So then it would be 1 out of 36. So if I roll 2 dice and I want to roll a 12, I have a 1 out of 36 chance of rolling a 12. The same would be true for rolling a 2, because 1 and 1, same idea, only one way to get it. So that's how we get, and I multiply the probabilities. This is where we can think about the, lottery winnings. If I have a lot of the lotteries, we've picked, one number out of 10, and they might go to another bin and pick another number out of 10. And then they might go to another bin and pick another number out of 10. And so I'm only correct, I only win if I get all 3 numbers. I got that, out of 10, I picked this correct number out of 10, this correct one. So then that would be 1 out of 1,000. And so that's the probability of winning just like a simple pick 3 lottery, 1 out of 1,000. And we see that 1 out of 1,000, probably, who knows? You could, the way you pick it, it's not a guarantee that if you played it 1,000 times, you're going to win. So that's where a lot of people, spend a lot of money hoping that 1 out of 1,000, lightning strikes and we get lucky. But we really don't know. So then if it's or, then I can add the probabilities. So supposing rolling dice, and let's say I'm rolling one die. So let's say, what's the probability of me rolling a 5 or a 6? You know, you're playing a game, you know, you need a 5 or a 6 to win. So, you know, probability of rolling a 5 is still that 1 out of 6, because that's one number on the whole cube. And probability of rolling a 6 is also 1 out of 6. But I'm correct if this one or that one works. So I would add the probabilities. So that gives me 2 out of 6. Or we could reduce it. But there we go. Anytime I have, that's correct. If this or that happens, then I add the probabilities. And so the general probability, we're always counting up how many possible options, and you know, number of correct odd number possible. And if both of them have to happen, then I multiply the probabilities. If either one, then I can add the probabilities. And we can build upon these to look at other ways to calculate probability. As it gets more complex, we really end up having a lot of different counting rules for how I can figure out the possible options. That's kind of the thing. How can I figure out the possible options? And then of you know, each of these, you know, all the different ways we can combine this. So we'll take a look at this, and we'll look at how we can do this with code.
And here's the formula. So the notation, big P in the middle for permutation. So that means that order does matter. And I have n on one side, r on the other side. So it's n things taken r at a time. And then here's the formula, n factorial over n minus r factorial. So two different ways to write it. And, you know, you can put, once you have specific numbers, you can put that in here around the P. And the formula, it's going to end up being pretty easy to do with code. You could just define these here and just put a, you know, n equals and then overwrite this code and write a variable, a number in there. But I wanted to set this up as, you know, prompting for input. So you don't even actually have to change this code, because it's going to prompt for input, how many things in the overall pool, and then how many, taking how many at a time. And there we go. And then that's what n and r are. So I call this p. I often do n for numerator, d for denominator, but I'm already using n. So I made this p for permutation. There we go. So factorial, and then the denominator, the factorial of n minus r, and then do that division, and then cast it as an integer. So there we go. And the answer, how many possible permutations. So we can run this and see. So it's funny that even, you know, some of the things in the overall pool, like let's say if I have like 10 things in the overall pool and taken, you know, 3 at a time, 720 possible permutations. There were, you know, that it seems like, wow, there's, you know, maybe, you know, an ice cream place that, you know, lets you mix up to 3 at a time. So 10 flavors, they can say, wow, we have 720 possible ice creams that we can give you. And a lot of places do that. They have, you know, only so many, you know, a little more than 10 even, and that number is going to be quickly up to 1,000, and they'll say, wow, we have 1,000 combinations, you know. But that would be order does matter. So probably not good with ice cream, because, like, yes, you could, it looks different, the order of the scoops, but it'll end up getting mixed together. So that's what leads us to combinations, when order does not matter. And this would be more appropriate to things like flavors, because, you know, just the fact that they're there, they'll end up getting mixed. So the order doesn't matter. You're going to mix them together anyway. But anytime, or if I'm selecting people for a team or a group where we're not defining the roles yet, so it's just, are you in this group or not? Or that's the cases where order does not matter. So we have combinations. So big C, the N things take an R at a time, and then the formula here. So notice combinations, just the fact that you're in the group, that's enough. So therefore, there's fewer possibilities because order doesn't matter. So I have that extra R factorial, the denominator's bigger, the overall number then is smaller. So same thing, we'll prompt for how many things in the overall pool. And then I have this. I just use the same variables, P for probability. It doesn't matter because that's just my in-between variable here anyway. Math.factorial and then factorial R times and minus R. So divide that and then cast as an integer. So there we go. So if I have this, so yeah, let's say, 20, let's say drink flavors, all the different juice or whatever they put in the drink, 20 different drink flavors taken 3 at a time, 11,000. And, there's at least one place I can think of that has that. They have, you get your slushy and, all the different flavors, but they only have about 20 flavors and they will mix up to 3 at a time for you. So then they advertise that they have more than 1,000 different drinks available. Pretty cool. So there we go. Permutations and combinations. Once you have the formula, then it's easy to then plug in the numbers and you can calculate how many possibilities you have. And that's what you want to see with it, is math. Think about the possibilities.
All right, so Pascal's triangle. Simple enough to generate, and so many patterns that seem to flow from this. So we look, understood zeros out beyond the triangle. So we're always adding that number, the two numbers next to each other. So 1 and an understood 0, there we go. We're adding the two numbers next to each other to get the next number, which goes in the row between them. So we have a 1 and a 1, and then we add that to make 2, 2 and a 1, and we add that to make 3. You see, and then there we go, 1 and a 3 to make 4, 3 and a 3 to make 6. There we go. So that's how we get Pascal's triangle each row. Straightforward, really cool pattern. All right, but that's not all there is to it. What else shows up as a Pascal's triangle pattern? Well, I could have binomial expansion. And I could have, if I have like a plus b to the 0, anything to the 0 is 1. That's the first row. I could have a plus b to the first, and then that would be 1a plus 1b. But then when I get a plus b to the second, so then I get, 1a squared b to the 0 plus 2a to the first b to the first plus 1a to the 0 b squared. So we see then we get this other pattern of these are the coefficients, but then the first term here goes to the second power to the first power to the 0, and the second term does the opposite to the 0 to the first to the second. And the same type of thing continues here, that it becomes a plus b to the third. So then that would be a to the third b to the 0 plus, and then this one would be a to the second b to the first, and then this one would be a to the first b to the second, and then this one would be a to the 0 b to the third. Pretty cool. And notice if you had this, then in writing it out, times 1, you might not write the 1. Anything to the 0 is 1, so you might not write that. But to fulfill the pattern, that's what happens. Pretty cool. Other things that come up with the Pascal's triangle is 11 to an exponent. And again, anything to the 0 is 1, but 11 to the first power is 11. And I wrote all over this, but 11 to the second power is 121. 121. 11 to the third power is 1,331. And, this one would be 11 to the fourth power is exactly this, 14,641. Pretty cool. It actually still continues, but then when I get down to the next one, then this has to carry over. So, it would be a 0 and then, well, then that's a 10, so the 1 would carry over, and then the 1 would carry over, so then that would be a 6. So then it really would be then 11 to the fifth power, 1,600, or 16,105. Then, it carries over. That's pretty cool, but it still follows the pattern. We just have to remember to carry. But, down to this, when you don't have to carry, it really works out. It looks nice. Other patterns. And I think I'm going to also include with the code, we'll do a little spreadsheet thing to show this, because if you just look at the even exponents, or just the even numbers that show up here, then you get kind of an interesting, I'm going to do one more row here. So 6 plus 1 is 7, plus 15 is 21. So then this would be 35, and then 35, 21, 7. So you see no more evens here, but these evens, 3, 2, 1, make a nice triangle. And then there's other triangles that show up in the evens, and actually the pattern of that is the Sierpinski triangle, which you can generate in other ways, but putting out Pascal's triangle and then highlighting or circling the even numbers gives you Sierpinski's triangle. Really cool. Other things that will work out more with the code, this also carries over to combinations, and how many elements taken how many at a time, and that would be how many elements that you start out with, that would be what row you're in, and then how many at a time going across, then the answer to that is how many different ways you can combine these things. I think that's pretty cool too. There's just so many different things that beyond what I could do justice with on the board. So we're going to look at it in different ways. I'm going to show you one way to generate this with code, and we'll look at, just briefly, maybe we'll look at a spreadsheet just because that spaces out kind of nicely to show some of those different patterns. And we'll look at some other things too to see all these different patterns. And that's kind of, again, some of the themes here in pre-calc. We're figuring things out, but we're also appreciating the beauty of all these interesting patterns that come up in math and in code. So let's take a look at that. Let's take a look at how this plays out in code.
Okay, so here's one way to generate Pascal's triangle. And I wanted to use combinations. I think in code this way works about as well as any other way. And remember with combinations, how many elements do you have? Then for Pascal's triangle, that would be what row, and then how many at a time, and that would be across each row. So we're just going to import math, and n is going to end up being our number of rows here. So I put that as a variable up top. That way you can generate different size triangles. Just change n right up here. And row as an empty array, spaces as an empty array. And I did this, and the next one's space string, really just because I wanted it to try to space it out to kind of look like a nice equilateral triangle, isosceles at least, rather than just everything lined up. Okay, so a lot of times for loops, I just do A and B, and this is first because after seeing it, I wanted to get a better spaced triangle. So just going through the range, each time I'm going to add to this string. So space string is going to have an extra 2 spaces here, and I'm going to append that to this array, spaces. There we go. We'll come back to that in a second. So then here's the triangle. So again, everything's in range n. And as long as if b is greater than a, continue. And then that way, that will just continue on. So I just wanted it to be, p for the variable. So this is what we have. Math.factorial a. And so that's our looping variable. So each one, I'm going to take that number factorial divided by, remember, the denominator is factorial b times factorial a minus b. So, there we go. So I can reuse a and b because all these are just within this loop. So remember, it's n factorial over n minus r, but I didn't want to reuse n. So this is really just the combination formula that we already talked about. And all that stored as an integer or casted as an integer, and that's p. And then that's going to be the row. So I really am just using this to append for the row. And then notice what I'm going to do is I'm going to print that particular element of this array spaces, which is going to give me the right number of spaces that I want. And in this case, it's n minus a minus 1, and you'll see how that kind of evens it out. So each of these spaces gets to be a part of this, this array, and then I'm going to print out that one, and then I'm going to print out just the row. And so you see that's what we're doing here. We're going to print out, a couple spaces and then the row, and then I'm going to clear the row because then I'm going to use it again in the next iteration of this loop. So, this is just generating Pascal's triangle. I have no need to store it for any reason. So that's why I have spaces, so it displays how I'd like it. And then each row, I'm going to go across and then output it. So what we have is Pascal's triangle. You see, it's spaced nicely along the left edge, and then just because we start getting double-digit numbers, now the spacing on the right edge, gets a little bit skewed, but I'm not really stressing about that. And we have one, there we go, Pascal's triangle. I could always make it, some other sort of list of, for each, but I just wanted to display this Pascal's triangle. There we go. We're only storing each row long enough to print it out. There we go. So that's, again, one way to display this. And we can see, some other just interesting things in the loop that we can do. And from here, now we can use this to generate, all kinds of things. So we'll go on to the next, and we'll make use of this and look at some other cool patterns.
So we also have geometric probability. If there's not something that I'm necessarily going to count, but I can look at the area. And so the geometric probability is the target area over the total area. So same kind of thinking, but having to do with area, not things we can count. So if I have like a bullseye, that bullseye, if I'm playing darts, in the center has a tiny area compared to the whole dartboard. So very low probability of being able to just hit that. Now, straight probability doesn't factor in skill. Maybe somebody's practicing and is a lot better. It's just probability. So there's a lot of sports, darts, baseball works a lot on probability, but there's still skill involved, which changes the probability, or somebody's tendency to throw to one side or the other. That could change the probability. But just straight geometric probability has to do just with the area, target area out of the total area. So therefore, lower probability to hit the bullseye, a little bit better probability to hit, let's say, the inner circle there because it's a larger area out of the total. So we see how we can calculate that. A lot of weather reports work on this geometric probability too, besides the probability that a particular cloud will actually rain. But if there's this rain cloud that we're expecting to rain, what's the area of the cloud compared to the area of the ground. So, in your town, what percentage of that town is covered by this dark cloud that could rain, and then that's your chance of rain for the day. So, you see, we still work on geometric probability, or if there's cloud cover, but, it's spotty, how much, what's the area of the cloud cover out of the total area of, the town or wherever, and we get our probabilities of rain. So there we go. We take a look at that, but where this really leads us into is other shapes like the normal distribution. Now, we'll get into the equation for that and everything, but our normal curve, so I can have scores here, and I could have a frequency, like how likely these are, and we get this normal distribution, looks like this. But connecting with statistics, then I can calculate the area under this curve, and a particular equation for generating this, like normal curve, would make the area 1. So then probability works out, and if I want to look at like the most extreme case, I might want to look at, what's that 5%? So, of that area, the area of this little part out of the whole area, then, maybe if the total area is 1, and so I want, something like 5%, so that would be like 5 out of 100 or something. If the area of this was 100 and then this little area was 5, or if this area was 1 and this would be 0.05. And given that, we can figure out, regard all these other equations, we can figure out, what line would this be? What would be the cutoff here to define that 5%? So this really, the geometric probability actually leads us into some other things we're going to do with stats and with calculus, because great, I could calculate the area of that. I have my circle formula, but how do I calculate the area under this weird shape here or any other weird shape? And that gets into calculus, breaking it down into things like rectangles and how we can do that. So it leads into, from probability to weather prediction to statistics and calculus, area under the curve. This, we're just scratching the surface of geometric probability here. But let's take a look at how we can do some of this stuff in code.
So let's talk about that probability distribution. And what we're looking at here, I think with rolling 2 dice, it's a nice discrete way to show this distribution here, where, all right, what can if I roll 2 dice, what numbers can I roll? I can't roll 1, that's not possible, because 1 on 1 dice, and then I can't just ignore the other one. But I can roll 2, because I can have a 1 and then a 1 on the next die. I can roll a 3 in 2 ways, because think about the sequence. I can roll the first die can be a 1 and the next one can be a 2. Or if I roll a 2, I still have hope because the next one can be a 1. And same with rolling a 4. We see the different ways. And again, think about a sequence here of I roll 1 and then I roll the other. 1 then a 3, 3 then a 1, or 2 and 2. And we see all the different ways we can generate. How many different ways can I roll a 5? How many different ways can I roll a 6? And we see that right here in the middle of our range is a 7, and there's the most ways I can roll a 7 compared to rolling any other number. And we see how for the higher numbers, it actually goes down. It's nice and symmetrical like this. There we go. And to roll a 12, again, only one way, because I have to roll a 6 and then a 6. And that's it. So, that gives us so when I look at the probability, I can look at like how many ways can I do this? Well, if I look at all of these and if I added these up, it's actually 36 different combinations here. And remember our counting principle, 1 out of 6, 1 out of 6, so 36 possibilities. And So if I want to roll 2, it would be 1 out of 36. Same thing with the 12. Probability is 1 out of 36. But for rolling a 7, 1, 2, 3, 4, 5, 6 different ways. So it's 6 out of 36 or 1 out of 6. Probably the most, it would be the most common number. So a very good way to show this. So let's look at a couple ways we can see this as a graph. Just looking at each of these numbers and then how many ways can we do this. And we're going to go back to the matplot library.pyplot, import as PLT, and I'm going to show you a couple ways. One way, I can create an array of X values for each different roll, and then an array of Y values for how many different ways I can get that. You see, and it all matches up here. So I can do that, an array of each, and what I'm going to do is plt.hist2d, 2D histogram, and these are each arrays, so I'm going to plot X, Y, and then I'm going to define the bins. So that makes it, we sometimes it comes automatic. How am I going to divide up these bars or these areas of my bar graph? And a lot of times you can skip this argument bins, but I recommend not doing it because then it might group things not the way you want to group them. So code-wise, you can skip it and Python will put in some default, but I recommend not doing that. So I'm going to have 11 bins for my X and then 6 bins for the Y, and we'll see how that blocks that out. So when I run this, I've commented out the other way. So this is how it shows. I think that's kind of cool. And we see, it displays it nicely, just the maximum of what's possible. So that's one way. Another way, and what I'm gonna do is I'm gonna comment this out, and I'm gonna uncomment this. So notice when you do up here figure x for fig x for variables, and I'm gonna use x.hist. So this is another way to get a histogram. So here, I'm going to create this array of all these values here. And notice in my array, I'm going to put 2 and then 3 shows up twice. 4 shows up 3 times. And I'm going to write it like this in my array. This is a good use because a lot of times when we get data, it might be in that way. We want to, from that data that we get, we already have something like this where things show up a certain number of times. And so I might have an array like this. And therefore, I'm going to graph that. Look, that's just the first argument is that array. And then here, I'm going to, again, define the bins specifically as not how many, but exactly where I want my cutoff to be. And you see, then my highest one's 12, so then 13, I want, to include in that last bin. And so when I run this instead, we get this, our classic histogram. So then we see again each value and the number, So we see this nice regular distribution where some values in the middle are the most common. And then as we get further away from that middle, it's less common. That's the concept of the normal distribution. So we'll come back to this in a second as we talk about the area here. But that's the normal distribution. And if we had things that were even more continuous, instead of making it some sort of bar graph like this or histogram, this equation actually defines it defines a line that would be the top of a normal distribution. So all we're doing is we're just going to graph this here, but this is the equation. And even though we see e to a negative exponent, which could just easily put that in the denominator and just 1 in the numerator. This is actually a pretty common way to write it, I guess just because the denominator is already crowded enough. I don't know. But there we go. So given this, then I'm going to define my minimum and maximum values here, and like our other graphs, number of points, and then I'm going to create that as an array, np.linspace. Graphing these, I am going to include, the window size. I'm going to plot an x and y axis to give you a reference. And then here is that equation just converted to code. So in the code, I did put it all in the denominator. So in the code, I did have 1 over, and then I just did math.e, that exponent, math.sqrt, square root of 2 pi, and then I'm going to plot these. We'll come back to this other stuff later. So when I run this is the normal distribution, or that, bell curve that you may have heard of. So this is like an ideal if there was like continuous data of all these different things, whatever I'm measuring, and, how far away from the mean, which would be in the center, that would be a nice regular distribution. And, that's what we have. The x value would be standard deviations. We'll get into that, as we talk more about stats. But, essentially how far away, if the mean or the average values, 0, then how far away from the average are we getting, above and below? And then the y value would be frequency. What's the frequency that this shows up, that a score like this will show up? And these medium or normal values have the highest frequency, and then it trails off as we go. And we can do calculus to get the area under the curve, but I want to show you just, I'm going to uncomment these. If I could just get the area approximate. And what I did is I drew some triangles here to show you. You notice it's approximate. We're skipping a little bit, a little bit here, not under in my triangle, a little bit here where it's too low, a little bit here too much, and it would even out. But the reason I picked this particular triangle is because I went from -2.5 to +2.5. So the area of the triangle, 1/2 base times height. So half the base is 2.5 times the height, 0.4, and that area would be 1. And so really we take it as the area under the normal distribution is 1. And then we look at like percentages, what values here give me a cutoff point of, 2%, 5%, 1% of that area. That's what we're looking at. And something over there where I'm only under the top, 5%, I'm going to say that, often that's extreme enough that, wow, that's news. So there we go. So just approximating this. And here with a histogram, because it's already blocky, we can approximate this. And remember that the width of every one of these bins is 1. So I can just make this a bunch of rectangles and calculate the area. The width is 1. So then the height is 1. So, the area is 1. In this next one, the area is 2. Next one, the area is 3, then 4, then 5, then 6. You see? And then we can get an area under here. And so we can look at another way to look at probability would be, this area, I would, just as we were adding up all how many ways this can happen, the area under this should be 36. And then so just the area, what's the probability of rolling a 12? that should be 1 out of 36. So we get it, we can see the numerical probability with the formula, and we can also see the geometric probability. And that's we want to see that connection and see that overlap. So there we go. Now, just connecting this with calculus, this is pre-calculus, but just to give you an idea, we could break down this into a lot of little rectangles with really, really narrow sides. And the idea is just like pixels or resolution on the screen, the more rectangles, the better the resolution, the better the approximate area. And calculus finds a way to take that number of rectangles to infinity. But that's where we get here. So, this is kind of like the sense of the normal distribution. You see, we see it as actual countable probability. But then we also see, the theory. Here's this general curve and ways we can look at this. And that's, all of this, it's good pre-calc, and then it leads us into our understanding of statistics. So much of it relates to probability and counting. How many ways can something happen, and, what I'm looking for, how many correct out of that, like what's the probability of that happening. So there we go. Some cool things and some interesting distributions you can tinker with.
The math of betting, the short answer is it's always against you. If we're not talking about skill or anything else factoring in just probability of something, anytime you're gambling, you have the probability against you. If you flip a coin, you still have 1 out of 2 chance. Roulette, your wheel goes around, even if you say, all right, I'm going to bet on, black or red, that's still not quite half because you still have 2 green zeros. A lot of other things then get, lower and lower odds. Like, for example, winning the lottery. A lot of games you have pick 3 numbers, pick 4 numbers. So, let's just talk about this. If you pick numbers and each digit, they come out of a bin, 0 through 9. So there's 10 possibilities. You have 1 out of 10 chance of picking that number. But if you have another number, you're only win if you get this and that one. So that's also 1 out of 10. And you multiply the probabilities because you're only correct if you get this one and that one. And then another one, so that would be, 1 out of 10. And you see, 1 out of 10, let's just say 3 numbers, that's a pretty common lottery. Pick 3 numbers. But remember then, the chances of winning are 1 out of 1,000. And the payoff, the idea is that the payoff is going to be less than $1,000. Way less. So you can't just, buy every combination because you'll lose money. Yeah, it's, interesting. So the, and if we get to like the larger lotteries, it works on the same principle. But you might have, pick, maybe 5 numbers, but maybe there's 50 total and they come out of the same bin. So picking the first number correctly, it would be 1 out of 50, but then it's all out of the same bin, so 1 number was used. So then the next one would be 1 out of 49. And again, we're multiplying those, 1 out of 48, 1 out of 47, and then times 1 out of 46. And that would be if you're picking 5 numbers. And so still it's 1 out of all of these multiplied. It gets to be a large number. And again, usually the payoff is so much, or is such that it's not worth buying 1 of every ticket. Some people have actually tried this, and they've gotten together with investors when the lottery jackpot gets to be a certain amount, and then they try to buy 1 of every ticket. I heard one person talk about gambling as a tax on people that aren't good at math. I think that's kind of funny, but still, nonetheless, any of us, here and there, we might say, oh, let me take a chance on this. Why not? Charity auction, so we know that if I lose, the money went to a good cause. But that's really, the math of betting. And what we're going to look at in the code is, so that you don't have to play with your own real money, is different ways that we can generate, place a bet, pick a card, something like that. And, did you win or not? And then add or subtract from your, from your bank and simulate this and see that, after only so many attempts, you end up with no money left. So we'll look at some of those, simulators that we'll create with the code. So let's take a look at that.
So this is just a gambling simulator, just to show you, some probabilities here. We're going to import random because we're going to generate a random number. So from that range, I'm going to give you a bank account and we'll look at that. And what we're doing is we're just going to prompt for some input. There we go. Sounds like a sentence, so maybe I'll capitalize that. Guess the number between 1 and 11. Store it. And here I'm just going to print the number in the guess once. And if it's correct, it's going to print you win, increase the bank, or you lose and decrease the bank. There we go. So in this case, essentially you win $1. That guess the number between 1 and 11. All right. 5. Well, but it was 10, so I lose. And see, I didn't print out a bank account here just to show you, here's one way. Here, we're going to expand on that. Start out with this bank here. Guess a number between 0 and 999. Because we can have all zeros and we can have 999, but we can't have 1,000. That's 4 digits. So here there's a reason why I have this loop, because right now we're just going to do it once, but I want this to loop, that we're going to have this bank account and we're going to generate a random number from 0 to 1,000, because remember, it won't pick 1,000. It'll pick 999 as the highest. And later on in the walkthrough for certification 5, I'll do this random number generating in a different way. But here's one, just generating this random number, and we're going to print out the winning number, your number, and we're going to say in this case, if you win, it's going to print that out and give you $100. Or if you lose, then you lose the $1 you spent on the lottery ticket. And after doing all that, then we'll print out what's in your bank account. So there we go. 789. How about that? 594. You lose, so then the bank account's 399. And the reason why I have this, so we can comment these out, because if I want to loop through this a bunch of times, I don't need hundreds of print statements. So we can comment out these print statements here. And let's just say we play this every day for a year. Now, let's even make it more than a year, because if the bank, you start out with 400, supposing you play for every day for 400 days. There we go. And you have this, if you do win, boom, you get the $100. So that's going to be even more. If you lose, you only lose $1 what you paid. And there we go. 6 to 9. Bank account 0. So probabilities against you. Or here we go. 2, 8, 3. Bank account 0. And this is what, sometimes in doing this, you want to be thankful that we're just dealing with variables instead of real numbers, because that could have been, oh, I lost another 400. Oh, I lost another 400. That's kind of what I want to show you with some of these gambling simulators. And, we'll get into looking at a couple others, but the idea is because the odds are always against you, who knows, maybe it's nice every so often to plunk down $1, a little bit of anticipation. Wonder if I win. But long term, it's always against you. And the gambler's fallacy is that, oh, it's been against me so long, it's got to turn. I'm due to win. but there's really no such thing. So there we go. A couple different ways to look at this, just generating random numbers and comparing, your guess to the other random numbers. And we'll take a look at how this plays out again in other situations at the end of the Foundational Math 5 certification project. So here we go. Some good things to think about and some code to write for this.
This is going to be a walkthrough of Foundational Math Certification 5, but please make sure that you do this or give it your best attempt before looking at this, because this walkthrough is going to show you, but the goal is that in going through everything in this course that you're able to do this on your own. And it's a little bit of a review, a little bit of a test, and in going through this, you'll see that, oh, I've been able to do this, I've been able to do that, and I've been able to build this and that. And, it completes, a lot of your math journey here to this point that, you'll have all these skills for the next thing. I mean, so many things you'll be able to do. So, yep, so here, this will be the walkthrough, but hopefully, if you're watching this, you've already given it an attempt and maybe you just want to go over some things. So here we go, the walkthrough for Foundational Math Certification 5.
So here's the walkthrough of Foundational Math 5. And hope you already did this and you're just going through checking up. But here we go. And like before, step 0, we just need to acquire the testing library. And you should also see how you can, post your own library of various functions on GitHub or wherever, and use this to access that library, and then you have access to all these functions. So there we go. And in running this, it will then make that connection, import this, and run that first function, which will output one more thing. And this is about how long it will take. And then running that function will output this code test passed. And it is. So remember, this one we're focusing on a lot of sequences and series and those sorts of patterns. So a sequence is any group of numbers in a certain order following a pattern. So here's how we can do a loop to generate that sequence. And I'm just going to say, here, this one you don't have to change anything. Just giving you an example of the loop. For A in range, from 1 to 7. And remember, Python, then 1 will be the first number, but then 6 will be the last number. It will always be less than that. If I say 1 to 7, it'll end at 6. So there we go. And it's just going to print, A squared, comma. And this is a nice thing to add. You'll see how this displays that. And you see, so it ends this and puts the next print statement on the same line. So notice this print statement is not in the loop, but putting this here then will put that next print statement on the same line. Sometimes that's nice. And in doing this, then we can take a look, 1, 4, 9, 16. So there we go. What would be the next number? Well, we see here how we generated this as A squared. So the next thing would be 7 squared, 49. So that's just one sequence. Arithmetic sequence is anything where we have something that we're adding or subtracting to get the next number. So the nth number, because n starts at 1, when n is 1, that's the first number. So the nth number is the first number plus the difference times n minus 1. And that's because n equals 1 for the first number. So here we go. So you're going to do this, and this is a carryover from before. But what we want is, we want this to be we want this to write a loop that generates a sequence beginning with 3 and adding 2 each time. So beginning 3, adding 2 each time. So if we start here with the range 1, so we have 3 plus 2 times n minus 1. So if that's the first thing, then a minus 1 is this. So you see, it will start with 1. And so for the first number, it's just 3 because 1 minus 1 is 0. And then the next one, it'll go 3 plus 2, 3, etc. And there you go. And you can keep this at the end, which we will do. Why not? And there we go. Starting with 3, adding 2 each time. There we go. So getting an error like this is supposed to be a little bit of a give and take. So, don't stress about it. Notice it's just an adjustment. This will work. And I was just going through and thinking of a different way when I was creating this. So notice the adjustment. Instead of range 1 to 7, we could just say range 7, which understood starts at 0, which then means I don't need to have that a minus 1. So that's just something, we could do it one way, and that is perfectly correct. But, take the feedback as give and take as here's another way to do this. We could just say range 7 starts at 0, which means we don't have to do that part. And it's just interesting converting always, code and arrays usually start at the first element is 0, and some things in math, the first element is 1. So there we go. So just, these are some of the things that hopefully I can point out in this walkthrough. All right, and in a geometric series, you're multiplying or dividing something. So the nth number is the first number times the ratio to the exponent n minus 1. Because, again, we want to take it as the first number, n equals 1. All right, so now we're going to take this, and we want to write a loop that generates starting at 3 and doubling every time. And since we're doubling, I didn't want to start at 2. That, want to start at 3 and make that one more step here. So if we just take this, so we see it's, not a squared, but we're starting at 3 times this to the exponent times 2 to the exponent a minus 1. Now, I could, like we were doing before, 2 to the exponent a, and go like this, and it starts at 0. So we see that's what we have, 2 to the exponent a, because when it's 0, then that works out. And then we see 3, and then doubling every time. There we go. So yeah, you could do it the other way also, but then it will give you that suggestion, hey, do it this way. Just, and again, we're often going for, this, if one way is a little bit simpler, a little more straightforward, we'll do that. So there we go. And now sequences as Python lists. So lists, you really could use the word array interchangeably. There might be some subtle differences, but we'll call it a list here. And there we go. So lists are indexed, means that each element has a number to it, and the first index is 0. There we go. again, contrasting with the math sequences. So we have this, and we can have the entire list. So notice what we have here. If I just call this a list, and I'm going to say that that I have 5 in the list. There we go. And the comment here, a list 0 is 5, element 0. So I can do this. Since I have element 0, then I definitely want that 1 in there, because I don't want to start with element 0. And then I have the next number. Well, let's so we're going to multiply by 2 and then add 3. So if I take the next number, then I really want, notice n starts at 1. So if I want a list, element n minus 1, then that gives me my previous number, which in this case is 5. And then if I want to create a sequence where I multiply by 2, then add 3, so I take that previous number times 2 plus 3, and there we go. So we have that previous number times 2 plus 3, and then I'm going to append that to the list. So a list.append next number, and then that way, that's another way we can do this, and we can just append it all to the list and then print the list at the very end. So there we go, and we have this. So the next one, recursive sequences. So recursive is when you know the previous number and you need to know the previous number to generate the next number. So it's dependent on that. Whereas some of the original arithmetic and geometric sequences that we were looking at, you can just jump to, you have the formula, you can jump to the 50th number. But here, if I have, let's say, a Fibonacci sequence, so I'll call this fib 1, 1. So that way I'm creating this list that the first element is 1 and the next element is 1, because then I need to generate the previous 2 elements. So, there's your hints here. So if I have the Fibonacci sequence, I already have the first element and the second one. So we're looking at Python list, so it's 0, element 0, and then element 1. So then I'm going to start my loop with element 2. And so what I'm going to have is next equals fib n minus 1 plus fib n minus 2. And we see this, so I'm adding the 2 previous elements to get the next one, and then I'm going to append that to the list. And that way I needed to generate, these first 2 elements so that I can reference them here. And element 0, element 1, so in my loop I start with element 2. And then doing this, all right, up to 11, that works. So then I can print the whole sequence, and there we go, 1, 1, 2, 3, 5, 8, etc. Pretty good. And yeah, that's it. So the Fibonacci sequence, it'd be tough to jump to, the 100th element because I still need the 2 previous ones. Now, you can graph these. Sequences, remember, are discrete, so that means it's not continuous. I want these nice integers, these in-between decimal values and such, are not really a part of that. So here's one way to do this. I can just plot them as points. So A list and then B list, and generate the axis here. And so I can plot. So I can plot n because I'm going through this loop for n in range, the length of a list. So you see I don't have to count them. I can just say in range based on this length, and I'm going to plot this point. So the first element, and then, that's the x value, and then what is the element in the list? That's the y value. And I'm going to print that as a red dot. There we go. All right, so we can run this, and a lot of these I have you run it, see what this looks like. And we see that curve, but I just have the dots. It's not a continuous line. So you see, element 2 is here, element 4. And there we go. So when we change B list, so then make B list the new Fibonacci numbers. So I can make it however many, 2, 3, 5, 8, 13, and maybe we'll stop at 21. And so the length of that list, I could have made it any length because I'm referencing that here. And so that means I should change this because I'm referencing B list now, and down here I'm referencing B list. So now I want the range of B, I change B list, and I want the range of the length B list, and I want to reference here. I'm going to plot the elements in B list. And just like B list could just sit there before, A list can just sit there. That didn't take up too much, and I don't have to reference it later. So now we have this, and just given this range, because I stopped here, there we go. We have these dots. And that would be, again, graphing that sequence. So that's the way a lot of sequence graphs look like, a sequence of plotted points, but not the lines connecting them. All right, so if I have a series, now the difference with a sequence and a series is you add them up. When you add up all the elements in a sequence, then it becomes a series. So here, rather than generate an array or a list, then what I want to do is I have a sum variable start out at 0, and then I'm going to just add each of these. So there we go. So if I have some element, and so here I have, my element is 2 times n plus 4. Now, notice I just wrote it like this, but it could be 4 plus 2 times n. That works just as well. I could have changed this to start at 1 and make the n minus 1, but that seems a little bit excessive. So really, all I'm going to do is add this code here, sum equals sum plus element. There we go. So each time it generates the next element in the sequence, but since I'm adding it up now, it becomes a series. And so we're going to print out the sum. There we go. And we could have also put in here, add it to a list and display that as well as the sum. We can combine those. So as you see, we're just going to keep adding it. The number's going to keep getting bigger. But we actually have two different types of series. We have divergent and convergent. So divergent, the sum keeps getting larger. It diverges. And usually, we'll just say toward infinity if we have enough elements. But a convergent series actually approaches a definite number, which is really interesting. So that happens usually if the denominator keeps getting bigger than the numerator. So there we go. So now here we're just going to run this code just so you can see this. And we see in range 11, so my element now is 1 over 2 to the n. So the numerator still keeps being 1, and the denominator is 2 to the n. So 2 to the 0, 2 to the first, 2 to the second, all these smaller and smaller numbers that will converge. Now, my range is just 11. And we see the sum here, not bad. Now, same thing, I'm just going to change the loop to 42, as just some random number that I just thought of. It did not take me a million years to think about this number. And if we run this, so we saw before it was 1.99 and then a couple things, 1.999, a lot more nines, and then we get to this. So now we're going to change the range to 100 and see what that does. And look at that, 2. So it does converge. I didn't even put anything here to round. It got so close, 1.999, so many nines, and it converged. And we often say, well, okay, as n approaches infinity, it should converge. We didn't even get close. We just even went up to 100. So that's what we see, because the denominator's, 2 to the n. So 2 to the 100th power. That's a huge number. So 1 over that's a very tiny number. It keeps going. You're adding tinier and tinier numbers. And so it converges. So factorial, another way for numbers to get bigger and bigger. Factorial of a number is the exclamation point, and that means it's multiplying that times everything less than that. So 5 factorial is 5 times 4 times 3 times 2 times 1. And I know that times 1 won't change it, but it completes the pattern. So 5 factorial, then multiplying all that gets you 120. And so by definition, 0 factorial is 1, because 0 factorial, these come up in situations where it's like combinations. How many different ways can things happen? So 0 factorial, if I have 0 things, how many ways can I arrange them? Well, 0 ways. I could just not do anything. And so that's one thing. That's one way. 0 things. The only thing I can do one thing, which is not arrange anything. And so that, it's kind of like the verbal explanation for 0 factorial. But anyway, by definition, 0 factorial equals 1. So in Python, we're going to import math, and then we have math factorial function. All right. So there we go. We're going to put something else here in the print statement. So we see if I have the number, we can keep it as 7. And then what I have it is printing that factorial, notice no space, equals, well, let's add this. Let's make it math.factorial number. And I'm just going to reference that variable. That way, if I change it, I don't have to change it multiple places. And then I have this code here, just so you see, for n in range number minus 1. So I have number minus n times, there we go. And we will see that this prints out 7 factorial equals, and we saw that we calculated that number up here, and it'll also just display 7 times 6 times. There we go. Because that's what we're doing. We're always doing the number minus n, so we subtract more each time. Just a way to display it as well. So Euler's number, which we usually see abbreviated as E, and we talked about this in other parts of the math course. So
there we go. So E, and again, it wasn't Euler naming the number after himself. It was other people much later, calling it E as a tribute. So this is a convergent series. It converges on this odd number here, but still. And it's the sum of 1 over n factorial. So, like we were looking at the harmonic series before, so, I have my sum, the range, we'll start here at 11, and you see 1 over factorial of that, and you see I just have range 11, so it starts at 0. 1 over 0 factorial is 1 over 1, which is 1. So we're going to generate that, 1 over each of these, and pretty good. 2.71828, and then 18. I mean, it's actually, even just going up to 11, it's pretty close to that number. But then if we change it to 100 instead of 11, we get that a little bit close, 2.7, 1828, 1828, and then, yes, that pattern does break down after a couple times. So, a much more close approximation. And remember, it's as n goes to infinity, we stopped it at 100. If you really wanted to go up to 1,000, it doesn't, this is more than what you need to do for this. And you see, very similar, even just going from 100 to 1,000, 1828, 1828, and then 459. Yep. Oh, and see, it'll give you the error. And each of these errors, there's no point value. Going through this, hopefully you've been, tinkering with different things as you go through this. Each of these notebooks. So probability. Very often probability, and we'll see that factorial and such will come back around again. Probability, likelihood of something happening. So we're always counting the number of correct outcomes out of, so we divide that number out of the number of possible outcomes. So there we go. So randomly selecting one's birthday. If I'm just going to randomly guess somebody's birthday, there's only one day out of 365. So we can just count and look at this probability. We can just say correct divided by possible. And for a simple thing here, just these couple lines of code, therefore you can always go back and change these numbers to be, anything, and there we go. So, 1 out of 365 or, 0.0027. All right, so then when we have probability of A and B, it's only correct if both of those happen. So what we end up doing is we multiply the probabilities. So like probability of flipping a coin and landing it on heads, we're going to look at 4 times in a row. So the probability once is just 0.5. Yep, because it's either going to land heads or tails. Then the combined probability is 0.5. Now, we can do this probability 4 times because I'm multiplying that same thing to the 4th power. There we go. I mean, you could have written probability times prob times prob. This is a much more efficient way to write it. And there we go. So that's the probability of getting heads 4 times in a row. And now, it's still just a probability. I mean, that chance is not 0. So it's still possible. So this is where we get into like the gambler's fallacy. So because it's such a low probability, if you were betting somebody and, I bet that it's going to land on heads and it was tails. And then, 3 times in a row it was tails. And then so you still, the next time you're going to bet heads again saying, such a low probability, then, I'm due to be correct at some point. But it's still, they're each independent. So each one flip, it's still 1 out of 2 chance. In the whole situation, it's this low probability, but if it's a fair coin, each instance is still 1 out of 2 chance. So the gambler's fallacy looks at these lower probabilities as you string together multiple events and says, oh, wow, it's been tails so many times, I'll bet on heads it's due to come up. But, things don't necessarily work that way. It's still, you could land on tails again. Same thing with, betting on, slot machine or cards or dice. There's no, it's due to come up. It may be a lower chance, but it's still, there is a chance that this could happen. So probability of A or B, we add the probabilities. So it's correct if either event happens. And so, that's like, buying 1 lottery ticket, and then, if you buy 2 lottery tickets, you doubled your chances. I mean, it's still tiny, but it's doubled. Or pick a number from 1 to 10. If I pick one number, but then if I pick another number also, now I have 2 chances out of 10. You add the probabilities. So there we go. Combine. So here we're going to calculate the pick 3 lottery if I bought 7 tickets. So the combined probability, so it's 1 out of 1,000 because it would be 1 out of 10 times 1 out of 10 times 1 out of 10, picking 3 digits correctly. But then the combined probability, if I have 7 tickets, I'm just going to say prob times 7. Because really, I'm not going to write it out to add them up. There we go. Oh, or we could do that. So, all right, probability plus prob plus prob. One, 2, 3, 4, 5, 6, 7. Just to really accent the fact that it is adding it up 7 times. There we go. Okay, so instead of 1 chance out of 1,000, you have 7 chances out of 1,000. And combinations. So how many different ways can we arrange things? So the numerator side, I often know how many correct things I want, but how many possible ways, the denominator part of it, we have these counting rules because there's a lot of different ways to look at this. How can I figure out how many different possibilities? And so combinations are unique groups of size R that you can make from a pool of n things. So when we write this notation here, so NR, so we can say n things taken R at a time. And then we put the big C because it's combinations. So there we go. And then here's the formula. N factorial over n minus R factorial. But then the denominator is even bigger than that because it's times R factorial. So how many 5-person starting lineups can it have? There's 12 people on the team. Now, this is, I guess this would be like an informal game because we're saying order does not matter. So 5-person starting lineups, we're not going to assign any particular position, whatever sport this is. We're just going to say, yep, groups of 5. How many different ways can we do this? So there we go. N is 12, R is 5.
5 at a time. So we have this formula. So I already imported math. So we're going to do math.factorial n divided by, and then we have, I'm going to put all this in parentheses in the denominator, math.factorial r times math.factorial n minus r, and that should be correct with the parentheses. So n factorial over r factorial, and not plus, but times math.factorial n minus r. Close those, close the denominator parentheses, there we go. And so when we run this, so 792. And this will be a decimal. You probably could cast it as an integer, but I didn't worry about doing that. Doing this, we would expect an integer value, but also dividing, Python wants to default to just a float because you're dividing, that you could end up with decimals. But there we go. How many possible starting lineups? 792. So, if we think about that, then, wow, a coach has 12 people on the team. How many different combinations? Who's starting today? 792 options. Wow, it's pretty overwhelming it's a lot of things for a coach to think about. Now, permutations, you're counting how many possibilities, but order does matter. So, like it has the word mutation in there, changing things around, but the order does matter. So there we go. So if you have 8 different participation trophies and you want to pick 3 to arrange on the shelf, it's not just that they're on the shelf, but what order are they in? That matters. If it would be the people winning, in the Olympics, gold, silver, and bronze. So it's not just 3 people on the medal stand. The order does matter, gold, silver, and bronze. Or, like this, books on the shelf, trophies on the shelf. The order does matter, so it's permutations. And the formula is similar. Notice the setup, but with the big P for permutation. And the formula here does not have that extra R in the denominator. So we have, more possibilities, because, if I have, gold, silver, and bronze, let's say, on the medal stand in the Olympics, but if it was rearranged, same 3 people, but they won different medals, that's a different permutation. So we have more options here. So in this example, 8 different participation trophies and 3 to arrange. So 8 things taken 3 at a time. And so we're going to have this math.factorial n divided by math.factorial n minus r. So there we go, number of possible arrangements. 336. Wow. So you see, the possibilities become a lot more. Now, Pascal's triangle, one of the things, if I just print this out, we can see Pascal's triangle here. It links into, you can generate Pascal's triangle with with combinations. So I wanted to include this here because it's an interesting pattern here. But if you just printed this out, this is what it is. And
You see, so beyond the triangle, it's like understood zeros for the nothingness, and you're always adding the number and whatever's next to it to get the one below. So then I have 1 plus 1 is 2. So that's how we get this 2, because adding the 1 plus 1. And then down here I have 1 plus 2, and then that's where I get the 3. And then here, same thing on this side, get to this 3, and then 3 plus 3, get you this 6.
And now let's look at how to use combinations to create Pascal's triangle. So you might already have this code if you were working along with some of the other assignments. And I'm just going to recap here. We're going to import math. And I'm going to create these variables here, n for the number of rows. So that way you can change that once up here and, have all different rows. An array for what's going on in each row, and another array for spaces, because that'll just, I think, make it look more like a nice triangle. Otherwise, everything just gets lined up on the left side, and I don't know, I think it loses some of the effect there. And with that, I'm going to have this space string that I'm going to incorporate here. So this is what we're doing here with the spaces. So each time I'm going to add or append another space to the space string variable. So each of these is going to have, so many spaces, and we'll see how that plays out later. Then I'm going to go through, and for everything in range, I'm going to, so notice if we go through here, for it still to be a triangle, we'll continue. So this is the combination formula, which might seem familiar by now. And there we go. So, we're going through A and B. So, A things taken B at a time. And so therefore, if B is greater than A, that just can't happen. And we go through, and after all this factorial, we just want to make sure we do cast it as an integer. So there we go. And then I'm going to append that to the row. So what we're doing is this for each row. And then I'm going to print those spaces and then the row. And then I'm going to clear the row. Notice all that's still in this loop here. So it just goes through this, and each time then we're going to create the row, print it out, but then clear it for the next time. So notice how the spaces, our space array just gets larger and larger. Each element has more spaces, so we are working backwards there than putting the spaces in. So the first row has a lot of spaces and less as we go down. So when we do this, all right, let's see, 8 rows, and we run this, and we will see 8 rows appear. And you see the spaces give it that nice triangle angle. Over here, it falls apart a little bit because now we start getting into the double digits. But these are minor things relating to spacing, if you wanted to change something. But there we go. So we have Pascal's triangle to 8 rows. And using the combinations, which I think, in terms of generating it, I think that's a pretty good, reliable, manageable way to do that. And then from there, we can use these numbers for anything we want. All right, pretty cool. So this certification project now. And I put this in here for you about creating a deck of cards. And there's other ways that other people have done this. I just decided to do it this way to really write out what cards. But a lot of times, and we'll look at this in some of these examples here, but there's a lot of other ways people have, like, just the one number or the letter J, Q, K, A, and just the letter for hearts, clubs, diamonds, spades, H, C, D, S. So I decided to write it all out, and this is just one way to do this. So here we go. So I have an array of all the cards, of all the suits, my array, which is going to be the complete deck. Right now it's empty, and temp card for now. So notice then I'm just building this deck for A in range cards and B in range suits. I'm going to go through, and this temporary variable, string variable, is going to be, that of that. So it's going to be, we have a 2 of hearts, a 2 of clubs, a 2 of diamonds, a 2 of spades, and then we'll go to a 3 of hearts, 3 of clubs, etc. And each time, that's just going to be the temporary string, and then we're going to append that, so now the deck has all the cards. And we can print this out. So when I do this to print this out, there we go. And as I mentioned, a lot of times people might do this just the number and then one letter. That works out nicely. We could do that just as well. So here's what I did as some examples of some things you can do, and you might do some of these, you might take it further, but this cell, I run this cell and creates the deck. That's there, and that's going to continue. Remember, the runtime in Colab is about a half hour, or about a half hour of inactivity, maybe 20 minutes, or even if you keep going, it might go 11 or 12 hours. So that code and those variables still exist for a little while, so I can do other things in these other cells referencing them, and that's going to work. So in this other cell, I just have one thing. Let's just draw one random card. Now, here's what I have, just as reference. Print the length of the deck here, and I'm going to draw a random card, and what I have is, from 0 to the length of that deck of cards. And remember, that's a random integer. So pick is going to be a number. It's going to be a random integer. And then pick 1 is going to be that particular card. So then we'll just print that out. Your card is pick 1. This, if, I have a game, I don't want to use that card again. It's already been picked. So I'm going to pop that out of, and again, I needed that variable as the index. I'm going to pop that out of the deck, and then just for reference, print the length of the deck again. So you see 52 cards, here's your card, and now there's 51. Now, this goes along with the next code block here. I decided to have one cell of just your points and computer points. So I can run this, and again, now those variables exist because now I can keep this. Now, the deck is still there. So right now we have 51 cards, and the ace of clubs, that highest card, is now not in the deck. For right now, for our examples, we can leave it like that. But you could always go back and run that original cell and then generate the deck again. So that is possible. All right. So this challenge is, create some card games. I just decided to pick a few simple ones, but there's definitely more complicated ones, and I really wanted to be more about the code and not so much about all the different rules for card games here. So war, you each put down a card, and who has the higher card. So what I have is, so pick A, so that's going to be the random integer, and then the computer's card is going to be from the same deck, that index. And we're going to print what the computer's card is and pop that off the array. We'll do the same thing for your card. Pick B, random integer. And then your card is a card from the deck with that index. There we go. Print it, pop it off the array. So now when we compare, and you see what I did is just if your card, so each of these, remember your card 0, your card is a string. So index 0 is the first character in that string. So there you go. If it's 1, then your card is a 10. Because that's the only way, that's the only way 1 would have showed up as the first character. J. So I'm giving values to each of these. So, if the first index in that string is 1, then the value of your card's 10. If it's J, that must be a jack. The value is 11. Q, it's 12. K, it's 13. A would be 14. And then everything else, it's whatever that first index is, and then cast as an integer. So, a 2 of clubs is going to be a 2 of value. A 3 of hearts is going to be a 3. There we go. So, again, these are some of the things, once you work that out once, how to compare, you can use that. And so I do this all for your card and then all the same things for the computer card. So now each of these have a value. So we have your number and computer number for what cards you have. And there we go. We just go through our comparison. If your number is greater than computer, you win. And then this is where I have the point values increasing. Your points, you see. So I have this once that it initializes. And then if you win, you get a point. If you lose, computer gets a point, or it's a tie. And it'll print that out. So you can run this. And you'll see the computer got a 7 of clubs. And you got a 6 of diamonds. So you lose. And the computer gets a point. And the idea with initializing at a separate, so you see, the deck was created in a separate code block, initializing the points in a separate code block, so we can just keep running this for every hand. And you see, so computer got a jack, you got a 2, computer won again, another point. And you can run this again. Look at this, you won this one. And we can keep going. You can keep running this. There we go. And what I have here is if it ever gets to, if the length of the deck is 0, then game over. All right. So there we go. And that's just one example of a game. Now here's another one. There you go, 5 card stud. So now this one, I just wanted to display 5 cards, yours and the computers, and then take it from there. But there are, again, more intricate ways to compare poker hands. That gets pretty involved. So, you can even do things, drawing cards and switching them out. But I just wanted to show here just, how it prints the computer's cards and how we can do the same thing. I have a pick. And I'm going to create this random, from the deck. Now, this is also continuing on. We're using that same deck. So for our purposes, this is going to be fine. But to really play this, I would go back again to that original and then recreate the deck, which is, you know, there we go. So I'm picking a random card and then popping that off the deck. So I'm going to do this 5 times because, you know, each person gets 5. So the computer gets 5 cards, printing them out, and then you get your 5 cards. And I just had it print who wins. So it'll just, you know, here are the cards. And then you can say, you know, who wins. So just some interesting things we can do with displaying. Now, the initial thing said, you know, card games, but, you know, any other gambling. Here I have, you know, initializing that the bank. This one, I put it in a loop. So initializing your bank account is in the same code. So then, you know, your bank account, and it's going to print out your bank account equals. All right. And what you're going to do is you're going to pick a 3-digit number, and you can change this range here. So I kept it as range 1 for this first instance here. And so picking 3 numbers, I could have decided to pick a random integer from 0 to 999. But instead, I decided to split it up here just because that's the way a lot of lotteries seem to do it. So just to show you, so you're going to, you know, get these random integer from 0 to 9, but you're going to get that for 1, for 2, for 3. And then since I want it to be a 3-digit number, I'm going to say, you know, 1 times 100 plus 2 times 10 plus 3, and then that'll give it a 3-digit number. There you go. And then there's your winning. These are all integers, so then the multiplication and addition works, and it's an integer that I can compare. So there we go, and it's going to print the winning numbers. And then you already have your pick up here. So if your pick equals that, great, you win. And let's just say I just picked, you know, maybe you win $500, let's say. There we go. Or if you lose $1 because that's probably about the cost of the ticket. So I have these commented out. And after all that, then it's going to print, you know, what's in your bank account. There we go. Pick a 3-digit number. All right. 4, 5, 6. There we go. Winning numbers. Oh, so the winning number was 4, but it didn't print out the zeros. It would have been 004. That's interesting. So, yeah, maybe I'll think about changing that display. So what I have here is then, yeah, there you go. So you played it once and, you know, you lost money, but I have this that you can change the range. Like, let's say 365. Let's say you play every day for a year, and I'll keep all of this, but then I will comment out all of these because I don't need 365 extra lines for whether you win or lose. So you see, now we can just, everything, you pick your one number. Let's say you play the same number every day, and you can see that, you know, if you happen to win, you're going to get $500. If you lose, you're going to lose $1. And if we run that, so there we go. I'll pick, you know, 777. That seems to be. Oh, and look at that. So we did win. So, you know, you come out ahead. If I can run this again. Pick a number. There we go. 789. And lost every day. So $400. minus 365, we lost every day. Or there we go, 2, 3, 4. And what's interesting is you can do this. You can simulate all these different gambling situations. You could make it, the pick 4, pick 6. You could make it, you could change this to simulate, the various, other, lotto, Powerball, whatever. You can change this to simulate various lottery winnings and, see how lucky you get. So yeah, just interesting. One more thing. And I have this just to show you just one other person online that now all this is connected to Project Euler. Pretty cool. And this person put together, I'm just going to show you this link here. And you see it's like, this. And now what I just did is I printed out some of these. So I'll show you this so that it's a little bit bigger and easier to see. But each one, that whole page has, like 500 lines of poker hands. Let's take a look at the code for a second here. So here, if you want to print all that out, it's actually fewer lines than I have here. Import the URL library. I split it up as a separate variable, target URL, and then put it in quotes here. So there we go. And I'm going to store this as my variable. I'll just call data, URL lib.request.url open. There we go. And this is one of the ways to just open this and copy things from that page rather than, store it as a variable here. Because you could, in this case, I'm storing this data as a variable, but you could also store the whole page or even more. But I'm using this variable here, opening that URL, and I just included this. You can do the whole thing, but I just put a limit here. And so for line in data, so there we go. So I could just go through this. I call the variable line because when you print this out, what it's going to print out is one line. And that's what this is. So the one line, when you print this out, this doesn't show up. So you're going to get that B and the single quote at the beginning. You're going to get the \n and the single quote at the end. But then this is the line that we have. And so notice, each of these represents a card for two different hands of 5 cards each. So the first hand is 8 of clubs, then of spades, is that a T for 10? Yep, probably. K for king of clubs, 9 of hearts. There we go, 4 of spades, and 1, 2, 3, 4, 5, and then 5 cards for the other hand. So now, again, just printing it out, you could have just gone through, there's your simple loop, and done. Loop through it for line and data, print line. But what I did is I wanted to store it as a temporary string, and that's going to keep overwriting it. So this is just for an example here. So it's going to keep overwriting it, and then later on, I just use the last one that came up. But what I did for the limit and the count here, so each time it counts it, and then if count is greater than limit, then it's going to break. So that's one way to limit. Hey, this is a lot of lines. I just want to print out 10 to see what's going on, and then print out that temp string. Just as an example. So this is going to end up being the last one that I loop through, but index 2, because I want 0, 1, and then 2 is going to tell me that. So there we go. Because it really brought it from here, that last line that I took in, index 2. So these are some of the things that you can do in here. Take each of these and encode it as something, give it a value. That might be something that you could do. A lot of possibilities. I just wanted to show you, here's one example of a place that has a bunch of these resources, like 500 poker hands. Here's just one way to read that and display it and grab information from there. And, that's going to continue on. The goal here is to make some sort of game, more than one if you'd like, some sort of gambling, game. And part of that is, looking at the probability and calculating that, testing it, keeping score. And if you do this and you run it a lot, you can iterate through these, then you might realize, how much money you are losing, and, the benefit of it being just variables instead of your actual bank account. So, seeing the probability and also seeing, the math of gambling, we want to put our time and our effort and our money toward things that give us a good return, like analyzing the data. Betting on it, probably not a good investment. Analyzing the data, good investment of your time. So that's what you want to be able to do. So if you've been building your notebook along the way, this is a chance to check and see how it lines up with some of the things we've been doing. Maybe you forgot to put something in, or you want to include something more. And I'm going to add a few things and just talk about how I would organize the notebook here. All of these, periodically, if it's something major, I'll make this a heading like this so that it shows up in the table of contents. And then we can see all the different major things that you'd want in your table of contents. I have here the first few ways, like some major ways to get data from, a CSV online, or if you want to upload a CSV. And so over here, you click on these and you get to, some code samples. And what I do is I put like sample URLs in there just as, a placeholder. Maybe you can like test it, and then you can, comment out different things. Maybe you have a few of the things that you want, and, comment this out or add a different one. Uploading, because maybe you've downloaded it, you have it on your computer, and, this creates a dialog box. Or just from a different web page. So, all these, notice we're using pandas, maybe there's a table on a web page you like. So I like to put all these, all the things we're working with, we need to get the data somewhere. Read data from other file types. And notice some of these, if you get the table somewhere and then you have the URL, or maybe you store it as a table, a good way to put this in is have all this as one step, so then you can continue the code. Now that you have it as a table, you can do some things with the table here. So I have this set up. These are some good things like I have as like a document that you might, or a notebook that you might want to include as yours, and have, all these references. You could always copy the code into something else, or you could just work on it from here. Maybe you have, this code, and you keep this, modify one thing, or easily add, some more code or text in here as needed. So, we're trying to kind of build this like nice like notebook, pre-calc calculator for yourself. And, just here's some of the things you can do. Another example. So again, reading data from different places. And notice all of these, I have, the heading, but then over here, within that heading, some of these, it doesn't deserve a heading on the table of contents, but, if you get to this, as example, data on a table from a web page, and then within here you have other examples, text, but it doesn't need to be a heading. And again, you can organize this your own way, but this is just my suggestion. Trying some different things. So, we put code in there that works, and then you can have it to use. Authenticating the connection if you want it from a spreadsheet. Maybe you have a spreadsheet in your Google Drive. And notice this is the snippet that works, and when you do this on your notebook, you can authorize this and connect it to your Google Drive. So again, do this once, and then once you have that, you can then reference that worksheet and get the data from there. Other file types, especially if it's in a URL, notice here this was just called filename.xlsx, and yeah, an Excel file that somebody might have put up, and within pandas, we have the function read Excel. So, they have corresponding functions for other file types too. So we have all these drawing lines. So just, kind of going through what we've been doing with the course, and, you might have seen, you remember the different code that I showed you, but here's how I'd put together like certain parts of that. Some of these were nice examples as we went through it, but here's just a nice notebook of stuff that works that you could use. Different ways you might want to just draw lines here. And then, each of these was its own separate thing, and that might be nice, and, show the graph. Or more elaborate, you can have an array of points, and that way, again, here's the code that you have, and you could, maybe like this, comment it out instead of deleting it, and you can put another array if you have, some different points that you have, you want to draw something. And the triangle. So notice the triangle gets to the, it's another heading on the table of contents, so that you can jump right to it. And we have everything here in the triangle, drawing triangles, and it'll display it like this. And we just might use that as a reference for all the Python trig functions. So here we have everything, if we do it in degrees and then we convert it from radians here, complementary angles, all the different things that we were doing. And this way you can, get the sine, cosine, and tangent of various angles. You can even keep, this as an example so you see what you're expecting it to output. And then as you change different things here, then you can, update that values. I kept this in here, going through the range of the sine functions just in case, you might be interested. So some of these, you may use more often than others, but you'll have all these here. Converting to degrees. So, we have ways to convert to degrees to radians, but there we go. Angles and sides. Conventional labels, because it just gives you that, again, the triangle, capital A for angle A, lowercase a for the side across from it. All these things that you can include, and you'll have all this. There's a link to this exact notebook, so you'll have all this code available to you. But just going through, using sine to find side measures, using cosine, because these are the things as your calculator. Hey, you can just go in and type these angles and one of the sides, and then remember we went through this, that the one that you don't know, make it 0 and it'll calculate it for you. Side measures, inverse to find angle measures. This one, happen to leave blank for the A, B, and C that you can put in there. Unit circle. Just different things you might want to use or display, or use this code to plot a circle for different things. There we go. Showing the trig triangles. Animated unit circle. If you like that, you can run this code. Pythagorean theorem, and then just showing the different X and Y values. Again, some of these you may use more often than others, but I wanted to include some of these just in case. There you go, converting radians to degrees. And of course, Python has that built in. You can just, convert from radians to degrees. Remember, we were doing this earlier, that you have, you see, math.radians. So you take that angle and convert it to radians, and the same corresponding math.degrees if you have an angle that already is in radians. So we have that, but then it's good to include this just to see, that is our ratio. So, here's what we can do. Degrees to radians, graphing trig functions. And again, you have other graphing utilities, but again, might be useful to be able to do this. So we include this in here. Graphing the circle in different ways, graphing sine, and all these. So now, as you see in this, all this is in the table of contents. So, some of these you might have, if you go to the table of contents, you may or may not, need to jump to these. But we have all these, so you know what you want to jump to graphing. And maybe if you're looking to calculate something, you might skip down to all these different graphs. Sine wave transformations, and then giving it interactive sine waves. So these are, now you have, interacting sine waves. You could jump right to this and adjust some things and, see some interactions here. Tides, as this one example. Tides. And then, you can make, you could use this. We'll look at some other uses of data in a little bit. Law of sines, law of cosines, area, solving any triangle. Some of these you might jump to more often. Triangle from points. And there we go. So, these are some of the things you might jump down to. Hey, I have 3 points. Can I draw a triangle? All the different matrix operations. So again, you see certain ones, all this under this heading, and then you have text here for each individual one. So you can jump to that and then just, look at which ones you want to use. And then, here we go again from the table of contents, a quadratic equation from 3 points. So you'll have this full example, solving a system of equations, inverse matrix, and you can jump down to this, different ways of encoding and decoding messages, the non-matrix method. We have this, and this is something you could use, and then if you wanted to, you could change. I think that this one had just a very simple cipher, and you could change this one. So we have this, and then the matrix method of encoding, even with a little bit of directions here, every 2 characters becomes a 1x2 matrix, multiplied by a 2x2 to encode it or decode it. So, there we go. All the different steps, encoding and decoding. And again, you can copy these, change whatever matrix you use, and you have your useful encoding and decoding code. Complex numbers. Of all the things we did with complex numbers, I is a square root of -1. I wanted to include just these two things, calculating and displaying, because again, you might, it might be a nice refresher if you don't use this and want to use this, how to create a complex number, how to break out the real and the imaginary parts and display those. Another way, if you just want the complex part, then just still make, or just want the imaginary part, you can still make the complex and just the real part is 0. So we have these, just some things, graphing on real and imaginary. So how you can import these labels. This one I kept it there, but commented out any title. Creating a complex number, and then again parsing out the real for x and the complex and the imaginary for y, and plotting it. So some useful things. Maybe you don't come across complex or plotting it often, but maybe there's some fractal you want to do, so this could be the basis of what you work with here. And you would put your fractal here in the points. Somewhere in here you would change that. And I included just the full Mandelbrot that does work. So just in case, and what I did is I used ChatGPT to get this, and then I tinkered with it a little bit. So then here's some just alternate values that might be interesting. So then we're going to get into some other things like projectile motion. So in addition to all these things that we currently have, the next few videos we'll look at projectile motion, some things related to that, some other more useful trig functions, logistic growth, all kinds of things, a few physics applications, and we'll look at how you can just add these to your code here. Might as well make it one unified notebook as a reference. So in all the things that we have so far, you can add some other things and some things that I show you, and whatever formulas you come across, and hey, I might use this formula pretty often. There you go. Write some code and add it to this, and you're developing your notebook calculator. So hopefully this gives you a good sense of what it might look like so far, and the next few parts we're just going to add to it. So one of the other useful formulas, and this collection of a few formulas here, relates to projectile motion. Now we have projectile motion formulas, the quadratics, that if I'm launching something straight up in the air, we can calculate height and everything like that. But this depends on the angle. So now we introduce trig to this. This depends on the angle that we launch something. And we see here from the formula, v squared times the sine of 2 theta. So the velocity, that's the initial velocity of whatever we're launching. And remember, this goes for any projectile. A ball that you kick from the ground, or something you throw or toss in any way, something flying, something shot out of a cannon or whatever. We have an initial velocity, and then we have an initial angle. So now if we notice, and certainly then divided by g for gravity. So if we notice then that if theta, it's a sine of 2 theta. So if theta is 45 degrees, or pi over 4 radians, then 2 theta would make it 90 degrees, and then the sine of 90 is 1. So that's the optimal angle. We can see this, that you're not going to get higher than this, a sine value of 1. So great, now we know the optimal angle, but then any other angle, we would just put it in this formula, sine of 2 theta times the initial velocity squared. And I like the default going to, standard units. So velocity would be in meters per second. And here's all of this running, running through the code. Initial velocity in meters per second, initial angle. And we can put this in radians so that we don't have to convert in the formula, but you could always have it in degrees and throw another line of code here to convert to radians. And then the gravity in meters per second squared. So we'll keep that as a constant here. If for whatever reason you wanted to change it to feet per second for velocity, then gravity you'd have to change according to that, make it 32. But nonetheless, here we have then the range. We have v squared times the sine of 2 theta, and notice a for the angle, all that divided by gravity. And then we're going to print 3 decimal places is fine. So then, I like doing the formula here and then the print statement next, round it to 3 decimal places. So that gives us the range of a projectile. And then supposing the ground is sloping at an incline. So we'll call the angle the incline B. And this is the formula. Notice slightly more complicated. And we can get into this sine of 2 theta minus b minus the sine of b, and then cosine. The denominator now becomes gravity times the cosine squared of b. All of this, right? And we have, very similar. We can have this initial velocity, and I just picked values to plug in here, but you could always change these. And this one as just an example, I made the slope just, instead of pi divided by 4, this ultimate, I did pi divided by 4.1. Make it a slightly lower angle so, we're not running into the slope there. And here's the formula, notice with the extra parentheses. And there we go. So we have, all these that we can adjust. And again, useful formulas. You can figure out the range of different things. So this one's going increase, at a slope that's an angle. Now, on a slope declining, and so declining, I just called it D, angle D from the horizontal, slightly different formula. And we have this, notice some similarities, but different formula, 2 times initial velocity squared times the sine of theta times the cosine of theta minus d. And there we go. So that's d is the angle of depression going down from the horizontal. And we can plug in here. Again, I just picked an angle. And here's the formula for the range. All of this just written in Python. And I might want to find out the maximum height of a projectile, because that's interesting. Maybe it's something I need to get over, or maybe it's, I don't know, a roof that I need to stay under. So the idea is you can use these, and notice this one, sine squared of theta in the numerator, and then 2g in the denominator. Just slight variations. So for each of these, formulas you might happen to use, if you happen to, work on, I don't know, designing something or planning out something, then, some formulas that you might find useful, and then you can have these built in, change a few numbers and calculate. So, there you go. Who knows? Maybe if you have some sort of model rocket, you can predict where do I want this to land, and we get what initial velocity, what angle, and we can adjust that. So these are the 3 related to projectile motion, and you can include these then in your overall notebook. So here's one with a complicated formula, but a brief explanation. If you want to calculate the number of hours of daylight on any given day of the year. So here's one. We'll take the latitude in degrees, because normally north latitude, south latitude, we'll reference them that way. This one, not only is it less accurate beyond 65 degrees, but actually the formula doesn't really account for that. So keep it, 65 degrees or less. You'll see at that point the hours, and then it gets more extreme around the poles. And so capital L is the degrees, latitude, capital J, day of the year. And I have the link here of where I've got this formula. It was an Ask Dr. Math article from years ago. So just here's the several steps calculating the, taking into account the angle of the sun, the angle of north latitude, and you go down here and then you're going to print the daylight hours, rounding it to 1 decimal place is probably fine. So there we go. We get, just in case you want to plan out, how many days of sunlight or how many hours of sunlight do I get on a particular day? And again, one of the other good ones you can add to your ongoing notebook of formulas. Here's another good, useful formula, logistic growth. And kind of connects with exponential growth where I have some sort of limit. And that's what C in this numerator is, the carrying capacity or the maximum Y value. So you could have a population that grows and there's only really a certain amount that the environment can sustain. Or, anything that grows but does have a limit, and then at some point it will stop growing as quickly. It doesn't completely flatline, but there is a definite horizontal asymptote there. And at 0. So we're usually talking about things we can count. So there is a horizontal asymptote at y equals 0. We're not going to be talking about negative y values here. There is a horizontal asymptote at y equals c, which is that carrying capacity. And what we have is, in this formula, a in this denominator. So if that a value will always be positive. And we see that we're doing c divided by something. So we can see that as this denominator gets really big, then that's when we get closer to y equals 0. But this denominator could get small, and then that's where we get to that carrying capacity, but we see it will level off. This negative in the exponent is a part of the formula, and then b, if b is positive, then we're talking about growth. And if b is negative, then we're talking about decay. So these are the asymptotes, but you could have something that decays. You start out closer to y equals c, and then the population dips down to, closer to 0. So this is the formula, logistic growth, growth within limits. And here we have, we'll import some things because we're going to graph this. That would be the interesting thing, to see what this graph looks like. So, I just put in some nice, except for this one, integers. Some c value, c equals 10, a equals 2, whatever it is, it's always positive. And growth, I wanted to make it a growth function, so I just made it 0.3. A lot of times this is the rate, but that's a good way to understand it. But there are some situations where the rate's probably not the best definition. But there we go. So this would be something that, we do have growth, but a limit. Now, giving a function like this that you can graph for all sorts of different logistic growth formulas. I mean, you could have logistic growth, like some small numbers here. I had like 10, a is 2. You could have a and b be even tiny decimals. You could have c be a huge number. So we want to capture that trend. So what I did here is, in our graph, to find minimum and maximum x values. So there is an inflection point in the middle as this changes. So what we're going to do is, you probably won't need to get anywhere near 1,000, but I'm going to run through this loop, and then I'm going to plug this in, once we have our values here. The x value, I just called it x test. So this is the function. Then that y value, all right, if b is greater than 0, we're talking about growth. So then if y is greater than c over 2, because the inflection point will be right in the middle. So if it's a growth formula and then we've gone, the y value has grown beyond that inflection point, we're about halfway. So then what I did is I did multiply times 5 times that x value. That actually seemed to be a pretty good estimate. Get that, round it, convert it to an integer. That's my x maximal. And then my x minimum, they're not always centered right around 0, but I just did 0 minus x max. Again, really good. It seems to apply to a lot of different things. If you're working on something, you can always tweak this a little bit, but it's a really good starting point. So it'll just go through this, and as soon as we get beyond that inflection point, now I have x minimum, maximum, and I'll break. The other one is if it's actually a decay formula, so if b is less than 0 and y is less than that inflection point. So if that's the case, then we'll go through the same thing. I want my x maximum, my x minimum, and then break. So again, that should work for most situations you encounter. And then if you look at your graph, you're like, hey, I want to tweak it a little bit, then you can modify some things. You could even, I just commented these out, but you could even, you don't even have to count this out. If you want to overwrite that, you just, put here x minimum and x maximum, and whatever you calculated up here, it'll overwrite it as your dimensions. So y minimum, remember, asymptote it, y equals 0. So I just put y equals -2, just so that we can see the axis. It's not right at the edge. Y maximum, again, that asymptote, +2. Points, like we've done before in graphs, the difference between the minimum and maximum times 10, and then that should give us enough points to plot a nice smooth curve. Import a NumPy, so linspace, and our graph, made it blue. I like blue. So here we are. Now this y value, so, x, just x, that's my x value, looping through that array, and my y value here, all right? And if we plot this, then we see for those points, we get that trend, and then there's 10. We can see that, we see enough of this graph that we see it level off at 0, we see it level off at 10, and we see about where that inflection point is. That's what we want to look at. This is the logistic growth here. And then if we wanted to make b something negative, and I'll just do everything and just change it to negative, and if we run that, then we will see. Now, sleight of hand, I actually just change this, and for making it negative, it will switch it. And you see, that's when b is negative, so it starts at a higher number and then gets lower. But because the x min and x max ended up being really close, it was giving an error. So I added this other bit that if the absolute value, and rather than just making it equal, I just wanted, if I subtract x max minus x min, giving me my range, if that's too small, then the absolute value of that would be, I just said less than 20, because then if it is less than 20, then I'll just make x min -10 and x maximum 10. So that's, I like that as a nice standard window anyway. So we're going to calculate it, but if it ends up being too close, you're not going to see the effect anyway, so then we would overwrite that. And then we would get this. And these are ones where you can see, hey, maybe you want to see more of this, that you have, you want to see, instead of stopping at 10, I want to see it get close to the x-axis. And it wasn't perfectly centered around 0, 0. So, I want to get it closer to that y equals 10. You could always do this knowing that we're going to end up invoking this one. Then you could change it here and make it, -20. And you could make that +20. Might not even have to make it as big. And we can run this. And you see, you just make that a little bit more and you can really see it get to that horizontal asymptote. And then it'll even off from there. And then if we made the window even bigger, you would see the extent of this. So you see this one's starting from high and then getting low. That's when B is negative. So, it just goes back to this negative B value. So there we go. Logistic growth. We can use this for planning a lot of things, a lot of population and carrying capacity, and sometimes even investments. You can use this. Sometimes things like sharing information. Things start out really quickly. That would be definitely a growth model, positive B value. But things could start out really quickly, and then by the time everybody knows this information, it can only spread so much. Or business saturation. Companies open so many businesses, but at some point they're everywhere, and then they can't open as many as quickly. So, there we go. Let's talk about limits. And we got a glimpse of this from before when we saw the logistic functions approach an asymptote. And so we could say that the limit of that function, the y value that it can't get to, but it gets really close to, the limit of that function would be this carrying capacity. And a lot of times, you can just put something in the graph and see the limit. Even if it can't get exactly to a value, what does it get close to? So here's an example of a really interesting limit connecting pre-calc with calculus. So if we graph these, I'm going to set the dimensions, and then this is the graph we're going to plot here. So sine of x divided by x. Now, we know that there's at least one value there. X can't be 0, so what happens when x is 0? But if we take a look at this graph, we can still plot it. It will still plot that and go right around that notion that, it can't exist here. And you might not even see, it doesn't even display an error. Most graphs, you won't even see the difference because it's really microscopic. But exactly at x equals 0, this doesn't work. But we see that the value of that looks like when x is 0, y is 1. So, the value of this when we get to, around 0 is 1, sine of 0 over 0. But what if I just actually try that value? So we see the value down here. If I have everything else that I just ran, that's still in the short-term memory of the Google Colab for a few minutes. So what if I add this, x value of 0, and then I just print the value of that? Sine of x divided by x. And I'm going to use this x value. So you see, error, and it'll say 0 division error. Now, certainly if I, put any other value in there, it'll give me the value, that's fine. But I can't do it at 0. Yep, gives me the error. So here's how I'm going to address it. I'm going to assign this difference here. And this difference can be any number, but let's make it really tiny. Like 0.1's fine. I can make it 0.001. So now I know that x can't be 0. And maybe I'll still put this x value down here just to not have to scroll up again. So that x value is 0. I'm going to make this difference here so a little bit to the right, because if I'm looking at the graph, if I add something to this x value, it's a little bit to the right of the other point. So x value plus the difference. Or a little bit to the left, x value minus the difference. Now, let's print these two values here. And we see they actually match up really well down to, many decimal places. I could even make this difference well, if they match up here, they're going to match up there. But the interesting thing with this is I can make that difference a tiny, tiny number. And look at that. It's so close that it rounds it that they're both 1. This tiny, tiny difference is so close that that's why it didn't give an error on the graph. That we could, we just call it 1, which it really was 1. Notice when I got to, even 0.01, it's still very close to 1.99998. Really close. But, I would certainly round that to 1. But, it's far enough that it'll give me all those decimal places. And you see, if I make it even closer, then we get this limit. And this is the notion of the limit here. That, this works because if I do this from the left and the right, then they are different values. Now, if I just went back and, never mind sine, what if I just said, like 1 over x? Now, that one, you see, this middle line that's red, that's a weird glitch here, that it should just display that as the axis. But you see, x can't be 0 here, but then it approaches from the right and the y value gets really big. It approaches from the left, the y value gets really small. And neither the twain shall meet. So I can say that there's no limit. Like, that just won't work. I can't, even if I try to make it an approximate value, it's not going to do us any good. So we see some interesting things like that where we have, a limit that, this limit does not exist because it's different from the right and the left. Whereas that, sine of x, cosine, ironically, also works like that. Does not match up very nicely. You see? And right at 0, this vertical line is actually not a value. It does not exist here. So, yeah, cosine, and a lot of them, from the right, from the left, does not match up. But our sine value matches up very nicely as one of many functions that if I have something that it can't exist exactly at this point, but anything even really close works, and if I go a little bit to the right, a little bit to the left, I get the same values, then we can say that this limit exists, and in fact that limit is this number. So I can't plug in 0 and get 1, but the limit as x approaches 0 is 1. And this, you could graph a lot of things, just straight up put it into a graph and see what it looks like. But then you also have this notion here of testing the right and left values. Whatever function you have, and then you can just test the right and the left values. Adjust the difference and then see what it does. So this is really, there's so many things in calculus that once you throw in, the actual graphing utility or writing code, a lot of it just falls into place because you're just going to, run it and see what it looks like. So you don't have to memorize all these limits, but, the more you work with them, the more you'll get familiar with them. And this is going to start connecting us with some of the things that we'll do in calculus. So here's something that you might not have thought about doing on a calculator or a notebook, but factoring trig functions. And as an example, you're probably familiar that sine squared plus cosine squared equals 1. So this function here, and this is just what we need to import from SymPy, import everything. And then I'm going to just define these two symbols. You could define more, you could make them A and B, whatever. And I keep this just to make sure that it prints out nicely. And all of these, you don't have to use a print statement. It's just the last line of code is what it'll output. So I commented out all these. This is what it's going to display. So if you do something like this, trig simp sine squared plus cosine squared, then it outputs 1. And all these things, it can, the fact that it can factor this, a lot of times, I tell my students, oh, at this point, the calculator won't help you. Oh, but your Google Colab notebook will help you. So, we could just do this trig sim. I wanted to show a few of these. You see, it'll do that Pythagorean identity. And then it will also do this one, 1 plus cotangent squared. And if we run that, see, it's very interesting. It sometimes will output secant, cosecant squared, but for the most part, it wants to do everything in terms of sine and cosine. So 1 over sine squared is what it'll do. And, you might hopefully remember that that's cosecant squared. The same thing here, if we take a look. Now also, even if I leave this one, it might run this, but then this next line overwrites it, so we won't see. So you see, if I do like 1 over secant, not squared, if I just do 1 over secant, and I run that, it did that. It will give me cosine. So, it likes to put everything back into sine and cosine. But if I do 1 over cosine, it won't give me secant. It'll give me an error. Oh, also because I put no. That will definitely get you an error. But you see, 1 over cosine, it just returns 1 over cosine. It won't put it back to secant. So I'm going to, in this notebook that that I will share with you, I'm going to leave these here as, some notes and reminders. And notice this, it's that same function every time, trig simp, because it really wants to simplify. So as we look at this, it wants to simplify, and in Python perspective, that goes back to sine and cosine. So you see, in terms of simplifying, I won't even uncomment this, but this one, sine of x plus y, that's simple enough. So no, this won't work. It won't. If you do that, it'll just return sine of x plus y. But sine of x plus y equals this, sine of x times cosine of x plus cosine times of x times sine of y. So if you run this, it will give you the sine of x plus y. So you see, it goes in that direction of simplifying, because that's what the function is, trig simp. It will simplify it. So if you put in the simplified version, it won't make it more complicated. Because, certainly, any simplified version you put, there's a few ways to make it more complicated, and it won't do any of them. So, you put this sine of x cosine y, there we go. So if you want to do it the other way, you're kind of out of luck there. And in the same way, put that comment back in. In the same way, it will, sine over cosine. And when I run this, it will simplify that. That's pretty straightforward. Sine, cosine, tangent. But if I ran tangent, it won't break it down into sine and cosine. And you might know from factoring trig functions, maybe I have tangent, I want to break it down to sine and cosine. It won't do that. Now, this would be like in conjunction with other things you're doing, or maybe to check things you're doing. So, the fact that some of these, can I take tangent, write it in sine and cosine, that might be, a good way, you'll know how to do that, and, you can use some of your brain, not write code for all of it. But there you go. It'll simplify that. The weird thing is the half angle formulas. It won't do it. Neither. So now this is the simplified version. So I would expect that it wouldn't complicate it. But this should simplify to tangent of x over 2. And it won't do that. So the half angle formulas, for some reason, and I'll keep that in there to remind you, for some reason that's just not built in. Who knows, maybe another version. But yes, the double angle formulas, it will. And once again, sine of 2x. Remember the one thing, it'll display it nicely here, the tangent of x or this. But when you put the input, you have to remember these multiplication symbols, for Python. And you have to remember, the x, for the exponent. So sine of 2x, no. But then you see, if we go to this one, that does simplify to the sine of 2x. So we will do that. And you see, SymPy, it will output that nicely, sine of 2x. But anytime here, you have to put the multiplication symbols in. Still need that Python syntax. So we have this. Notice the other double angle formula. I didn't do all of them here as examples, but it will do all of the double angle formulas. And you see this will simplify to the tangent of 2x. Nice. All these, we'll just run through a couple more here. Trig sim. So, and notice this one, I also included just a reminder. So this sine of x plus the sine of y, it won't do, but it will do this one and simplify it down to that. And notice it just put 1.0 times this. That's fine. But yeah, it will simplify this more complicated part and break it down into the sine of x plus sine of y. So pretty cool, but it won't take that and make it more complicated. And even just, one more, one more formula here. Shift enter and look at that. Good times. Good times. So you could, keep all these. You could, put some other ones in there. But one of the things, if you're working on this in conjunction with, other problems in a book to simplify, you can use this to check, or you could try it. Put everything into one and see if it works. Hey, I need to simplify everything on this side of the equal sign, and do it. Trig simp, give it a try. See if it works. So there we go. Some good trig factoring for you. So here's a bonus, because remember we're building this, resource center here at Google Colab. One of the other things you can do, and we'll do some math to this too, is find all the elements of the periodic table. So, we import these modules for some things we're going to do. And remember, you can just, run this. Then you don't have to do the import every time. We can read this data that we'll use. And, this guy, Adam Lemie, he posted this. So he's the one that created this. You'll see the credits at the end. Run that. And now that we have this, hey, we can display the first 5 rows. Or the first 20, and we see, we can display the heading. We can not put a number in here, remember, and then if we just get the first 5, can put any number. Especially data sets you're not really familiar with how big it is. You want to just get a sense of this. And then, so this is all the headings, but let's say we want just the names. So we can do data.name, and I don't have to comment this out. It'll just do, the second line will overwrite the first one. And look at this. It listed all the names. So nice, ordered by atomic number. This is great. And supposing I just wanted one, then I could do a number in here. So if I could do there we go. And we can see we can pick this. So other things we can do. We can look at the math and calculate, pH of things. There we go. So again, all these different things we're referencing that data set that we just stored as data. There we go. And we can just calculate some things, the mass. Notice negative log of the hydrogen concentration is the pH. So here we go. And we can just list the names of all the columns this way. You see, I could list, like I did before, name and list everything in that column, or this one lists all the column headings. Maybe I want that. There we go. The shape, rows and columns. There we go. This can give you some information that you need. And more things we can do. Maybe we can, do some math to the shape. Here we can graph some things. And, I commented this out, but we have, you can plot. If you know that this is going to be a number, and we know that this is going to be a number, there we go. We can plot those. And to arrays of these numbers, and we see, because what do we have going across the row? The radius increases, but then you're at the beginning of the next row. So we have all these, some things we can graph. And you could always, change this. I think this is funny, something versus something else. But, you could always change this. There we go. Number versus radius. And then when we run this, there we go. Pretty cool. So any data set in chemistry, there's going to be plenty of math we can do. So we can sort values. You see, we can sort the table in different ways. And all of these, you could keep this. I'll make a copy of this. And you see the way that this is sorted here. And then the table of contents really just has, 3 parts. You could always name the different parts to help you jump to the ones you need. But there we go. The headings here. And notice how they had the headings underneath. If I double click, you see 2 hashtags, and that makes it a subheading. So this will help you get more organized with some of the things that you might be creating. Yeah, you can keep it as one notebook. Maybe you just, go to it and, enter values, overwrite it, and take it from there. Or you could always, make some sort of customized analysis and do a save as, save a copy, and then do your customized analysis on your copy. There we go. And as you see, he has some nice directions here on some of the other things that you can do. All right. And here's where the data came from. Here's where the, formatting, ETL, exchange, transfer, load, all very important. Otherwise it might be a mess. There we go. Located it. And, there we go. And here's the guy that did this. We have Adam Lamy. There we go. So, yeah. Give him props. This is good. There we go. Coding in K12.org. So, pretty cool. So, some other things that you can do with all of your collab skills. And really all this, especially when we see these things that we're doing, we've been doing a lot in math with NumPy. So really that's like the winning combo, pandas and NumPy. Get it in some sort of, version that I can do math with, and then use arrays and do the math. So you see, so we could, we could loop through. So just like we have name, and notice the indexes here. So we could look at some things we can do with this mathematically. Now, we could even really, try to do some sort of like weird sinusoidal function for this because it's up and down. I think that's too choppy, and we see it as too choppy, so that wouldn't help. Sometimes it's good if there's something I can predict. If it's, not getting a better answer than what I already have, then it's no good. All right, so we could have like melting point and boiling point. This could be interesting. Maybe if I have this data dot melting point, and notice how easy this is if there's no space, because that would mess it up. So, encourage your friends to, make table headings with no spaces. That way you don't have to mess with quotes and such. And so we see all these melting points here. And what we can do is we could, add up those melting points. And again, summation, we could do this as a list, or we could do it as a sum. And we could, graph these melting points. So the same way that we did, some of these other graphs here. So you see, if we have atomic number and radius, we could do this. And so if we really look back at atomic number, we could even just overwrite this for now. And what I like to do is comment something out and then you use that later. So we could, there we go, atomic number and melting point. There we go. And there we go. Yeah, very interesting how it goes, up and down also. Yeah, really interesting. But the important thing is looking at this as some sort of graph that we can get these arrays of numbers and then plot these points. So, just one more bonus. This is really, all these different things we're learning for pre-calc with Python. We want to be able to also apply it to all these different things. And this is really what I want you to see, that then, with that little bit connecting with what we were doing at the beginning of the course, can I find data in different places? Can I get it in a table? Can I read it, probably using pandas? And then now all the things we've been doing in the course, what can I do to do some math to all this, and then look for interesting patterns, do some calculations. So hopefully this all brings it together and you enjoy the course.
I hope you enjoyed Precalculus with Python. Hopefully now you really feel comfortable with your skills, using trigonometry, finding the sides and angles of any triangle, even with little bits of information, working with trig graphs, repeating patterns, getting data, analyzing repeating patterns, appreciating the beauty of e to the I pi equals -1, working with sequences and series, and all these things. Then now you can take this and run with it and apply these skills to all kinds of new data that you come across. So hopefully you got a lot out of this, and this is leading up to calculus, where things are going to start to move and we're going to look at other sorts of interesting trends. So happy coding.